Now let us see the property of surface tension. You know, when a drop of blood is dropped on a glass surface, it is formed into a approximately spherical hump. Suppose mercury is dropped on a glass surface. It is broken into number of small spherical shaped droplets, and you can roll it like a steel ball. This is also due to surface tension. Now let us see a liquid fuel. A liquid fuel injected into an engine forms a mist of bubbles. Water dropping from a leaky faucet or surface also will have a nearly spherical droplet shape. Suppose water is dropped on flower petals. It also will have the shape of a spherical droplets. As you know, a soap bubble in air is also of a nearly spherical shape. So all these natural features we observe in our daily life are due to surface tension. Now what is the definition of surface tension? How it is developed on a surface? Let us understand from the basics of molecular cohesive forces. Now let us consider a container partially filled with a liquid, say water. See here. Now here we have molecule at the surface. Consider another molecule inside the liquid. As clearly shown here, this surface molecule has towards the bottom the same liquid molecule, whereas the other side, say a gas or air is there. It means it is subjected to unsymmetrical forces. Let us say outside air is there. The force of attraction in between the air and the liquid, I can say negligibly small, whereas attractive force towards inside, which is nothing but cohesive force. What is cohesive force? The intermolecular attraction of the same substance. Of course, here liquid, let us say water. So here the cohesive forces towards downside on the surface molecules are much more than the force of attraction by the air towards outside. Hence there is an unsymmetry. So because of this unsymmetry, the surface molecules are pulled down. They are, you see here, they are net force is pulling down. Now if you see the inside molecule, it is surrounded by number of molecules of the same liquid. Hence there is a symmetry. Because of the symmetry, the forces are balanced, symmetrical, balanced all round. So it is not going to be influenced, whereas the surface molecule is subjected to an unbalanced normal force towards downside. I'll tell you with respect to strength of materials, just for fun. Assume this is a cable. This is a cable. Assume a load is applied here. Now all of you can guess. The cable is pulled down. Once the cable is pulled down, this cable is subjected to stretching or some tensile force. Same logic here. Because of the unbalanced normal force towards the downside, the surface is subjected to tensile forces stretching on the top surface. So this unbalanced force is the reason for stretching. So the tensile force on the top membrane is called surface tension. In one previous competitive exam appeared. What is surface tension? Surface tension is the downward normal force. Is it? No. Surface tension is the force developed parallel to the surface, along the surface, along the membrane, but it is due to the unbalanced normal force towards the downside or towards downward. So the surface tension is due to the unbalanced normal force, due to the asymmetrical forces, and it is the force along the membrane or parallel to the membrane as discussed earlier. Now let us see the mathematical definition of surface tension. In fact, surface tension is represented by the symbol sigma s. Sigma s, surface tension, is the force per unit length. This is the general mathematical definition. How it is? Now you see here a rigid wire frame, it is having a surface of a water film, clearly shown here. Suppose here I am applying an external force. Assume that external force is not there. In case that external force is absent, what happens? Can you guess? Try to guess. What happens? That wire frame in fact will pulled inwards because of the surface tension. Now if you apply the force, the movement of the frame inside is stopped. Now let us, I am applying the external force F. The surface is subjected to stretching. Say the dimension is B, small b. Now what is this? F. So F is equal to, for equilibrium, F. Now if you see carefully here, there are two surfaces. One is the top surface, another is bottom surface. Okay. Sigma s into 2b implies sigma s is equal to F by 2b. It is nothing but force per unit length. I think you can understand why I have taken 2b, because one is two surfaces are there on either side. So surface tension is mathematically the force per unit length. Fine. Surface tension is also defined as the surface energy per unit area. Now let us see how it is. Suppose due to the external force applied, assume the frame is moving towards right side, it is subjected to stretching. Now how much is the distance, additional distance or additional surface area created? So now some work is done in increasing the surface area. Let us say work is equal to force into distance. This is we have studied in our childhood. Force F, distance as shown here, it is x. What is force? We have already derived sigma s into 2b. Now this is x. I will keep this 2b into x into brackets. So this is sigma s into some area. I will say this as delta A. Some additional surface area is created. Of course, now work is also called surface energy. So sigma s is equal to work by area. We know work is equal to energy. Therefore, surface tension is also defined as the surface energy per unit area. Now let us see the units in terms of surface energy. Now let us see the unit of surface tension in terms of energies, surface energies. Energy Newton meter per area meter square or Joule per meter square. Now let us see some more examples as a result of surface tension. The first is here, some insects, say water striders moving on water. You can see the image here. A stabler pin or a hairpin, when you drop on water, it will float. You see the video? Now let us see factors affecting surface tension sigma. The first point is cohesion of liquids. As all of you know, surface tension is primarily due to cohesion. Of course, we have already discussed it is unbalanced. It is due to the unbalanced normal forces at the interface of two different media, and of course primarily due to cohesion. Now let us understand this using some numerical data. You see here in this table, water, first forget about the temperatures. So water at 20 degrees centigrade has 0.073 Newton per meter. My dear students, I strongly advise you to mug up this value. Why at 20 degrees centigrade, sir? Generally NTP, normal conditions of temperature and pressure, and 20 degrees centigrade is considered as normal temperature. Because in engineering services exams, prelims exams, sometimes they don't give the values of surface tension like water, mercury. So I advise you to mug up these values. So for water, it is 0.073 Newton per meter. Now once you add soap solution, actually once you add soap solution, which is an impurity, in fact, surface tension decreases because the cohesion decreases. You see the mercury. You know, mercury is having more cohesion compared to water. So mercury at 20 degrees centigrade has 0.44 Newton per meter. So as cohesion increases, surface tension increases. First point. Number 2, what is the effect of temperature? Now let us see the chemistry here. If temperature increases, yes, cohesion of a liquid decreases. As cohesion decreases, we have seen cohesion increases, surface tension increases. But as temperature increases, cohesion decreases. As cohesion decreases, surface tension decreases. Now you see this tabular form here, 0 degree centigrade, 0.076 Newton per meter. Water at 20 degree centigrade, 0.073. Water at 100 degree centigrade, say boiling point, 0.059 Newton per meter. Simple illustration. As temperature increases, cohesion decreases, surface tension decreases. Third, sir, what is the effect of pressure? Of course, the experiments have shown that the effect of pressure on surface tension is negligible. Effect is negligible. The fourth one is impurities, effect of impurities. Let us say some surfactants like detergents, etc. When they are added to a water, say it becomes a soap solution, surface tension decreases. I think this is the reason when soap solution is added to a cloth, wet cloth, the water can penetrate easily to the fibers of the cloth and washing becomes quite easy. So the practical aspect of detergent is less surface tension. So once the impurities are added, surface tension decreases. There is one more additional point with respect to the temperature, how it affects surface tension. That is critical point. Of course, this appears to be Greek and Latin for civil students, but mechanical students know it very well. You know the phase diagram of water. You see the critical point I am showing here. What about the temperature? 374 degrees centigrade approximately. What is the pressure? Approximately 22 megapascal or 218 atmosphere. So temperature is equal to 374 degrees centigrade or 647 degree Kelvin. The pressure is equal to 218 atmosphere or approximately 22 megapascal. These are the values of temperature and pressure for critical point. At critical point, in fact, the surface tension of water tends to 0. Very simple reason is, at temperatures beyond critical point, there is no distinct liquid vapor interface. The liquid vapor interface vanishes beyond critical point. Once the liquid vapor interface vanishes, surface tension tends to 0. Of course, I don't want to deal this in detail. Reason, it will have an elaborate explanation for mechanical students in thermodynamics, and of course for civil students I don't advise you to go beyond this, but whether civil or mechanical students, it is important from statements perspective, something like pick up the correct and incorrect statements or in interviews, that's all. Okay. Surface tension is due to cohesion or adhesion or both what it is. We already discussed surface tension primarily due to cohesion of the fluid. Option A. So another question, what is surface tension? Surface tension, the surface energy per unit area. I think you have already studied joule per meter square. True. Force exerted by the free surface at interface to different media. Yes, this is also correct. Third, the tendency liquid surface to shrink into the minimum surface area possible. Minimum surface area means, so what are the correct statements? I think you know. All the three statements are D option, all are correct. See, at the interface of a curved surface, there will be a pressure difference, also called pressure jump. Pressure jump. You take a general diagram. Say this is a spherical droplet. This is concave side. This is convex side. Actually, the pressure inside this droplet or bubble, that is concave side, more pressure. The convex side, the pressure will be less. So, this difference, suppose outside I say atmospheric pressure. So, naturally inside pressure is more, I told. What is the meaning of more? P more means P atmospheric plus some extra delta P. So, this delta P, this extra pressure I am calling as excess hydrostatic pressure or gauge pressure. You all know gauge pressure means pressures with respect to local atmospheric pressure. So, gauge pressure inside a droplet or a bubble. You can see a practical example in the hydraulic machines also. Suppose you have a blade of a turbine, let us say. So, this is concave side. This is convex side. You will come to know in future that, so the pressure towards the concave side of the blade is more and convex side is less, leading to a fluid phenomena called cavitation, which we will discuss afterwards. So, what I am trying to emphasize here, at the curved interface, there will be a pressure difference, more pressure towards concave side and less pressure towards convex side. This leads to one practical application in the hydraulic machines in the name of cavitation of blades. Now, let us see case 1, excess hydrostatic pressure in a liquid jet delta P. Now, you see a nozzle, cylindrical jet. I am assuming the shape of the jet as cylindrical coming out of the nozzle. Now, you consider a small part of the jet of length L and dia D. Now, the free body diagram of the part of length L. You see the various forces I am showing. Pressure delta P. What is this delta P? We already discussed briefly. delta P is nothing but inside pressure minus outside pressure. And what is the reason for this excess pressure? You know. So because of the surface tension, the surface area will try to reduce, or the water is trying to squeeze. When it is trying to squeeze, the pressure inside will be slightly more than the outside pressure, which is nothing but atmospheric pressure. So delta P is equal to inside pressure minus outside pressure. We know surface tension is the force per unit length on the surface. On the surface. Now you see in this diagram, so you have surface tension force on the circular parts at both sides, and also you are able to see the surface tension force on the straight line portions as shown there. Now I want to show you in separated diagram. So that rectangular part, exposed area, I am showing here as L into D, and the semicircular part also I am showing here. Now pressure force will generally act on the exposed area. So what is that exposed area shape? Rectangle. So some of you may get generally doubts, sir, why not that curved surface? For that I have shown, you see here, it can have a horizontal component, say like this, and here also the horizontal component. So in fact they will balance each other. So horizontal components of pressure forces, they are balancing each other, whereas the vertical component is not getting balanced. Therefore the pressure force on the exposed area, so pressure force delta P L into D. Surface tension force. So this is equal to sigma into L into, see, surface tension is acting along the length, but we have two lines on the boundary, sigma L into 2. So for equilibrium, you have to equate these two. You have to equate the pressure force and surface tension force. Therefore delta P is equal to 2 sigma L by LD. So L will cancel. So this is equal to 2 sigma by D. If you try to express in terms of radius, diameter is equal to 2 times radius, implies delta P is equal to sigma by radius R. Now let us see excess pressure or gauge pressure inside a liquid drop or droplet. Now let us see this sketch. Here I am showing the free body diagram of half of a liquid drop or droplet. We already discussed. Surface tension acts along the circumference or surface. Pressure is the normal force per unit area. Pressure is the normal force per unit area on the cross section shown of the free body diagram. Now, what is the internal pressure force? Internal pressure force. This is equal to internal pressure into exposed area. area of cross section. I say area of cross section. So what is this internal pressure? I told you delta P excess. So delta P into pi r square. Sir, what is R? R is the radius of the droplet. Now what is the pressure force outside? I am taking the horizontal components. So it is nothing but surface tension sigma s into circumference 2 pi r. Now horizontal equilibrium force, what is that? Sigma Fh is equal to 0. So my dear students, now equate internal pressure force and external internal pressure force and outside pressure force or external pressure force. If equate these two, very simple, you will get, I need not do the simplification, delta P equal to 2 sigma s by capital R. If you want to express in terms of dia D, 4 sigma s by dia D. Sometimes in some exam they are saying air bubble. So any bubble inside a liquid or water is treated as water bubble. So the excess pressure inside an air bubble is nothing but same delta P is equal to 4 sigma by D. Now let us see case 3, excess pressure inside a soap bubble. See the free body diagram as shown here. The internal force is nothing but pressure force as usual, delta P into pi r square. Now on the surface you have surface tension force. Of course in the earlier case I might have used the word external pressure force, I am sorry, it is the surface tension force. It is nothing but surface tension force. Force means now sigma s into 2 into 2 pi r. Can you guess why I used an additional factor 2 here? You carefully examine this diagram. A soap bubble will have 2 surfaces, 2 circumferences. Therefore, I used multiplying factor 2. Soap bubble will have 2 surfaces. Now, as usual, sigma Fh is equal to 0 implies delta P is equal to, means excess pressure inside the soap bubble is equal to 4 sigma s by radius r, this is equal to 8 sigma s by dia D. So in the soap bubble problems, I advise particularly students preparing for engineering services to remember the value of surface tension of soap bubble, because paper setters are not giving the value of sigma s sometimes. Now we see the concept of capillarity. See, one of the most practical aspect of fluid mechanics which is useful in real life. Anyway, there are certain terms to be understood before going to the capillarity, its derivations, etc. One of the most important term is angle of contact. Theta. So, what is this angle of contact theta? We should understand in detail. So, to explain this, I'll take the water and the mercury. See here the animations. This is water in a container. Now, this is the mercury in the container. Now, water on the slide or says a plate, solid glass plate. Now, you see mercury droplet on the same slide. Now, you see I have shown a tangent. So, what is that tangent? I want to mention here tangent between the solid towards liquid. Okay. So, solid to the liquid surface nearer to the container wall. I want to tell you why the water has got meniscus with upward bend near the solid wall, whereas this mercury has a downward bend for this meniscus. You know cohesive forces and adhesive forces. So, in case of water, the adhesive force between the solid and the water is more than that of the cohesive force of the water. This is the reason, see, the bend is towards upward, the meniscus is towards upward in the case of water. So, coming to the mercury, in case of mercury, you know, cohesive forces are more dominant compared to the adhesion between the solid and the mercury. So, naturally what is happening? You see the bend of the mercury, it is slightly towards, bent towards downward. So, now I want to explain this angle of contact again. Now, you see for a tangent, the tangent to the mercury surface from the wall of the container. So, tangent between the solid towards the liquid. Okay. Now, what is this angle? So, theta. So, this theta is angle of contact. So, this angle of contact is measured towards liquid. Towards liquid. You see those angles shown? Water towards water, mercury towards mercury. So, the angle between the tangent and the wall is angle of contact and it is towards liquid, right. Now, same thing you can see here on the slide also. You see here thetas are towards liquid, not towards solid. Now, if you see carefully for this water, theta less than 90 degrees. Say here it is mercury. For mercury, theta more than 90 degrees means obtuse angle. Here For water, theta less than 90 degrees acute angle. So this angle of contact in fact depends on liquid only? No. Actually, the angle of contact depends upon three major parameters. So what are those three major parameters? As shown here, number one is liquid. I'll show here. So factors affecting theta. The first factor affecting the contact angle is the liquid itself. Number two, the solid with which the liquid is in contact. I'll give a simple example. Suppose water in contact with a glass jar or glass container, you will have some sort of angle of contact. Suppose pure water, clean glass, I can say that the angle of contact is almost zero. And let us take a different example. Water on a solid surface, say a glass plate, same water droplets on the petals of a lotus, then what happens? The angle of contact will be different. So angle of contact in fact depends upon not only liquid but also solid. So apart from this, the third most important point is impurities. I'll tell you one example. Suppose pure water, say glass is also pure glass, zero angle of contact. So we add sugar solution, then the angle of contact is definitely not zero, more than zero, less than 90 degrees. Fine. So these are three parameters. Now there is one term called wetting fluids. So what are these wetting fluids? You drop water in your hand, it will wet. Na? Why the water is wetting the hand? Because adhesion between my hand and water is more than cohesion of the water itself. So I think you can guess. Wetting fluids example is water. Water, for which theta less than 90 degrees. So wherever this meniscus angle or contact angle is less than 90 degrees, they generally tend to be wetting fluids like water. Suppose mercury. You place few drops of mercury in your hand. Whether mercury will wet your hand? No, definitely not. So non-wetting fluids. So mercury is a non-wetting fluid. You know, in case of mercury, theta more than 90 degrees. How much, sir? Don't worry, it depends upon 130 degrees, or roughly around 130, 140, etc. So mercury, non-wetting fluid. So for non-wetting fluid, the contact angle is more than 90 degrees. Okay. So my dear students, this concept of angle of contact you have to understand properly in the analysis of problems related to capillarity. I think you are happy. Let us see the meaning of capillary action. See this animation. Water is poured in a container and glass tubes of different diameters are dipped in this container. If you observe carefully, you see here diameter is least diameter the rise is more. I can say that H inversely proportional to dia D of the tube. Of course, I want to say that capillary rise is more if the diameter is less. So why this is happening? So it needs certain derivations. So I want to explain the capillarity in detail now again. Now let us see. You have two different fluids in two different containers. So this side you have water, and this side you have mercury. Assume now the glass tube is dipped in the both containers. Now you see here, the water is rising, okay? Water rise. And this side, mercury side, it has fallen. Mercury falls. So now the general definition of capillarity. The rise or fall of liquids in tubes of small dia is called capillarity. I think you might have studied in your 6th class or 7th class. So now let us go to further meaning of why it is rising, why it is falling, etc. So in case of water, I already told you, the adhesive forces are more than cohesive forces. I already told you. Adhesive force more than cohesive force. It means wetting fluids. So wetting fluids in fact rise. It is called capillary rise. Now here in the case of mercury, cohesion of mercury more than that of adhesion. We already discussed. Mercury is a non-wetting fluids. So the non-wetting fluids will have a fall off level. It is called capillary depression. Already I told you, capillary depression. So the rise or fall of liquids is called capillarity. So capillarity may be rise or may be fall. Right. Now this capillarity in fact has got one derivation. So how do you work out that value of H? Now let us see the derivations now. Factors affecting capillarity. So H is nothing but 4 sigma cos theta by gamma d, where gamma is equal to rho g. So what are the factors affecting? All the factors affecting surface tension will also affect the capillarity. Fine. So what are the factors affecting? Surface tension will influence as as temperature increases, surface tension decreases. And theta will also influence. It means the angle of contact will influence. Okay. So sigma will influence H. The angle of contact will also influence. This angle of contact further depends upon type of solid and liquid, and of course the impurities also. Fine. Then H is inversely proportional to D. Of course, small d or capital D, don't worry. It means as the diameter of the tube decreases, the capillarity increases. So H is inversely proportional to D, or H2 by H1 is equal to D1 by D2. Several questions I have seen in various state service commissions on this particular simple equation. Of course, at the same time, H is inversely proportional to mass density of the fluid and of course acceleration due to gravity. These are the factors affecting capillarity in a nutshell. One general routine question in various state service commission. Capillarity is due to, all of you know, it is due to both cohesion and adhesion. Now I want to create one conceptual question, very simple question. Read the following statements with respect to capillarity. As diameter increases, capillarity decreases. Yes, we have already seen H inversely proportional to diameter. Yes, statement 1 is correct. Statement 1 is correct. Immediately, option D wrong. Okay. Now, if impurities in water increase, capillarity increase. No, impurities will increase, capillarity decrease. Suppose soap solution. Soap solution will have less capillarity due to pure water. So second statement is wrong. Second statement is wrong. Second wrong. Second wrong. Now don't break your head. Option C. No sir, you analyze the rest of the two. Wetting fluids will have capillary depression. What is wetting fluid? Water is a wetting fluid. Water will have capillary rise, not capillary depression. What about non-wetting fluids? Mercury is a non-wetting fluid. Mercury non-wetting fluid will have capillary depression. So statement 3 is also wrong. What about 4? For obtuse contact angles, capillary depression. You know, mercury will have obtuse angle, contact angle, roughly around 130 degrees. We already discussed their capillary depression. Yes, this is correct. Suppose you water has acute angle. So for acute angles, capillary rise. So on the whole, option C, statement 1 and statement 4 are correct. Now let us see the derivation for capillary rise in case of water. I have already shown this diagram. You see, the water is rising. Now, the top curved surface, you see here, the top curved surface is something like hemisphere, na? Yes, it is assumed to be hemisphere, something like hemisphere. You have some arrows, upward arrows. So what are those upward arrows? They are nothing but the surface tension forces. Now, you see the angle of contact, theta, already discussed. Now I am going to discuss the derivation. We have one concept called equilibrium of forces. Equilibrium of forces. In any stable system, equilibrium of forces. Driving force is equal to resisting force. So what is the driving force here? The driving force is nothing but surface tension force. What is the resisting force? The weight of the volume of the water rising. Weight of volume of water. Fine. Now you see here. So H, the capillary rise, where I have shown in the diagram, from water surface to the meniscus, that circular surface, top one is called meniscus. So that meniscus, I say this as meniscus. So this surface tension will have two components. One is the horizontal components you will have, and also you will have the vertical components. The horizontal components acting opposite to each other, na? So they will balance each other naturally. But the vertical components, they get added to each other. So surface tension force means the vertical component of surface tension force. So what is this? Sigma. So this is nothing but sigma. Sigma cos theta. Simple maths. Sigma cos theta. Surface tension is a line force. So acting on the circumference of this meniscus. So sigma cos theta into pi d. So this is surface tension force. Now weight of volume of the water, that is actually lifted by this surface tension force. So it is nothing but pi d square by 4. I am assuming d as the diameter of the tube. Pi d square by 4, area of a circle, into height h into rho g. So volume into specific weight. Sir, I have a doubt. See, h is up to the bottom of the meniscus practically, but there will be some weight of water of that curved surface also, no? So here there is an assumption that the weight of the water in that meniscus part is neglected. Now if you simplify these two, pi will get cancelled, 1d also gets cancelled, implies h is equal to 4 sigma cos theta by rho g into d. You may also write like this: h is equal to 4 sigma cos theta by gamma d. So where gamma is nothing but specific weight of fluid, which we already know, which is nothing but rho g. Right. Now let us see the capillary depression in mercury. You see here, glass tube is dipped in mercury. The mercury level is falling. You see here, the surface tension forces, now they are downward. See the angle of contact theta more than 90 degrees. If you really derive this, na, capillary depression H is equal to 4 sigma cos theta by gamma d. But something is missing here. I think you can guess. Minus, because it is falling. So H is equal to minus 4 sigma cos theta by gamma d. I don't want to derive. You try yourself. You try yourself. You'll really enjoy this derivation. Okay? Do it yourself. Capillarity through parallel plates. I think this is one previous IS question. I don't remember, civil or mechanical. Say there are two parallel plates. Say the gap between the plates is t, small t. Okay, small t. See the length of each plate normal to the board is L. Say it has a capillary rise of H. Say the angle, the contact angle is theta. Say acute angle, this is the liquid. I want to know the value of H. Same logic. So this is surface tension sigma. So the other side also I think I need not explain. Sigma Fi is equal to 0. Balancing of forces. The balancing of forces gives upward force sigma cos theta 2 sigma cos theta 2 sigma cos theta into length L. Upward force is equal to downward force. What is downward force in this particular volume? The capillary rise volume. So downward force gamma is equal to or rho g into volume. What is volume? H T into L. Okay. So weight density into volume. So L will cancel. What I want? I want H. H is equal to 2 sigma cos theta by rho g t. So how to remember this? I give a technique. In case of a circular tube, 4 sigma cos theta by rho g gamma d or rho g t. Instead of 4 sigma, there 2 sigma. Here gamma rho g t. So 4 sigma 2 sigma. Their diameter in the denominator, here t is the gap between the parallel plates. Very important. Try to remember. Now we have two different practical cases. Nowadays latest exams they are asking this type of questions. This is capillarity through annular tube. So annular tube means D naught outer dia of tube, Di inner dia. Now what about capillarity? H is equal to, as usual, 4 sigma cos theta by rho g. Generally what we write? Rho g d we write, but here rho g bracket start, outer dia is more, d outer minus d inner. So similar to water, 4 sigma cos theta by rho g d, but instead of d, d outer minus d inner. Don't worry about derivation. Now come here. The tube is inserted in a container where two different fluids are there. Bottom fluid S1, top fluid S2, specific gravity S2. I am assuming S1 more than S2. Now in such a case, what happens? What is H? Same. H is equal to, as usual, remember logic, 4 sigma cos theta by rho g d. This is diameter of the tube, rho g d bracket start, bottom fluid S1, top fluid S2. That's all. Understand the logic and try to mug up. Don't worry about the derivations. Okay, particularly for prelims and gate exams. Now let us see the practical examples of capillarity. Number 1, rise of oil in a cotton wick. You know, in olden days oil lamps are used. So how this oil is rising to the top? Because of capillary. Number 2, most popular is rise of sap in trees. Means the water in the ground reaches to the top of the leaves, top leaves, through the trunk, stem etc. It is also because of capillarity. Now you take a third example. Blotting paper placed on an ink. Suppose ink is fallen on a table. You have to clean it. Keep the blotting paper. What happens? This blotting paper will have a number of pores and it will squeeze the ink. So next example is, in summer we use cotton shirts. Cotton shirts in summer. I think you can guess, cotton shirts also will have pores. So the sweat on the skin will be squeezed by the pores of these cotton shirts because of capillarity. So the fifth example, you take a cotton towel of certain length, keep one end of this cotton towel in a container of water and keep the other end outside. Now after some time you can observe that the water will rise in this cotton towel from one side to the other side. I don't want to show you the animation. You treat it as an assignment. You do this experiment, you'll really enjoy it. Okay? So water rising from one end of a towel to the other side. Now coming to the farmers. See, generally farmers will plough the soil before taking up the crops. So by ploughing, what happens? The pores will develop in the soil. Say you have two types of soils. One is clay soils with pore size smaller, sandy soils with the pore size more. So from this capillarity perspective, so what happens? The retention capacities of water in capillary soils is more, whereas sandy soils will drain out the water faster. So capillarity is useful in the agriculture also. Of course, I want to give some two funny examples. Sometimes some magicians will do. See, now and then during Ganesha festivals, you will be observing Lord Ganesha drinking milk. People will be saying something. So there, in fact, they are using the concept of capillarity. So Lord Ganesha will have a trunk. Okay. Assume this trunk, at the center of the trunk, a small hole is created by keeping some small wire, etc. And if you keep a bowl of milk there, what happens? So the milk will rise through the trunk by capillary action. Even there are some examples. The lips of a goddess drinking milk. So it's nothing but capillarity between two parallel plates. So if you can see similarly in your routine life also, you'll find number of examples for capillarity. You please try to list out some at least 4 or 5 examples from your side. Okay. So in a nutshell, finally what I would like to say of these examples, so capillarities is due to both cohesion and adhesion. So their influence, cohesion and adhesion, is playing a crucial role in all these parameters. A funny question asked in several interviews and in several state service commission exams. You see here, a glass tube, circular glass tube say, is inserted in a water trough. The water level is rising to the height h. Now assume this tube is cut slightly. Now what happens? Whether the water will be sucked up and it will flow continuously, or something else, something like spillover, etc. What happens? Come on, students, guess yourself. Come on. Okay. Now I will explain what happens. Because now the point of cut is less than the actual capillary rise. So the rising fluid will not find a glass tube continuously. Now what happens at this point of cut? The surface tension tends to become horizontal. So because it is becoming horizontal, it will have only horizontal components of surface tension, no vertical components. Since only horizontal components, and that too equal and opposite to each other, they balance each other, no vertical component, and hence no spilling over, no sucking over. So the water surface at the point of cut will remain as it is. I will summarize that in the printing form now. Now let us take the concept of vapor pressure. Before switching to the definition of vapor pressure and its practical applications, first I want to explain how this vapor pressure is measured. You see here, I am showing a beaker at the bottom, say containing water up to a certain level. Then at the top, I am showing a manometer, let us say U2 manometer like this. Now what I am going to do, you see here, the manometer is connected to this beaker. Okay? If you carefully examine the level of mercury in the manometer is same. In both the limbs, the level is same. Why, sir? You see, at this top point, atmospheric pressure. So, at the outside atmospheric pressure. Again, at the other end, it is also subjected to atmospheric pressure. Since the pressure is same at both ends, naturally, the mercury level is same in that U2. Now you see, suppose the temperature is increasing gradually. Now once the temperature is increasing, you see the molecules, the surface molecules of the water are getting evaporated. Sir, what is the reason for this evaporation? You know, the liquid molecules are generally in the dynamic state. So there will be certain molecules of liquid which will have higher energy level. So those molecules at a higher energy level will overcome the intermolecular cohesive forces and they try to escape. They escape and accumulate in the empty space or the open space above the liquid surface. You can see here how many molecules. Now, if you care here, there is a level difference in the mercury level. What is the reason? So the evaporated molecules, the exerted pressure. So naturally, the mercury level towards the water has gone down. It is due to the pressure exerted by the vapor. Okay, so there is some difference in level. That is because of the evaporation and the vapor pressure. Now you see here. So the molecules are further under dynamic state, and the molecules are getting accumulated in the open space above the surface of the liquid. Fine. Now you see here, I am showing certain level difference, that I have used the symbol small h, that is equal to PV by rho g. So what is this? I want to explain again. Suppose the molecules are evaporating. So what I say here, evaporation is a function of temperature. Higher the temperature, higher the evaporation or vaporization. Okay. So now once the molecules are vaporizing, so after certain stage, naturally these vapor molecules start condensation. So one side evaporation, the other side condensation. So this condensation I say is a function of density of vapor molecules. So now we have two different terms here. One is evaporation. What is that? The molecules at higher energy level try to escape from the surface. And when the molecules are getting accumulated, naturally they lose their stability and condensation start. It's something like water molecules getting condensed in clouds. So now at a certain stage, the vaporization is equal to condensation. Means an equilibrium stage is reached. Say balancing. So balancing of evaporation and condensation. When these two rates are equal, the pressure exerted by the vapor on its own surface is called, in fact, vapor pressure or saturation vapor pressure. I say here, evaporation rate is equal to condensation rate. So when this particular stage is reached, then the corresponding pressure is called vapor pressure. Right. Sir, suppose this evaporation rate is not equal to condensation rate before that, when there is no balance, then what type of pressure? In fact, it is not called vapor pressure. In fact, it is called partial pressure. Okay. So finally, what is vapor pressure? In fact, vapor pressure is the pressure exerted by its own molecules on the surface when there is an equilibrium. This evaporation rate is equal to condensation rate. Now, so mathematically, I have already shown the head, the pressure head, vapor pressure head. All of you know how to calculate vapor pressure head. So head H is equal to pressure, what pressure? Vapor pressure by rho g, or sometimes I use the symbol gamma. Okay, right. So this is the vapor pressure head. Now let us see factors affecting vapor pressure. The first factor is temperature. We generally say that if temperature increases, vapor pressure increases. Why, sir? If temperature increases, the molecular activity increases. Higher molecular activity and the energy level of liquid molecules will increase. So as molecular activity increases, evaporation increases, leading to higher vapor pressure. I want to explain with a tabulation you see here. See, this is a table for water at different temperatures. You see, 0 degrees centigrade, 0.611, 25, 3.17, and at 100 degrees centigrade, you see at the bottom, 100 degrees centigrade, it's 101.325 kilopascal. I think most of you know what is this 101.325 kilopascal. It's nothing but generally standard atmospheric pressure. So at 100 degrees centigrade means the boiling point of water, the vapor pressure is equal to the atmospheric pressure. Simple point. So at boiling point, vapor pressure is equal to atmospheric pressure. Here I would like to tell one difference between boiling and evaporation. Most of the students will have one doubt. What is that, sir? So suppose you have a container here. Let us assume. Say I kept a plate here. Let us assume. This is a lid. So in this you have, say, water. Okay. So evaporation is generally related to surface. It is related to surface. So evaporation or vaporization related to surface. Now coming to boiling. Suppose same thing you have. Assume you have a lid. Say here, I am heating it just for fun. I am very poor in drawing. Now what happens here? So the vapors or bubbles will start from bottom. So from this I would like to say that boiling is related to the volume of the fluid. It is a boiling is related to volume, whereas boiling is related to volume, whereas evaporation or vaporization is related to surface. So I would like to repeat one point. At boiling point, the vapor pressure is equal to atmospheric pressure. Now let us see the second factor affecting vapor pressure. What is that? Cohesion or cohesive forces of a particular liquid. Higher the cohesion, lower the vapor pressure. Lower the cohesion, higher the vapor pressure. I want to show you with this simple example. You see here, this tabular form, what it shows? Vapor or saturation vapor pressure of various liquids generally at 20 degrees centigrade. See, water at 20 degrees centigrade, it has vapor pressure of 2.4 kilopascal. Mercury, 0.17 into 10 to the minus 3 kilopascal, means even less than 1 Pascal. Coming to petrol, 70 kilopascal at 20 degrees centigrade. From this, I want to make one common man's statement. More volatile, highly volatile liquids will have higher vapor pressure. So, you know, petrol, etc. are highly volatile. Sir, how do you know, sir? You just have one drop of petrol in the corner of this room. Assume without my knowledge you keep a drop of petrol. Within no time I say, क्या भाई साहब, क्या petrol गिर गया क्या? Where is the petrol? How I am able to say? Because that petrol being volatile, it will evaporate faster. So, my dear student children, so volatile liquids will have higher vapor pressure. This is a generally common statement. Arrange the following liquids in the increasing order of vapor pressure. Increasing order of vapor pressure. For example, in this case, which is having least? Mercury, then water, then petrol. So petrol has got maximum vapor pressure because it is more volatile and it has less cohesion or less cohesive forces. I think understood. Now let us see one of the important application of vapor pressure, that is cavitation. Now I am showing a pipe. So assume from left to right, water is entering the pipe. You see here. So initially larger pipe size, lower velocity. Okay, large cross section, low velocity. Now assume the water is entering the throat. I say the small size is throat. You see here. So in the throat, area less area, more velocity. I think you may be knowing continuity equation. A1 V1 is equal to A2 V2. Higher area, low velocity. Less area, more velocity. Fine. So from the larger section to small section, the water is entering. Now what happens in between at the junction of larger section to smaller section? You see here. You see here. So actually at this junction, velocity will be more. At the corners of the junction, velocity will be more. So what, sir? If velocity more, kinetic energy more. Law of conservation of energy. So V more, the pressure will be less. So what, sir? Suppose this pressure at this junction, I say this as minimum pressure. If this minimum pressure is less than the vapor pressure of the liquid flowing, the pressure is less than the vapor pressure of the flowing liquid. Now what happens? You see here, bubbles will form in the form of a ring. Bubbles will form. In fact, the formation of bubbles is called cavitation. In fact, so formation of bubbles is called cavitation. So what is the reason for cavitation? minimum pressure less than vapor pressure. Most commonly appearing question in various competitive exams. Cavitation is due to A. Low pressure, B. Low vapor pressure, C. High pressure, D. Very high pressure. Lot of confusion is there. Na? The correct answer is cavitation is due to low pressure. Sir, what about low vapor pressure? No, wrong. See, let it be any pressure. Suppose vapor pressure is low. The pressure at that junction must be lower than this lower vapor pressure. So, the correct answer is cavitation is due to low pressure. There will be another option giving low vapor pressure. Please don't choose it. Cavitation is due to low pressure. So, the formation of these bubbles, you are able to see the ring of bubbles is called cavitation. Now, these bubbles will travel. You see, the bubbles are traveling. So, now what happens towards right side? Naturally, the velocity will be less here. So, here the velocity will be less. At this ring, velocity will be less. Velocity less, pressure more, pressure more. So, the bubbles have formed in the low pressure region, but at certain section the pressure is more. Now what happens? What happens? Because the pressure now is more all around the bubbles, they collapse. You see here, they collapse here. Here and here they collapse. Once they collapse, in fact, microjets will form. So these microjets will attack the nearby solid surfaces. When they attack the nearby solid surfaces, these solid surfaces get destroyed. Something like you take sand particles, take some sand, you throw it on this glass board. Number of times, what happens? After certain time, this glass board gets damaged. So, cavitation, formation of bubbles. When these bubbles travel to a high pressure region, all around high pressure region, these bubbles condense, collapse, microjets will develop, they hit the nearby solid surfaces, causing damage of these solid surfaces. So some professors call this damage, what is that? Damage is called pitting. So this damage is also called pitting. Now I want to show this particular process of microjets again using an animation. Now let us see the animation of the microjet. You see here, as I already mentioned, bubble is formed. When this bubble reaches a high pressure region, all around you have different pressures. But at some point on the surface, the pressure will be the maximum. So at this point of maximum pressure, the bubble starts condensing. You see here, you see here. So the bubble collapsed. The bubble collapsed. You see a ring. I call this as torus, T-A-U-R-U-S. A ring formed. You can see at the center a microjet striking the solid surface nearby. Now you see tamasha. So these microjets strike the solid surface. Sir, after all, one bubble, what it can do, my dear student children? In fact, the bubbles are millions and millions in number. It's not one bubble, millions and millions of bubbles. So these millions and millions of bubbles exert number of microjets striking the nearby solid surfaces. You know, in strength of medicine was studied, if a body is continuously struck at some point, after some time it gets damaged. So that damage is called pitting. In a nutshell, I want to explain the cavitation. Fluid is passing through a low pressure region, pressure lesser than vapor pressure of the flowing fluid. Bubbles will form. So formation of bubbles, what is it? It is called cavitation. Now when these bubbles are reaching a high pressure region, all around the bubbles you have high pressure region to low pressure region, the condensation, so the bubbles will collapse. So when these bubbles will collapse, I already told you microjets will be released, microjets will be developed, a lot of energy is released. With this energy hitting the nearby solid surfaces, they are likely to be damaged, and this damage sometimes some professors call it as pitting. So this is a nutshell. I want to show you two practical applications for cavitation with reference to hydraulic machines. Of course, I am drawing rough sketches, okay? Don't fret me. So this is a rough sketch of a centrifugal pump. So pump is used to this here lift water. You see here. So the water surface, the pipe is, this particular pipe is suction pipe, water is sucked inside. So as the water moves up, the pressure will decrease. Say here atmospheric pressure, here atmospheric pressure. As you move up, the pressure will increase. Here at the entry or eye of the impeller, at the entry or eye of the impeller, pressure will be minimum. My dear student, understand the word pressure will be minimum. Where? At the entry, also called eye of the impeller. The rotating part of the centrifugal pump is called impeller. When this pressure is less than the vapor pressure of the flowing fluid, what happens? Cavitation starts. So in the case of a centrifugal pump, cavitation occurs at the entry or eye of the impeller if not properly designed. Okay. Now the second practical application in hydraulic machines, in reaction turbines. So in reaction turbines, one statement, cavitation is likely to occur at the exit of turbine or entry of draft tube. So the end part of the reaction turbines is called draft tube at this location. I will just briefly explain. So water enters from the penstock or pipe to the turbine. So at the entries, pressures will be more. As water comes out of the turbine, reaches the exit, so pressure goes on decreasing. So the pressures will be lesser than vapor pressure. So there is a possibility that at the exit of turbines, minimum pressure lesser than vapor pressure of the flowing liquid. So naturally, the cavitation is likely to occur at the exit of turbine or entry of draft tube. Now I want to explain the chances of cavitation in the blades of hydraulic machines. I have a submission, my dear children. I am going very briefly. In detail, you will study in hydraulic machines. So I am giving the introduction of cavitation. Okay, don't curse me, right? So we have studied earlier that, I think in the case of surface tension, Suppose you have a droplet of water. The inside pressure will be atmospheric pressure plus some delta P. So outside pressure will be atmospheric pressure. Now it means there is some excess pressure inside the bubble. Na? We told you delta P, excess pressure. Excess pressure, excess with respect to atmospheric pressure. In a nutshell, P more, P less. Okay. Now coming to the blades. So if you come to the blades, you see here, just for fun, assume I am erasing this. Okay, I am erasing this. Okay, just for fun. So inside more pressure. Inside means concave side. Outside less pressure. Convex side less pressure. Just I am converting here. You see here, convex side of blade will have less pressure, P minimum. In case this pressure will be less than vapor pressure. What is the effect? Come on. Pressure less than vapor pressure, cavitation likely to occur. This is the reason. In the case of blades of hydraulic machines, the convex side, particularly hydraulic machine, hydraulic turbines, the convex side of blades are more susceptible for cavitation. Of course, you will read in detail in hydraulic machines. Now let us see another question related to temperature effect on viscosity. Sorry, I have already discussed it just now. Waste of time now. No, I want to test your understanding. Okay. Now see the question. With increase of temperature, viscosity of a fluid, not mentioned gas, not mentioned liquid, general viscosity of a fluid. Come on, you see the options. Option A, what is that? Doesn't change. Wrong. Always increases. See, it is question is related to fluid, liquid or gas are not specified. So always increases, wrong. Always decreases, wrong. Now see option D. Viscosity increases if the fluid is a gas and decreases if it is a liquid. We have already seen just now. So for this, correct answer is. Let us take one more question. Of course, assertion reasoning question. First one. Blood is a Newtonian fluid. Wrong. What is blood? Blood is a non-Newtonian fluid. Actually, blood is non-Newtonian. Among this, it is again pseudo plastic fluid. It is nothing but shear thinning fluid. If you draw the curve, actually this is pseudo plastic. Of course, there are some more examples like paper pulp, milk, etc. Okay. So assertion is wrong. Statement 1 is wrong. Naturally, statement 2 will be correct. What is the reasoning? The rate of strain varies non-linearly with shear stress for blood. True. So assertion statement A wrong. Second statement is correct. Whatever may be the answer, I think generally this type will be D or something else. Okay. Another previous IS numerical question. Honestly speaking, if I am in the exam hall in the prelims, to read and solve this type of questions, it takes a lot of time. Further, without calculator, difficult to work out. I am in the exam hall, I'll skip this type of questions. Anyway, let us try. The velocity distribution in a laminar flow adjacent to a solid wall is given by U is equal to 3 sine 5 pi y. The viscosity of the fluid is 5 pi mu. 5 pi is 0.5 Pascal second. So what is the shear stress at a section? Two parts are given. Y at a distance 0.05 meter from the boundary and 1.12 meter. Let us take the first one. Shear stress tau is equal to mu dot du by dy. Mu dot du, differentiation 3, differentiation of sine 5 pi y cos 5 pi cos 5 pi y dy. What is dy? First one is 0.05 meter. So mu, it is given as 0.5, 3 5 ja 15, 15 pi divided by 0.05 into cos. Now mu 0.5 du, differentiation 3 into 5, 15 pi cos 5 pi y du by dy. So this is equal to 0.5 into 15 pi cos, calculator not allowed, 5 pi 0.05, so you will get 0.5 15 pi cos 5 into 0.05, 0.25 pi by 4 cos pi by 4, 45 degrees. So 0.5 15 pi into 1 by root 2. So how do you work out? 15 5 ja 75, means 7.5 into pi, 22 by 7, roughly 22 by 7, 1 by root 2, 0.707. Okay. So now roughly say 22 by 7, 3, 22 by 7, 3. So 3 into 7.5, 3 7 ja 21, something 22.5. 22.5, again in that 70%. It will come around somewhere around 16 so and so, approximately 16 so and so. Now those options, 16 option A, option C, option D. Okay, 4 answers are there. Now you have to work out for y is equal to 0.12 meter. Now let us see that. Now let us see for y is equal to 0.12 meter. So these are the steps already done, because you might have done on a rough sketch, rough page. So you'll get 0.5 15 pi cos 5 pi into 0.12. Okay, Yeah, don't write all these things because these are prelims. Cos 5 into pi 180 degrees, let us take into 0.12, this is equal to cos 0.12 into 5, 0.12 into 5, 0.6, 0.6 into 180, 18 5 ja 90, 108 cos 108 degrees something, cos 108 degrees, second quadrant, all silver teacups. So in the second quadrant, cos will be a negative value. You will get a negative value. Shear stress negative value. No, shear stress is not taken negative value. If it is coming to be negative, you have to consider it as 0. So therefore, 16.7, first one, second is 0, which is the most nearest answer. Yes, answer D. D is the correct answer. Another conceptual question. This is the conceptual question. So the annular space between two coaxial vertical cylinders of equal length is filled with an incompressible liquid of constant viscosity. The outer cylinder is held fixed, outer is fixed, and the inner cylinder is rotating about its axis at a uniform rotational speed. Assume Newton's law of viscosity holds good. There are 4 options. What is the option? Newton's law of viscosity holds good. Newton's law of viscosity holds good means, what is the option A? The tangential velocity of the liquid varies linearly across the gap. Already discussed several times. So option is the correct answer. Just for fun, what is option B? Viscous shear stress in liquid is uniform across the gap. Wrong. Actually, shear stress is more near the fixed cylinder. See, fixed cylinder is resisting, na? So shear stress is not uniform across the gap. Shear stress is maximum near the fixed part. So second one is wrong. Yeah, automatically C and D are wrong. So option A is correct. Let us see another theoretical question. Pseudoplastic is a fluid for which A. Dynamic viscosity decreases as the rate of shear increases. Rate of shear increases. Let us see here. Pseudoplastic. Tau du by dy. Rate of shear means du by dy increasing. Earlier we discussed viscosity is not represented by the tangent at a point. Viscosity is represented, suppose this is a point. This is origin. Now we connect this point. This is mu1. Suppose you have another point. Join this. This is mu2. Similarly, mu3. So as the rate of shear strain is increasing, the slope of this is increasing, viscosity decreasing. So option A is correct. Plastic is a non-Newtonian fluid. Now dynamic viscosity increases as the rate of shear increases. Now let us see this. What is the meaning of this? Actually, this option C represents dilatant fluid. You see here. This is dilatant fluid. This is du by dy. If you carefully examine, as du by dy increasing, the slope is increasing. Na? It means rate of shear strain increasing, viscosity increasing. In fact, this is dilatant fluid. So C is not pseudoplastic. Okay, anyway, now option A is correct for pseudoplastic fluids. Now another, of course, is a gate mechanical previous question. An incompressible fluid with a kinematic viscosity, not dynamic viscosity. Kinematic viscosity nu is equal to 7.4 into 10 to the power of minus 7 meters square per second. Specific gravity 0.88. Specific gravity 88 is held between two parallel plates. The top plate is moved with a velocity of 0.5 meter per second. U 0.5 meter per second. While the bottom one is held stationary. Okay, bottom is stationary. The fluid attains a linear velocity profile. Linear velocity profile. What does it mean? Newton's law valid. Valid. The gap between the plates 0.5 mm. The shear stress in Pascal on the surface of bottom plate is, okay, Newton's law. Tau is equal to mu dot du by dy. I think earlier we have done one similar question. Only thing is, in this problem, kinematic viscosity given, not a dynamic viscosity. So I will work out kinematic viscosity and I'll give rest of the thing as assignment. Nu is equal to mu by rho. So implies mu is equal to nu into rho. Nu 7.4 into 10 to the power of minus 7 into mass density. Specific gravity is given as 0.88. So 0.88 into 1000, 880. Okay, into 880. So substitute this value of mu. Du means u, dy means y. You simplify, because calculator is allowed in GATE exam. You will get the answer B. That is solving. Tau is equal to 0.651 Newton per meter square, which is nothing but Pascal. You will get option B as the answer. Please do it yourself. Now let us see another previous gate, of course, mechanical question. See the diagram carefully. Of course, diagram is not properly drawn. A cubical block of side L, cubic block of side L, and mass M, capital M, is dragged over an oil film across table, means the below that cube there is an oil, assume, connects to a hanging block of mass small m, okay, as shown in figure. The Newtonian oil film of thickness h, see the diagram carefully, has a dynamic viscosity mu and the flow condition is assumed to be laminar. Laminar, okay. The acceleration due to gravity is z. The steady state velocity v of the block is. Okay. So there are four options. Option A, option B, option C, option D. See carefully. Now I want to analyze. Okay. Now you see. According to Newton's law of viscosity, here students will get a doubt. Sir, in the question it is mentioned, assume laminar flow. Na? I think we have studied in our second year, sir. In laminar flow, velocity distribution is parabolic, but Newton's law assumes linear velocity distribution. So there is a paradox, na, sir. You know, even in laminar flow, when the thicknesses are small, even in the laminar flow, when thicknesses are small, we can approximately assume linear velocity distributions. Don't worry. Okay, right. Now I am showing the free body diagrams here. You see the capital mass M. Okay. Now you see the right side, this free body diagram. the cable is subjected to tension T. Okay. So equal and opposite. So tension force in the string or cable. Okay. So now tension T, force is equal to so tension force is equal to, we know, shear stress into area. So what I have done, shear stress mu dV by dy into A. Okay na? So what is A? Surface area of the cube. Cube side L na? So A is equal to L square. Now this is nothing but, now tension T, it is nothing but small mg, because that hanging block has a mass small m. So tension T, so you can clearly see mg is equal to mu A, I will bring it here, L square, dV V, thickness of the oil h. Now what I want velocity V. If you simplify velocity V, cross multiply mgh by mu L square. So same steps I am repeating here. So what is the right answer? The right answer is option C. One previous GATE civil question. A liquid of density rho and dynamic viscosity mu flows steadily down an inclined plane in a thin sheet of constant thickness T. Neglecting air friction, the shear stress on the bottom surface due to the liquid flow is, where theta is the angle of the plane, makes with horizontal. Okay, I'll draw a rough sketch. So there is an oil flowing. Okay, you consider a small strip of oil. The thickness of the strip, is T. Okay, right. The slope is given theta. Already we discussed one similar question. So this weight of the oil of a small strip, how do you get weight? Gamma means rho g, specific weight, into volume. Volume means area, surface area, assuming A, and thickness T, WgAT. Now you have to resolve these forces along the inclined plane. If you resolve, this is W sin theta, but there will be shear resistance na, or shear resistance or shear force, tau dot A na. So upward force is equal to downward force along inclined plane. So what is upward force? Tau dot A. Downward force W sin theta, rho g AT sin theta. Both sides cancel A. So therefore the shear stress is equal to rho g T sin theta. So what is that? Option A. Option A. Option A is the right answer. Surface tension is in a soap bubble. Very important. Bubble. Soap bubble. A 50 mm dia. With its inside pressure being 2.5 Newton per meter square. Above the atmospheric pressure means excess atmospheric pressure. I want what is surface tension. You know, soap bubble will have two surfaces. Already discussed. So here P atmosphere plus delta P, outside pressure P atmosphere. So this delta P is equal to 8 sigma by D. Derivation is already done. 2.5 is equal to 8 sigma, I don't know, D, diameter 50 mm, convert into meter, 0.05 meter, implies sigma is equal to, if you simplify you will get 0.0156 Newton per meter. Now see this question, previous IS question. The dimension of surface tension is, already I have defined in earlier, it is the force per unit length. One is Newton per meter. Surface energy per unit area, surface energy Joule per meter square. Now see among the options, A wrong, B wrong, C correct answer. C is the correct answer. Now see one question of surface tension. A spherical water drop of 1 mm in dia splits up into air into 64 smaller drops. Suppose a bigger drop splits into number of smaller drops, say 64 numbers, just for fun. Okay. Equal size. The surface tension coefficient of water is 0.073 Newton per meter. The work required in splitting up the drop is, so bigger drop to number of small drops, 64 drops, how much work is required? You know, work is equal to force into distance. So force, I will say F into L. F by L into L square. So surface tension into surface area. So what is this surface area? You know, when the bigger drop is splitted into number of smaller drops, actually the surface area increases. So what is the surface area? This is the additional surface area. Additional surface area by splitting the bigger drop to number of smaller drops. So this is the way to calculate work. Now let us come back here. So surface tension. Okay, let us say, what is the surface area of the bigger one? Okay, original surface area is equal to, let us say this as capital R, pi R square 4 pi R square. Correct na? Original surface area. Now surface area of small droplet is equal to 4 pi small r square. I say each one of small r. Okay, right. So additional area, additional surface area is equal to 64 into 4 pi r square minus 4 pi r square. Now we have to find out the relation between capital R and small r. We'll work out now. Now I want to find out the relation between capital R and small r. When the bigger droplet is broken into number of smaller droplets, volume doesn't change. You know, volume of a sphere is equal to 4 by 3 pi r cube formula. So here I'll work out. Bigger droplet, 4 by 3 pi r cube is equal to 64 into 4 by 3 pi small r cube, 4 by 3 pi, 4 by 3 pi. Therefore, small r is equal to capital R cube by 64 whole power 1 by 3. This is equal to r by 4. Okay. Now, additional surface area is equal to 64 smaller droplets into 4 pi r square small r is equal to I 4 square minus 4 pi r square. So you will get 64 into 4 pi into r square by 16 minus 4 pi r square. 16 4 ja. So this is equal to 16 pi r square minus 4 pi r square. So 12 pi r square is the additional surface area. Now work done. Surface tension 0.073 Newton per meter. Additional surface area 12 pi r square. 12 pi capital R. But actually what is given? 1 mm diameter given. So I want to work out radius. So radius is equal to 0.5 mm. So 0.5 12 by 0.5. You have to convert into meters by 10 cube whole square. If you simplify, you will get, I think, approximately 0.69 to 10 to the power of minus 6 joules. Now I want to take one numerical question, a practical application. What is the maximum diameter of the steel pin of density 7600 kg per meter cube that can float freely on the surface of water? Surface tension 0.072 Newton per meter. Neglect effect of bias. We have earlier discussed that a water strider and in walk or move on water. Similarly, steel pin of small weight, little weight can float on water. You can do this experiment. You take a small pin, try to keep it gently on water surface, it will float. I tried, it's not possible. In such a case, what you do? Keep one paper, small newspaper floating on the water. On that paper is this needle gently. Paper may sink, but along with that, this pin also will sink. How it will sink? I have shown 3 different positions. When pin is placed initially. Now, assume it is sinking to a smaller depth. In such a case, this will be the resisting force. What is this resisting force? This is due to surface tension. Now, once the depth slightly increases, assume the resisting forces are vertical. No, sir, some angle is given in paper setter. In such a case, if angles are given, say some theta is given, you can resolve this into the vertical component. Okay. So this will be sigma L. This also will be sigma L. this also will be sigma L. What is L? Length of the steel pin. Now, the pin will have some self-weight W. Here I am assuming buoyancy is neglected, and at the same time the resisting forces are upward. I am assuming. We know mathematically sigma Fi is equal to 0. Sigma L, 2 sigma L. I am assuming theta 90 degrees minus downward force, self-weight of the pin is equal to 0. So, self-weight of the pin W is equal to rho G into volume of the pin. Volume of the pin is equal to pi d square by 4 into length of the pin L. Okay. Now, let us equate, substitute in this equation 2 sigma L minus rho G pi d square by 4 into L is equal to 0. 2 sigma L is equal to rho G pi d square by 4 into L. L will cancel. I want D na, so I will work out here. Therefore, D is equal to 4 to 8 sigma by pi rho G under root. If you substitute 8 sigma 0.072 by pi, density of the steel pin 7600 kg per meter cube, Z let us take 9.81. In the gate exam, paper setter sometimes may say assume so and so value Z. In such a case, you assume under root. So, if you simplify, how much value you will get? Approximately 1.6 mm is the answer. Now, let us see one previous IS question. The capillary rise at 20 degrees centigrade in a clean glass tube. So, what is the meaning of this? Already we discussed clean glass tube, contact angle theta is equal to 0 degrees. Okay. 1 mm diameter, T is equal to 1 millimeter. Containing water is approximately H is equal to 4 sigma cos theta by gamma d. 4 sigma not given. In prelims, you have to understand such numerical values. For water with air interface, sigma is equal to 0.073 Newton per meter. 0.073. Cos theta, cos 0, 1 divided by gamma not given of water 9810 Newton per meter cube into diameter of the tube 1 millimeter, 1 into 10 to the power minus 3. If you work out, approximately you will get 30 millimeter. Now, let us see another IS question. The angle of contact of a drop of a liquid is acute angle. Acute angle means like water. You know, water rises, na? So acute angle is rise. What is the meaning of rise? The adhesive force between the glass tube and water is more than the cohesive force of the liquid. So now let us see. Option A, cohesion is equal to adhesion. Wrong. Option B, Cohesion is more than adhesion. Wrong. Adhesion is more than cohesion. Yes, C is the correct answer. Now let us see this. Cavitation and pitting. Cavitation is a practical application of vapor pressure. They can be prevented by creating which one of the following conditions? Okay. We know cavitation is due to low pressure. Cavitation is due to low pressure. I want to avoid cavitation means low pressure shall not be developed. Okay. Option A, reducing the pressure head. Wrong. Pressure shall not be reduced. A, wrong. A, wrong. B, reducing the velocity head. Let us see this. Velocity, kinetic energy. If kinetic energy increases, pressure energy increases. High pressure, not low pressure. Yes. B is the right answer. Let us wait. Increasing the elevation head. You know, at higher altitudes, as you go to higher altitudes, pressure will decrease. Low pressure, no. Wrong. Reducing the piezometric head. Piezometric head reduce means pressure head reduce. Wrong. So therefore, cavitation and pitting can be avoided by avoiding low pressures, means reducing the velocity heads. So option B is the correct answer. Now let us see one miscellaneous question which covers entire chapter, concepts of entire chapter. Matching. List 1, list 2. Capillarity. Capillarity is due to, yes, surface tension. So A4. A4. Okay. Right. A4. How many options are there? A and C. So B and D are wrong. B wrong, D wrong. I am following elimination technique. Fine. Next. Vapor pressure causes cavitation. B1. B1. Now among A and C, B1. Wow, both are having same. So A4, B1. Next. Viscosity is the reason for shear forces. C3. C3. Yes. Option A. Option A. Anyway, let us see. Specific gravity relates to density of water. D2. So correct answer is A.
We are now starting the chapter of fluid statics. The chapter of fluid statics is around 20% of fluid mechanics syllabus. This chapter depends heavily on engineering mechanics. Over a period of time, when you start studying this chapter, you will feel that every problem comes down to almost an equilibrium problem which you study in mechanics. Let us see what are the topics, subtopics under fluid statics. The first thing we study in fluid statics is regarding the concept of pressure. Please remember, when it comes to mechanics, the most important parameter was force, but in fluid mechanics, the most important parameter happens to be pressure. When we deal with pressure, we will be seeing two laws corresponding to pressure. The first law is known as Pascal's law. First law is called as Pascal's law, very famous law. The second law is known as hydrostatic law. Hydrostatic hydrostatic law. Regarding Pascal's law, the name itself is suggesting that this law was given by Pascal, and hydrostatic law was given by Torricelli. Moving further, after having studied pressure, next thing we'll be studying is regarding pressure measurements. Pressure measurements. What do we study in pressure measurements? We'll be talking about different devices used for measuring pressure. The most important device under pressure measurement will be manometer. After having studied pressure measurement, we will talk about hydrostatic or hydrostatic forces. Let us broadly discuss what hydrostatic is. Whenever you submerge any plate or any surface, flat surface or curved surface, inside a fluid, due to the pressure intensities, there is going to be a net thrust developed, net force developed. That net force is studied in hydrostatics. The applications of hydrostatics especially are extremely important in the case of dams. After having studied hydrostatics, a very famous topic known as buoyancy is studied. Buoyancy basically is the upward thrust exerted by a fluid on a body whenever the body is displacing the fluid. Lastly, after buoyancy, we'll be studying a topic known as relative equilibrium. This topic has another name. It is also called as rigid body motion. Rigid body motion. These are the topics we are going to study in fluid statics. From examination point of view, the most important topics are going to be these three things. These three topics will be extremely important from examination point of view. Let us start with the concept of pressure. Regarding pressure, how do we define pressure? Imagine that you are having a surface. On top of the surface, you are applying some force. Due to that force, there is going to be an intensity of force per unit area developed. That intensity of force per unit area is known as pressure. So we can define pressure as intensity of applied force per unit area. Intensity of applied force per unit area is known as pressure. Now, a similar kind of definition you have studied for stress as well. So therefore, we have to now define some differences between pressure and stress. The primary difference is the type of force. If you see over here, I'm talking about applied force. Whereas in the case of stress, you don't talk about applied force, you talk about resisting force. What do I mean by this? Let us imagine that I'm having some surface. Please imagine my palm to be a surface. When I apply a particular force, this force per area is talking about pressure. Whereas when I apply a force, my palm is also resisting some force. The resisting force per area is known as stress. So the type of force is different in the case of pressure and stress. Secondly, in the case of pressure, we always have compressive nature. So pressure is always compressive in nature. This is a second difference. If you remember, in the case of stress, you can have compressive, you can have tensile, you can also have shearing stresses. So therefore you are having multiple types of stresses. Pressure is only compressive in nature. Lastly, if you recall, stresses were tensor quantities, whereas pressure happens to be a scalar quantity. So pressure is a scalar quantity. This is a basic definition of pressure. Apart from this definition of pressure, you have to know one more idea of visualizing pressure. Now this idea of visualizing pressure is more important for mechanical background people. The reason is it involves basics of thermodynamics. Let us get into that thing. Imagine you have a cylinder. Let us say this cylinder is a fixed cylinder. This cylinder is a fixed cylinder. Inside this cylinder you are having a compressible fluid. For example, let us say you have a gas. Now what I do is I take an airtight piston. Let us say this is an airtight piston. I apply certain force in order to compress this fluid inside over here. Let us further say that the cross section area over here is equal to capital A. Since I am pushing this piston, let us say the piston is moving forward by a very small distance dx. Now because of this small distance dx, the gas inside has got compressed, and doing so I have committed some work in order to compress this gas. If I want to find out how much work I have done to compress this gas, what I have to do is I have to write the equation dW is equal to F times dx, or F dot dx. dW is equal to F dot dx. So what do we call this dW as? I can say that this dW over here is compressive work. Compressive work. dW over here is compressive work. Now further, I can as well write this dW as F upon area times dx. All I'm doing in this equation is I'm dividing and multiplying with area. There's no harm in doing that. Now I want you to observe F upon area separately. If you look at this F over here is the applied force, and area is of course area over here. So intensity of applied force per unit area, this again has to give me pressure. Therefore the value of dW now comes out to be equal to pressure multiplied to. Now you see over here area times dx. What is area times dx? Please imagine that area times dx is the swept volume of this particular piston, or you can say it is equal to the volume compressed. Let us say compressed volume. From here I get the equation dW is equal to PdV. This is a very famous equation in thermodynamics. From here I can further say that the value of pressure therefore has to be equal to, all you have to do is get this V over here. So therefore dW by dV, this is the value of pressure. If it is so, then I can say that pressure over here is equal to the intensity of compressive work per unit compressed volume. So I can say intensity of compressive work per unit volume is known as pressure. These two definitions of pressure, I hope, are giving you sufficient idea regarding pressure. So whatever we have seen till here, in that what we have to highlight, the first thing is pressure is equal to force upon area, also equal to dW by dV. This is the primary thing. Secondary thing is you have to remember that pressure is compressive in nature and pressure is only a scalar quantity. After having seen the definition of pressure, now let's talk about the units of pressure. The most important unit we have to speak about is the SI unit. The SI unit of pressure is 1 Newton per meter square, commonly called as 1 Pascal. Very common name. But the practical problem with Pascal is the value of Pascal is extremely small. Please imagine 1 Newton amount of force functioning over 1 meter square plate. You can imagine 1 Newton as the weight of approximately 100 grams on Earth. Let us say 100 grams of something you are spreading evenly throughout 1 meter square plate. That is going to have very small intensity. Therefore, we mostly go for multiples of Pascal. Most commonly used multiple in our subject is 1 kPa, which is equal to 10 power 3 Pascal. You might also come across 1 MPa, which is equal to 10 power 6 Pascal. In some cases, you'll have to deal with 1 GPa, which is equal to 10 power 9 Pascal. It is better to remember that 1 MPa is also equal to 1 Newton per 1 mm square. 1 Newton per 1 mm square is 1 MPa. Apart from these units, there are some other units also used, one of which is 1 bar. The value of 1 bar is equal to 10 power 5 Pascal, or you can say it is equal to 100 kilopascals. Apart from 1 bar, we also have 1 atmosphere. The value of 1 atmosphere is approximately equal to 1 bar. Exact value is 1.013 bar. Therefore, I can say it is equal to 101.3 kilopascal. This unit of 1 atmosphere is very important. It is the amount of pressure exerted by atmosphere at the mean sea level on Earth. Moving further, there is one more way, a standard way of measuring pressure. That standard way of measuring pressure is known as pressure in terms of pressure in terms of head of a fluid. Pressure in terms of head of a fluid. This is a very, very important way of measuring pressure. How do we define this? I can define pressure in terms of head of a fluid as height of a fluid column, height of a fluid column required to create a particular amount of pressure, to create a particular amount of pressure. Height of a fluid column required to create a particular amount of pressure. How do we understand this and how do we calculate this thing? Let us see by taking a small example. Suppose you have a test tube. Let us say this is a test tube we have. In this test tube, you are filling in some fluid. Suppose you have filled in some fluid. Let us say that the fluid filled in is up to a height small h. Now, corresponding to this height small h, there is going to be a pressure created over here. Even though we have not studied hydrostatic law, but I hope some of you might be knowing that the value of pressure at the bottom, if the fluid is having a constant value of gamma, then the value of pressure at the bottom is equal to gamma times h, or you can say it is equal to rho gh. This is the value of pressure. It is only true provided the value of gamma or density of this fluid is a constant. Now, I want you to understand that in this formula of pressure is equal to rho gh, I am having two important parts. One part over here is a part of density. This density over here is talking about the property of fluid. Property of fluid. It is representing the property of fluid. The second part of this formula, it is h over here. This h over here is talking about depth or height of fluid column. Height of fluid column. Now, if I give you the value of density and the value of h of a particular fluid column, indirectly I have given you the value of pressure. This idea is bringing to the next topic, or this topic, which is pressure in terms of head of a fluid. What we do over here is, instead of defining pressure in any of these units, we will rather say that I am having a particular fluid with a particular amount of height. Correspondingly, what pressure I am having is indirectly known to me. For example, if I know that I am having 760 mm of mercury, 760 mm of mercury, then this value is equal to 1 atmosphere. 760 mm of mercury is equal to 1 atmosphere. Now please observe, what is the 760 mm over here representing? This over here is giving you the value of h from here. And when I say Hg, that is mercury, then this over here is helping you get the value of density. Once I have defined density and I have defined the value of h, indirectly I have defined the value of pressure, because pressure in this is rho gh, and this value is equal to 1 atmosphere. This method of measuring pressure is known as pressure in terms of head of fluid. It is known as pressure in terms of head of fluid. Now, I hope you can relate this thing with the statement written over here. It is the height of a fluid column required to create a particular amount of pressure. After having seen this, let us go one step ahead. What we have done is, since 7 mm of mercury is equal to 1 atmosphere, we standardize 1 mm of mercury as well. 1 mm of mercury. The value of 1 mm of mercury is approximately equal to 133.33 Pascal. If I'm having a fluid column of mercury having a height of 1 mm, it is exerting a pressure equal to 133.33 Pascal. This value you have to memorize, and you are going to call this as 1 torr. It is called as 1 torr. 1 torr is named in honor of Torricelli. Pascal, of course, is in the honor of Pascal. Torr is in the honor of Torricelli. One more thing I would suggest you to remember is, for creating 1 atmospheric pressure, if I want the height of water column, then I require height of 10.3 meters of water column. So if I have 10.3 meters of water column, it is going to be equal to 1 atmosphere. 10.3 meters of water column is equal to 760 mm of mercury column is equal to 1 atmosphere. So the gist of all these things is, if you want to find out head, if you want to find out head, all you have to do is take the pressure, divide by gamma. If the value of head is given to you, then the value of pressure is equal to gamma times h. That's it. If you want head, take the pressure, divide by gamma. If you want pressure, take the head multiplied by gamma. Now let us look at some standard pressures. What we are going to study now is extremely important for measuring pressure. Without this small topic, it is impossible to study any further in fluid statics. So please concentrate in this. There are three standard pressures I am going to mention. The first pressure, very basic pressure, it is called as absolute vacuum or absolute zero. What do I mean by absolute zero or absolute vacuum? This is the least amount of reference pressure we take. How to imagine this thing? Let us say right now you are in a room in which there is some amount of pressure which is exerted by atmosphere. But suppose you keep on reducing this pressure. As you keep reducing the pressure, the molecular activity keeps on reducing. Suppose I reduce it to the point that the molecular activity completely stops, then that pressure is called as absolute zero. So I can define it as the pressure at which the molecular activity in matter in matter completely stops. The molecular activity in matter completely stops. That pressure is known as absolute zero, also called as absolute vacuum. This is very simple. Now we are going to discuss about two pressures which are having similar name but lot of difference. One is known as standard atmospheric pressure, the other is known as local atmospheric pressure. Before I write the definition, let me first explain. Please understand that atmosphere also is a fluid, and this fluid is enveloping the earth throughout. Therefore, atmosphere on top of earth is exerting pressure. The pressure exerted by atmosphere on earth is known as atmospheric pressure. But the problem with earth is not having a uniform altitude throughout. Everywhere its altitude keeps on differing. This is a rough image I am drawing. Let us say this is the altitude of earth, a small portion of earth's surface. Now you see, everywhere it is not having the same level. It keeps on varying. Suppose I have atmosphere starting from here. Let us say atmospheric level is starting from somewhere over here. Now if you see, the depth of atmosphere everywhere keeps on changing. If I take some location over here as location A, this as some location B, I'm not having the same level of atmosphere at A and at B. Since the depth of atmosphere in these two locations is different, therefore the pressure at A and pressure at B also should be different. Now since atmosphere is creating different pressures throughout, what we do is we take a mean level. Let us call this as mean sea level on earth. Whatever pressure is exerted by atmosphere at the mean sea level on earth, it is called as standard atmospheric pressure. This brings us to the second type of pressure called as standard atmospheric pressure, standard atmospheric pressure. Its value is equal to 1 atmosphere. How do we define this standard atmospheric pressure? It is the pressure exerted by atmosphere at the mean sea level on Earth. The mean sea level on Earth. The pressure exerted by atmosphere at the mean sea level on Earth is known as standard atmospheric pressure. The value of standard atmospheric pressure, please remember, it is equal to 1 atmosphere. I can also say it is equal to 760 torr. I hope you all remember, torr is 1 mm of mercury's pressure. Now coming to the third one. Third one, very important pressure called as local atmospheric pressure. Local atmospheric pressure. Now how do we define this local atmospheric pressure? Now you see, the pressure exerted by atmosphere at the mean sea level was called as standard atmospheric. But at any particular location, the pressure might be different from standard atmospheric. That particular location's actual atmospheric pressure is called as local atmospheric pressure. This, I can say, is the pressure exerted by atmosphere, at a particular location is that location's local atmospheric pressure. For example, let us say you are located right now at some place which is above mean sea level. If you are located at some place above mean sea level, of course the depth of atmosphere at your location is lesser. If it is lesser, that means this location over here will have local atmospheric pressure less than 1 atmosphere. Or let us say you are located somewhere over here which is below mean sea level. If you are located below mean sea level, then the atmospheric depth at your location is greater than this depth. Therefore, you can guess what is going to happen to the local atmospheric pressure over here. Will it be equal to standard atmospheric pressure, or less, or more? It has to be greater than standard atmospheric pressure. If you are located exactly at mean sea level, then at this location the value of local atmospheric pressure, it will be equal to 1 atmosphere. So therefore I can say now that local atmospheric pressure, it can be less than, equal to, or greater than standard atmospheric pressure. Now let us say I locate two positions on Earth's surface, X and Y. You are traveling from position X till position Y, and while you are traveling, you are observing the pressure, atmospheric pressure. Please tell me, what do you expect the standard atmospheric pressure to be when you are traveling from this location till this location? When you are traveling from here to here, standard atmospheric pressure will still remain equal to 1 atmosphere. Please remember, standard atmospheric pressure is independent of your location. It only depends on mean sea level. Whether you are at mean sea level or you are not at mean sea level, every location is supposed to have same standard atmospheric pressure. It is equal to 1 atmosphere. But what would happen if you are traveling from here till here to local atmospheric pressure? Now you see, local atmospheric pressure is a function of fluid's depth or atmosphere's depth at that location. So everywhere you move over here, the value of local atmospheric pressure will keep on changing. It keeps on changing. Therefore, let me go one step ahead and tell you something which is important for the next slide. Therefore, local atmospheric pressure is a non-universal reference. It is a non-universal reference because it keeps on changing. Whereas standard atmospheric pressure as well as absolute zero, both of them are universal references. Why universal references? Because their values are independent of where you are located. Everywhere their values will remain same. Let us now talk about scales of pressure measurement. Scales of pressure measurement. Now, to measure anything, the first thing required is to create a reference. Imagine I give you a line, ask you to measure it. You'll take a scale. First thing you do is you'll adjust your zero. That zero is what I call as reference. Similarly, for measuring pressure, we require some reference. For this purpose, what we have done, we have chosen two references. The first reference, I like to call it as universal reference. That's not the actual name, but that is my preference. I call it as universal reference. Let us say this is a universal reference. It is actually absolute zero. Absolute zero is the first reference we have. The second reference is a non-universal reference. That is, let us say, local atmospheric pressure. These are two references. If we have two references, then we can measure something in two scales also. Let us say I have a container which is having a fluid that is pressurized. The pressure in that container is this much. This is a level of pressure. Let us say this is P1. I want to measure this pressure. So now I have to adjust my reference. I can choose absolute zero as reference. I can also choose local atmospheric pressure as reference. Let us say I choose absolute zero as reference. Then what I measure is going to have this much of value. This pressure is known as absolute pressure. So I can say now that the pressure measured with respect to absolute zero as reference is known as absolute pressure. I can also measure the same pressure taking local atmospheric pressure as reference. So let us say I measure this. This pressure is known as gauge pressure. So now two scales of pressure measurement we have. One is absolute scale, the other is gauge scale. Gauge pressure is measured taking local atmosphere as reference. Absolute is measured taking absolute zero as reference. What is the relationship between these two? To understand this relationship, I have to extend a line over here. Let us say this is P naught. P naught is the value of local atmosphere taking absolute zero as reference. Taking these three things, now I can say that the value of P absolute is equal to P naught plus P gauge So the value of P absolute is equal to P naught plus P gauge. Let us move further. Suppose that container I was having, I open it up. When I open the container, what happens is it is completely exposed to atmosphere. When it is exposed to atmosphere, the pressure from P1 falls down to local atmospheric pressure. When it has fallen down to local atmospheric pressure, then the value of gauge pressure becomes equal to zero and the value of absolute pressure becomes equal to P naught. From here I can say anything that is exposed to atmosphere, imagine a river's or a pond's interface exposed to atmosphere, the gauge pressure has to be equal to 0 and the value of absolute pressure has to be equal to P naught. Please remember this thing. Anything exposed to atmosphere should have 0 gauge pressure. Let us say in that container create a suction such that the pressure in the container falls down below local atmosphere. So suppose I am having some pressure at this level. Let us say this is some P2 pressure, lower than the local atmospheric pressure. Now, if I measure the absolute pressure, having the absolute pressure like this. If I measure the gauge pressure, please look at the direction sense now. The gauge pressure is downward now. What does it mean? It means that the gauge pressure right now is negative. Negative gauge pressure basically means that the pressure is lesser than the local atmospheric pressure. If I want to create a relationship between these two, then what I have to do is I have to now write P absolute in this case is equal to P naught minus P gauge. Therefore, my formula is now going to become P absolute is equal to P naught plus or minus P gauge. This is the formula for P absolute and P gauge relationship. When do we use plus? We use plus whenever we are having a positive gauge pressure or pressure above local atmospheric. When do we use minus? We use minus whenever we have negative gauge pressure or pressure below local atmospheric. After having mentioned these things, let us now write down some definitions. The first definition is for absolute pressure. Absolute pressure. Regarding absolute pressure, first thing you have to remember is it is measured with respect to absolute zero as reference. Measured with respect to absolute zero as reference. One more thing, please remember, it is always non-negative. It is always a non-negative quantity. Okay, you see that even in this case the value of absolute pressure is positive. The least value of absolute pressure, it is supposed to be equal to 0. That is when you are having absolute 0, you'll have absolute pressure itself equal to 0. Coming to the second type of pressure or second scale, it is called as gauge scale. Gauge scale or gauge pressure. It is measured with respect to local atmospheric pressure as reference. Next thing, tell me, is it supposed to be only positive? We have seen that it can be 0 also. Anything exposed to atmosphere is 0 gauge pressure. We have seen it is negative also. So I can say it can be positive or negative or 0. It can hold a positive value, a negative value. It can also be equal to 0. One more point, please remember this thing. Negative gauge pressure is called as suction pressure or vacuum pressure. Suction or vacuum pressure. negative gauge pressure is called as suction pressure or vacuum pressure. Now, to understand this perfectly, let me ask you a question now. I hope you remember I had taken some random diagram stating that this is the surface of Earth. Altitude everywhere is changing. Suppose this location is some location X, this location is some location Y. Suppose you are carrying some container filled with the fluid, closed container. You are moving from location X to location Y. Okay, the pressure, actual pressure inside the container is not changing, but you are moving from X to Y. Please tell me that when you move from here to here, what is going to happen to the value of absolute pressure and what is going to happen to the value of gauge pressure? The value of absolute pressure in the container would remain same. Why so? The reason is the actual pressure is not changing, also the reference is not changing. So both these levels are remaining same when you are moving from X to Y. But what would happen to the gauge pressure value? Please imagine, gauge pressure value. Would it remain same or it would change? I hope you are getting that it should change. The reason is, even though the actual pressure is not changing, the reference everywhere is keeping on changing. Let's say this is fixed, but this is keeping on fluctuating. This local atmospheric pressure is keeping on fluctuating. Therefore, the value of gauge pressure would keep on fluctuating. That is why I call this as a universal reference and this as a non-universal reference. After having seen the topic of pressure, let us move forward to the concept of Pascal's law. Pascal's law is the primary most law in the topic of fluid statics. This law helps you understand how the pressure is going to act when a fluid is at rest. Let us do a small mathematical experiment to understand this Pascal's law. Suppose you have a container. In this container, let us say you are having a fluid at rest. Now what I do is, I choose a point in a fluid at rest. Let us say this is a point. Now we know that a point is dimensionless, but for the sake of understanding what I do, I choose a point as having some kind of shape like this, a triangular wedge. Please imagine a unit width perpendicular to your screen. Now let us say the vertical height over here is equal to dz, the horizontal length over here is equal to dx, and the inclined length over here is equal to ds. So this is how the triangular wedge is shaped, and perpendicular to it is 1 unit. Now we know that pressure is compressive in nature. Since pressure is compressive in nature, on each of these faces the intensity of pressure is attacking to compress this wedge. Let us say over here I am having Px. Over here I am having an intensity of pressure that is equal to Pz, and over here I am having an intensity of pressure that is equal to Ps. It is equal to Ps. Now I want to write the equation. Apart from this, I am having one more force, that is dW. I know that the acceleration in x-axis is equal to 0. What does it imply? It implies that the net force acting in x-axis on this wedge element has to be equal to 0. Let us see what are the forces acting in x-axis. I can say that Px multiplied to the area that is acting over is dz into 1 unit. So Px times dz minus Ps multiplied to ds. Now I have to take the component in x-axis. So let us say if this angle over here is theta, then I should multiply over here with sine theta. This has to be equal to 0. What does it imply? It implies that Px times dz has to be equal to Ps times ds sine theta. Now please observe, what is this ds sine theta equal to? Ds sine theta has to be again equal to dz. Therefore I can say that the value of Px times dz has to be equal to Ps times dz. I can cancel dz on either side. From here I get that the value of Px has to be equal to Ps. Let us move forward. I am now talking about z-axis. I know that the value of Az also is equal to 0. If the value of Az is equal to 0, this implies summation of force in z-axis has to be equal to 0. If summation of force in z-axis is equal to 0, from here I can write that Pz times. Now please observe, the area over here is dx into 1 unit. So therefore dx. This is acting in the downward direction, therefore minus Ps times ds into cos theta, and weight also is acting in the downward direction, therefore minus dw has to be equal to 0. Now if you observe over here, since I am reducing this entire thing to a particle size or a point size, the weight is supposed to become negligible. Let us say the weight is 0. Furthermore, I can say that ds into cos theta is again equal to dx. Therefore, pz times dx has to be equal to ps times dx. I can cancel dx on either side. If I cancel dx on either side, this implies that the value of pz is equal to ps. Pz is equal to ps. Now let me hold this as some equation number 1 and this over here as some equation number 2. From equation 1 and equation 2, what can we conclude? We can conclude that the value of px is equal to pz is equal to ps. This is a very important relationship. What does it actually mean? What is the physical meaning of this thing? Now that we have done all these things, we have to understand the physical meaning of this. You see, the wedge I have taken is depending on theta, but the result over here is not at all depending on theta. It is not a function of theta. That means whatever the value of theta I would have taken, the result would still be holding good. This implies that at a particular point, when a fluid is at rest, the intensity of pressure in any direction is going to remain same. This over here is known as Pascal's law. So I can state Pascal's law as when a fluid is at rest, the pressure at a point in all the directions would remain same. That's a very basic way of understanding Pascal's law. There are more ways of understanding Pascal's law which we'll be seeing further. Now when we describe Pascal's law, we have used the word rest. But technically Pascal's law is not valid only when the fluid is at rest. For validity of Pascal's law, rest even though is one of the criterias, but the actual criteria is the absence of shear stress. Shear stress should be equal to 0. And this shear stress equal to 0 condition is referred to by constrained fluid. Constrained fluid. It is referred to by constrained fluid. So now instead of saying that when the fluid is at rest, I can rather say when the fluid is constrained. So let me write a statement for Pascal's law and then I'll explain you. The statement goes something like this. When a constrained fluid is pressurized, then every point in the fluid experiences a rise in pressure by same magnitude in all the directions. Now this statement is a very good statement for expressing Pascal's law. Let us understand this by taking a virtual experiment. Imagine you have a container. The shape of container is something like this. Let us say in this container you are having a fluid filled in over here. suppose exposed to atmosphere. If it is exposed to atmosphere, I hope you will be able to answer what would the gauge pressure on top be equal to. The gauge pressure should be equal to 0. We have discussed this thing, that anything exposed to atmosphere should have 0 gauge pressure. Now let us say over here I choose a particular point. Let us say point is point 1. At point 1 the pressure I am having, let us say, is P1. Why have I chosen this direction for P1? Because I know that pressure is supposed to be compressive in nature. Therefore, for compressing at this particular point on the wall of a container, I have to take this direction. Let us say I choose another point over here. Let us say this point is point 2. The pressure at this point has to be in this direction. Let us say P2. Suppose I have chosen some point over here. Let us say the point is point 3. The pressure at this particular point has to be in this direction. Let us say P3 is the pressure over here. Now, the statement says that a constrained fluid, let us first concentrate on this phrase, constrained fluid. Please check whether the fluid over here is constrained or not. For checking whether the fluid is constrained, all you have to see is whether shear stress is or is not equal to 0. I see that the shear stress throughout is equal to 0, so I have satisfied this condition of constrained fluid. When a constrained fluid is pressurized, let us do one thing. On top I was having 0 gauge pressure, but now let us pressurize over here. By some mechanism, let us say I apply some pressure P prime over here. So when a constrained fluid is pressurized, then every point in the fluid experiences a rise in pressure by same magnitude. What does it mean? Since I am increasing a pressure on this entire constrained fluid, now I have to add pressure P prime at every particular point. At every particular point. Point 1 also experiences a rise in pressure by P prime. Point 2 also is experiencing a rise in pressure by P prime. Every point likewise is supposed to have an increase in pressure by same magnitude. In which direction? Can I say that since I'm applying over here downward, the rise also should be downward? That is wrong. That rise has to take place in all the directions. Since P1 is acting in this direction, the value of P prime also added will be in this direction. Likewise for P2, likewise for P3. So every point in this fluid rises its pressure by same magnitude in every direction. This is what Pascal's law states at. Now we have to see the validity of Pascal's law. Validity of Pascal's law. Validity of Pascal's law. When can I say that Pascal's law is valid? I have already mentioned the criteria is when the value of shear stress is equal to 0. This is the actual criteria. But if you want to see in detail when is it valid, first thing I can say is it is always valid, if fluid is ideal. That means you are having an ideal fluid. Whether the fluid is at rest or in motion, Pascal's law has to be valid. Why do I say so? The moment you look at the word ideal fluid, what should appear in your mind? The value of shear stress is equal to 0. We know that if shear stress is equal to 0, automatically in every case, the value of viscosity has to be 0. If viscosity is 0, automatically shear stress has to be equal to 0. Therefore, if you are having an ideal fluid, whether the fluid is at rest or in, Pascal's law has to be valid. But now let us come to real terms. We work with ideal fluid. Every engineering application is going to have a real fluid. So when do we use Pascal's law if the fluid is real? Let us say I am having a case of real fluid. I'll give you certain conditions in real fluid. Please tell me whether Pascal's law is valid over here or not. Let us say condition number 1, when the real fluid is at rest. At rest, velocity we know has to be 0. If velocity is 0, I'm continuing over here, if velocity is equal to 0 everywhere, it implies du by dy also is equal to 0. If du by dy is also equal to 0, it implies shear stress has to be 0. Therefore, at rest, Pascal's law is valid. Pascal's law is valid. Let us take the second case. I'm not straight away going to motion now. I'm going to a particular type of motion. That particular type of motion is known as rigid body motion. Rigid body motion. Rigid body motion. This topic of rigid body motion I have also mentioned previously. It is also called as relative equilibrium. Rigid body motion basically means you take a container of a fluid, you move it in such a way that the particles of the fluid are relatively at rest. They are relatively at rest. They might be absolutely moving, but with respect to each other, they are at rest. For example, I take a bottle of water, I keep accelerating the bottle of water in a particular direction. That is rigid body motion. In that case, again the value of velocity is 0, the value of du by dy is equal to 0, and the value of shear stress is 0. So therefore, even in rigid body motion, Pascal's law has to be valid. Lastly, if I take a case of a real flow, when a real flow takes place, shear stress is not equal to 0. In that case, Pascal's law is invalid. So therefore, I can say Pascal's law is valid always for ideal fluid. In the case of real fluid, it is valid under two conditions. Either the fluid should be at rest or the fluid should be experiencing rigid body motion. This is regarding the basics of Pascal's law. Any machine that functions on the principle of Pascal's law is known as Pascal's machine. Pascal's machine. So how do we define a Pascal's machine? Any machine that functions on the principle of Pascal's law. Any machine that functions on the principle of Pascal's law is known as Pascal's machine. Let us take a simple example of Pascal's machine, and probably the most important example of Pascal's machine. It is known as hydraulic lift. The setup of hydraulic lift is something like this. Imagine you have a container. In this container, let us say there is a fluid filled in. After filling in a fluid, I am putting two stands on either side. Two stands on either side. The cross-section area of the container on the left-hand side is small a, and the cross-section area over here is capital A. It is evident that the value of small a I have taken is less than capital A. Let us say on top of this I am having a load. The load is capital W. My aim over here is to lift the load capital W upward. To lift the load capital W upward, I can do one thing. I can tie a rope over here, lift it upward with a tension greater than or equal to W. But let us say I don't have sufficient energy or strength to lift this load W. For this purpose, what I do, I apply certain amount of force over here. Let us say the value of force is F. Now, I am choosing 2 points over here. Let us say point 1 and point 2. I know that the pressures at point 1 and point 2, both of them have to be same by the virtue of Pascal's law. So if I say P1 is equal to P2, it implies from here that the value of capital F upon small a is equal to capital W upon capital A, which further can be mentioned as F is equal to W multiplied to small a upon capital A. Now please observe, since small a is lesser than capital A, the ratio small a upon capital A is less than 1. What does this imply? This further implies that the value of F, the force required to lift upward, is less than the actual load I am lifting. So whatever is the load I am lifting up, I have to use lesser amount of force to lift it up. This is giving me something known as mechanical advantage. Mechanical advantage. How do we define this mechanical advantage? Mechanical advantage is defined as load lifted by force applied. Load lifted by force applied. In this particular case, if you see the value of mechanical advantage over here, it is equal to load lifted is W, force applied is F, therefore W upon F. This is the value of mechanical advantage in this case. This entire setup, since it is based on Pascal's law, happens to be a Pascal's machine. It is called as hydraulic lift. Hydraulic lift. Now moving further, I want you to create an analogy in your mind from strength of materials, or rather mechanics, on this concept of hydraulic lift. Let us say you have a lever, and you are putting a support over here. The support is not placed exactly at the center of the lever. You are placing it eccentrically such that this distance over here is small a, and this distance over here is capital A. You have a load over here. The load is equal to W. You want to lift the load, so you are applying a force over here. Force is F. If I want to identify that how much is the value of force I have to apply, for that purpose I would have to again establish equilibrium about this point. So I can say F multiplied to capital A, F multiplied to capital A has to be equal to W multiplied to small a. From there again I am getting the value of F as W multiplied to small a upon capital A. So again I am requiring a lesser amount of force to lift a heavier weight. Similar kind of situation is over here. Again the value of mechanical advantage in this case happens to be equal to capital W upon capital F. After having seen this, let us take up a very simple problem which has appeared in IS examination. It was regarding pressure at a point in a fluid at rest. In a fluid at rest. So imagine you are having some container, a container in which there is a fluid at rest. You have chosen a particular point. You want to observe how the pressure at this point is acting. For this purpose, let us say I magnify the point. But you should know a point is dimensionless. How much ever I magnify it, it is again going to be a point only. Therefore, what I do, I am showing this point in the form of a cube, but mind you, the dimensions of the cube everywhere are 0. Let us say this is a cube. Now, if the dimensions everywhere are 0, this implies that the pressure acting on every face is going to have uniform intensity in all the directions. So first thing I can mention over here is uniform intensity in all directions. Uniform intensity in all directions. Second thing, please observe, is the pressure tensile or compressive in nature? Purely compressive. So therefore, second point I can say is pressure is compressive in nature. Pressure is compressive in nature. Lastly, third point. Third point. If you see, all these things are working in the form of a normal stress. I don't have any shear stress. So therefore, I can say 0 shear stress. 0 shear stress. Now, what question appeared from here in IES is, they asked you to draw Morse circle for pressure at a point in a fluid at rest. I hope all of you remember the concept of Morse circle. It is a circle which represents how the pressure is acting at any inclined plane in a particular member. So let us say I am drawing the Morse circle. The horizontal axis in Morse circle represents normal stress. The vertical axis represents shear stress. Please imagine that this is over here representing sigma y, and this again over here is representing sigma y. This is representing sigma x, this again is representing sigma x. Now, if you see, sigma x is compressive and it is having an intensity P. Therefore, what I have to do is I have to go in the negative horizontal axis at a distance P and locate sigma x. Coming to sigma y. Sigma y again is compressive and it is also again having the same intensity P. So sigma y also, if I locate, it is again going to be the same point. Now, if there is any shear stress, I'll have to produce a vertical over here, perpendicular over here. But I see that the shear stress everywhere is 0. So therefore, I don't even have to produce a vertical. This itself is a center for the circle and there is no radius for the circle. Therefore, this itself is representing Morse circle. Morse circle. So please remember, the Morse circle in the case of pressure at a point in a fluid at rest has to be a point. Now, what would happen if I keep choosing the point, or if I keep taking a point deeper and deeper compared to the present point? Let us say I choose a point somewhere over here. What change will be developed in the Morse circle? Will the radius of the Morse circle change? Will the shape of the Morse circle change? No. The Morse circle again is going to be a point circle. Only thing is, since you have gone deeper, intensity of pressure increases. Only thing that will happen is this Morse circle will go even further from the center, but it will again maintain its point shape. What would happen if I choose a point somewhere up over here? It would maintain the shape. Only thing is, the Morse circle would come closer to the center. So remember, Morse circle for pressure at a point in a fluid at rest has to be a point circle, that too in the negative normal stress axis. No shear stress whatsoever. The next law we are discussing is hydrostatic law. What is the aim of hydrostatic? What is the purpose? The purpose of hydrostatic law is to identify the rate of change in pressure with respect to the vertical axis. Rate of change in pressure with respect to the vertical axis. What does it mean? Suppose I choose a container. In this container, let us say I'm having a fluid. The property of fluid is gamma. The fluid is exposed to atmosphere. If it is exposed to atmosphere, the gauge pressure has to be equal to 0. I know that in the horizontal axis, throughout the pressure is remaining same by the virtue of Pascal's law. But what is happening in the vertical axis that we are seeing in hydrostatic law? For that purpose, what I do, I define vertical axis. Let us say at this level, I am taking the value of h as 0, and as I keep going down, let us say the value of h is increasing. So h is measured positively in the downward direction. Let us say at the lowest point, the value of z is equal to 0. Z is 0, and as I keep going up, I choose z to be positive. So vertical axis in my case is measured in two ways. One way is downward positive, one way is upward positive. You can call downward direction as depth direction, and vertical direction you can call as altitude, or a better word to use, more technical word to use would be datum. So Z over here refers to datum axis. Datum is a word which will come more frequently once we start the topic of Bernoulli equation. Now, what I'm going to do is, in this fluid, let me choose a prismatic fluid element. Let us say I have chosen a prismatic fluid element. I hope all of you know what prismatic is. It is having a constant cross section throughout its axis. This prismatic fluid element I have chosen is, let us say, at some depth h. It is having a height dh. It is having a cross section area dA. So what have I defined for this prismatic element? I have defined its position. I have defined its cross section area. I have defined its own depth. So cross section area dA, own depth is equal to dh. Now, please observe, this prismatic element is neither accelerating in x-axis nor in vertical axis. It is right now in equilibrium. If it is in equilibrium, I can write the equations of equilibrium to establish it. So let us say I am writing summation of force in vertical has to be equal to 0 since it is in equilibrium. What are the forces acting? Let us draw a small free body diagram. Let us say this is the element I have. The forces it is experiencing, the first force over here is its own weight, let us say dW. On the upper face, it is going to have a pressure force since it is compressive downward. On the lower face, again it is going to have a pressure force upward. This pressure force, let us say, is P times dA. P times dA. Now I want you to think logically. Take your time if you want. You can pause the video. But please think what will happen to the pressure over here. Should it be equal to P, more than P, or less than P? Think logically. You would find out that the pressure over here has to be greater than P. Why so? First thing, I'm not talking about a point. If I was speaking about a point, then the pressure here and the pressure here both would be same by Pascal's law. I'm talking about a fluid member, fluid element. This element is having some depth. Since it is having some depth, this pressure force has to balance of P times dA as well as dW. That means this pressure has to be greater than this so as to counter dW as well. Therefore, I am writing over here P plus dP whole times dA. This is the value of pressure force I have. Now, if I write the equation of equilibrium, I am having P plus dP whole times dA has to be equal to dW plus P times dA. I can cancel off P times dA and P times dA on either side. After having cancelled, I get from here that the value of dP times dA has to be equal to dW. Now, you have this dW weight part over here. Remember, throughout our subject, whenever you come across weight, think of weight as gamma times volume. Gamma times volume. So if you see volume of this prismatic element is dA times dH, therefore I can rewrite this equation as dP times dA has to be equal to gamma times dA times dH. I can cancel dA on either side. What am I left with now? From here I'm left with dP upon dH is equal to gamma. This simple equation over here is your hydrostatic law. Even though this equation might be looking very simple, but it's a highly potential equation, very important equation. dP by dH is gamma. What exactly it is telling you? From mathematics, you know that d by d actually is representing a rate of change. So I can say this is saying rate of change in pressure. Rate of change in pressure. This is representing the rate of change in pressure. But with respect to which axis? Is it horizontal axis? No. It is with respect to vertical axis. So therefore rate of change in pressure with respect to vertical axis. Vertical axis. The rate of change in pressure with respect to vertical axis in the absence of acceleration has to be equal to the specific weight of the fluid. This is called as your hydrostatic law. What does it physically mean? It physically means that if the density of a fluid is higher, then the pressure will quickly change with respect to vertical. If the density of fluid is lesser, then the pressure is going to change gradually. For example, if I give you two containers, one having mercury, other having, let us say, water. Both the containers are having equal height column of mercury and water. In which case are you going to develop more pressure at the bottom? Of course, it is going to be in the case of mercury. The reason being, mercury is going to have higher density, therefore the pressure in the case of mercury will increase faster as compared to that in water. That is what Pascal's law states. Let us not stop at this. Let us do justice with z-axis as well. I have got over here dP by dH is equal to gamma. I want you to think, what is dP by dz going to give you? What is dP by dz going to give you? See, when I said H is increasing down and I got a positive value over here, that basically means pressure also is increasing in the downward direction. So one thing you have got from here is pressure increases as you go down. That is good. But come to this equation. Z is increasing in the upward direction, pressure is increasing in the downward direction. That means their direction of increase is opposite. I should not get a positive now, I should be getting a negative. Therefore minus, but the magnitude still remains gamma. So dP by dZ has to be equal to minus gamma. This equation and this equation, both of them are simultaneously the same. Both of them together I can call as hydrostatic law. Now after having got these equations, let us see where it is applicable. Is it applicable in the case of compressible fluid or in the case of incompressible fluid? Most of you might be thinking it should be applicable in the case of incompressible fluid. That is wrong. It is always applicable. Whether the fluid is incompressible or compressible, you can always apply. So therefore, please remember this. It's a very important point. From here, we have seen many questions coming, not directly, indirectly, that hydrostatic law, hydrostatic law is applicable for both compressible and incompressible fluid. So whether the fluid is compressible or incompressible, hydrostatic law has to be applicable. Before we go any further, let me first remind you what is the meaning of the fluid being compressible. A fluid being compressible means the density is not a constant. It should be varying. Please remember, whenever you see a case of compressible fluid, if density is a variable, please take density in some way a function of dH, in the function of h, so that you can go for variable separable method. We'll be seeing it further. What is the meaning of incompressible fluid? This should not be difficult for you. In the case of incompressible fluid, the value of density or gamma has to be constant. The fluid throughout, with respect to vertical, is going to have same density. Let us now apply hydrostatic law in incompressible fluid case. So let me say a bit incompressible fluid. If a fluid is incompressible, then the gamma value of the fluid has to be constant. So let us say I have chosen a container. In this container, let us say I'm having a fluid. On top over here, it is exposed to atmosphere. Suppose this point is some point A where the value of h is equal to 0. This is some point B. The value of h over here is the complete h height of this container. I wish to now find out how the pressure is varying. Let us say the property of the fluid is gamma. I can start with hydrostatic law, which says dP upon dH is equal to gamma, which implies dP is equal to gamma times dH. Let us integrate on both the sides. Since gamma is constant, I'm leaving gamma aside. I know that at h is equal to 0, the value of pressure has to be equal to 0. Remember, by default, when we say pressure, we mean gauge pressure. So therefore, by default over here, I mean gauge pressure is equal to 0. At any random height h, let us say the pressure is P. Now, if I integrate this, I'm going to get P is equal to gamma times h, or I can say it is equal to rho GH. So pressure is equal to gamma h or rho gh. This is how the pressure is varying. But this is for gauge pressure. If I wish to find out the value of absolute pressure, please recall the formula for absolute pressure, it was equal to P naught plus P gauge. Therefore, this has to be equal to P naught plus gamma h or equal to P naught plus rho gh. P naught plus rho gh. This is how the pressure is going to vary in the case of incompressible fluid. This formula of pressure being equal to gamma h or rho gh is a very famous formula. But please be careful, you are supposed to apply this formula only in the case of incompressible fluid or when the fluid is having constant density. Now, what does this equation physically mean for us? What is its physical significance? The physical significance is the linear proportionality of pressure with respect to depth. So it basically says that with respect to depth, the pressure is linearly varying. That variation is given by a diagram, very important diagram called as pressure distribution diagram. So let us say I am choosing over here a point A and over here another point, let us say B. I wish to find out how the pressure is varying from A till B. To find out how the pressure is varying from A to B, I will apply this particular formula. At A, the value of H is equal to 0. So if H is equal to 0, pressure is also equal to 0. At B, the value of H is equal to capital H. Therefore, pressure is equal to gamma into G into capital H. So now, linearly, the pressure is supposed to keep on increasing. The pressure increases linearly over here. The pressure at B is equal to gamma times capital H. If I take any random point over here, such that from here to here I am having a height small h, then I should be getting over here gamma times small h. This diagram over here is known as pressure distribution diagram in gauge scale. What if I wish to draw a similar type of diagram in absolute scale? Let us say again I am choosing a point over here capital A. Over here a point I am choosing is capital B. Now in absolute scale, the pressure at point A is supposed to be equal to P naught. It is supposed to be equal to P naught. Therefore, I am extending over here forward by a pressure equal to P naught. At point B, the pressure has to be equal to P naught plus gamma times H. Therefore, something like this. This is how the pressure is varying. So over here, the pressure was equal to P naught. Over here, it is equal to P naught plus gamma times capital H. If I choose any random point over here at a distance of small h, then the pressure has to be equal to P naught plus gamma times small h. What I want you to observe over here is if I take over here a depth equal to 1 unit, again over here depth equal to 1 unit, this over here is representing change in pressure. So what I have done, I hope you have seen this thing. I'm doing a small manipulation over here. If I take the value of depth equal to 1 unit, what should be the value of dp then? You would observe that the value of dp has to become equal to gamma. That means this is equal to gamma. Similarly, this over here is equal to gamma. Please imagine I'm taking a fluid over here which is having a greater value of gamma. If the value of gamma increases, please think what would happen if the value of gamma increases. Only thing that should happen is this particular line, instead of going down like this, it should be going down in a way that the value of gamma increases, so the pressure would increase very rapidly. If I take a fluid having lesser value of gamma, what would happen to this line? Instead of maintaining this slope, it would go down in such a way that the value of gamma would decrease and the pressure would increase gradually. Are you following? So this is known as your pressure distribution diagram. Both these diagrams, both these diagrams are known as pressure distribution diagram. Pressure distribution diagram. After having seen incompressible fluid case, let us now move forward to a more interesting case. Let us say I am taking the case of compressible fluid. Compressible fluid. In the case of compressible fluid, the value of gamma is not going to be a constant. It is going to be a variable. Let us take a simpler case in compressible fluid. Suppose I have a container. I have a container in which there is a fluid present over here. Let us say this is h-axis. Over here it is exposed to atmosphere. Therefore, the value of gauge pressure over here is equal to 0. Suppose that the density as a function of h is mentioned equal to density naught plus alpha h, where alpha is greater than 1, sorry 0. Alpha is greater than 0. What is this equation telling you? This equation over here is telling you that as you keep going down, density itself is linearly increasing. Okay, it is increasing because alpha I have mentioned is positive, so there is a linear increase in density as you keep going down. I now want you to draw, pressure distribution diagram in gauge scale. In gauge. For drawing the pressure distribution diagram, again I have to start with hydrostatic law. I told you, same hydrostatic law is going to be valid for both incompressible as well as compressible fluid. So let us say I write over here dP upon dH is equal to gamma or equal to rho g. dP by dH is equal to rho g. I can imply from here dP is equal to E into density. I can write as density naught plus RH. I have taken dH over here. What I do is I integrate on both the sides. When H is equal to 0, H is equal to 0 is this topmost. It is given to you exposed to atmosphere. Therefore, the value of pressure is equal to 0. At any random value of H, any random value, let us say, the pressure happens to be P. Now, from here I can write the pressure P is equal to G multiplied to rho naught into dH integral will give you rho naught times H plus alpha H dH integral is going to give you alpha H square by 2. This further implies that at any height H or depth H, pressure is equal to rho naught GH plus alpha GH square by 2. So this is how the pressure is varying for the given equation. Now please tell me, is it a linear variation as we have seen over here? No, it is not a linear variation. It is a parabolic variation. So this should tell you something, that in the case of compressible fluid, you are never going to have a linear variation. For linear variation, the fluid has to be incompressible in nature. So now if I wish to draw, let us say, I have chosen over here, this point is point A, this is B, let us say, again A, again B over here. How is the pressure varying? The pressure is supposed to vary parabolically, something like this. Pressure is varying parabolically over here. How much is the pressure over here? It is equal to rho naught G capital H plus alpha G capital H square by 2. Now please observe, in this parabolic variation, I can break down and make a linear part and another part parabolic. Let us say something like this. Something like this. If you observe, there is a linear part to this parabolic and rest of it is a parabolic part. Come on, please answer me. What is this linear part equal to? If you see, the linear part is this rho naught GH. This is rho naught GH. And what is the parabolic part? This over here is a parabolic part, which is equal to alpha GH square by 2. I hope all of you are following this thing. Now some of you might be having a doubt that when I said parabolic, why did I draw it this way? Some of you might be thinking I should have drawn something like this. This also would be parabolic. This also would be parabolic. Why have I not drawn like this? Let us answer this question. This is correct. Now let us see why this is wrong. Now you see, if I draw a tangent and I see that the slope is supposed to be equal to 1 by gamma, is it not? If you look over here, the slope at any point is equal to 1 by gamma. Let me draw a tangent over here. A tangent over here. If I draw a tangent, this is 1, this is gamma. Let me draw a tangent over here again. This is 1, this is gamma. Now what is it telling you? It is telling you that over here I'm having a higher value of gamma, over here I'm having a lower value of gamma. That means as you go down, the value of gamma or the value of density is decreasing in this case. Whereas the equation given to you says that the value of gamma is supposed to increase as you go down. Therefore, this has to be wrong. The curve is supposed to be in that manner only. Under compressible fluid case, we are now going to see variation of pressure in atmosphere. Variation of pressure in atmosphere. Before we start this, let me tell you, this topic is not important for civil engineering. It is important for mechanical engineering alone. And this is going to have a small part of thermodynamics also important, very simple part of thermodynamics. Let us move ahead. We know that atmosphere can be assumed as ideal gas. So suppose we are assuming atmosphere as ideal gas. For that purpose, what we are going to do now is we are going to establish ideal gas equation. Ideal gas equation says PV is equal to mRT. PV is mRT, which further implies that the value of P is equal to m by V into RT. We know that m by V is density, which further implies density is equal to P by RT. This is the equation of density we have. Now in this equation, P stands for pressure. P is pressure. P is pressure. R over here is gas constant. Gas constant. And the value of this gas constant for atmosphere, it is equal to 287 joules per kg Kelvin. And T over here is temperature in absolute scale. Absolute scale. By absolute scale we mean the temperature is measured in Kelvin. Now taking these things into picture, we are now going to look at variation of pressure in atmosphere. I'm going to take three cases. The first case happens to be the simplest case rather. That is a case when I am having an isothermal condition. Let us say A bit over here, isothermal conditions. Isothermal conditions. Under isothermal conditions, the temperature is going to be constant. Temperature is constant. I want to find out with respect to vertical axis how the pressure in atmosphere is varying provided temperature is constant. Now I can say by hydrostatic law that dP upon dz is equal to minus rho g, or I can say that dP is equal to minus of. Now the value of density I am borrowing from here, that is P by RT times G times dz. What I can further do is I can take P over here. I can take P over here by variable separable method. Therefore, dP upon P has to be equal to minus G upon RT times dz. This is the equation I'm having. Now let us integrate on both the sides. I am putting an integral over here. G, R and T, all of them are constant. Mind you, temperature is constant over here due to this condition. So integral will be coming over here. Let us take some boundary conditions. Suppose at Z is equal to Z0, the value of pressure is equal to P0. I want to find out at any random value of Z how much is the pressure equal to. So from here I can say that integral dP by P is equal to ln P ranging from P0 to P has to be equal to minus G upon RT times Z minus Z0. From here I can say that the value of ln of P upon P0 is equal to G by RT multiplied to Z0 minus Z. If I put antilog, I am supposed to get P upon P0 is equal to e power G by RT times Z0 minus Z, which ultimately implies that the value of pressure at any elevation Z under isothermal conditions for atmosphere is equal to P0 times e power G by RT times Z0 minus Z. This is how the pressure is varying in the case of atmosphere for isothermal conditions. If you observe again, since the fluid is compressible, I am not having a linear variation. This time the kind of variation I am having is an exponential variation. Let us take B bit now. Second is in atmosphere. When temperature, let us say, is given as a function of Z. Suppose as you go up or down in atmosphere, temperature is varying, and that variation is a function of Z axis. How is this variation going to be acting? Let us see. The standard variation closer to Earth is given as T is equal to T naught minus alpha Z. This is the equation. T naught over here, T naught is the temperature on Earth's surface, temperature on Earth's surface, again in Kelvin. Remember, everything over here is in Kelvin when it is referring to temperature. Alpha over here is known as lapse rate. It is known as lapse rate. Lapse rate basically means the rate at which the temperature decreases. Now you see why decreases? Because minus sign over here. The rate at which the temperature is decreasing with respect to the vertical axis. What is the standard range of lapse rate? On Earth, the standard range of lapse rate is 6 Kelvin per kilometer to 9 Kelvin per kilometer. So every kilometer you are going to have a change around 6 to 9 Kelvin. If nothing is mentioned to you in question, you can take a value 6.5 Kelvin per kilometer. This is a more standard value for alpha. What does it basically mean? It means that every kilometer you go up on Earth, the temperature in atmosphere is decreasing by 6.5 Kelvin. That is why higher altitudes are going to be cooler. Now let us apply a hydrostatic law over here. I can say dP upon dz is equal to minus rho g or equal to minus P by RT times G. Let us now apply variable separable method. So I have over here dP upon P is equal to minus G upon R multiplied to dz upon. I am left with temperature now. Instead of writing T, I'll choose this equation, T naught minus alpha Z. Now let us integrate on both the sides. Suppose I put integral over here, integral over here. I know that when I'm on Earth's surface, the value of Z is equal to 0. Let us say the pressure is equal to P naught on Earth's surface. At any random elevation Z, let us say the pressure is equal to P. What do I get from here? From here I get that ln of P upon P naught has to be equal to minus G upon R into this integral is ln of T naught minus alpha Z ranging from Z is equal to 0 till Z is equal to Z. Further I have to divide by minus alpha. If I divide by minus alpha, I'm going to get this. So now it is ln of P upon P naught equal to G upon R alpha multiplied to ln of. Now you see this thing T naught minus alpha Z, and Z is having a range. If I put this thing, I'm going to get T naught minus alpha Z whole divided by T naught. This is the equation. If you put antilog on both sides, you are going to get P upon P naught is equal to. Now this I can simplify as 1 minus alpha Z upon T naught whole power G upon R alpha. Furthermore, I can write P now, pressure is equal to P naught multiplied to 1 minus alpha Z upon T naught whole power G upon R alpha. This is how the pressure would vary if the temperature is varying with respect to Z, and that too the temperature's variation, remember, should be a linear variation. Should be a linear variation. Now let us talk about pressure measurement. Pressure measurement is a very commonly asked question in examination, whether it is GATE examination or IES examination or any other competitive examination. The most basic device for measuring pressure happens to be piezometer. Piezometer. In piezometer, look at this word piezo. The word piezo over here stands for pressing effect. So piezometer basically is telling you that pressure is being measured by the virtue of pressing effect of the fluid created. For example, let us say you have a pipe through which a fluid is running. Suppose a fluid is running. This, let us say, is a cross section of a pipe. In the topic of pressure measurement, this is known as pressure bulb. It is known as pressure bulb. Now let us say in this pressure bulb, at a certain point A, I have to find out the value of pressure. So what I have to do is, just above this point A, I am going to install a thin transparent glass tube. Let us say I install a transparent glass tube. This thin transparent glass tube is exposing the fluid to atmosphere. When the fluid is exposed to atmosphere, the fluid is now going to rise up in order to maintain this pressure. Let us say the fluid rises up till here. It rises up till here. Now we know that at this particular point, since the fluid is exposed to atmosphere, the gauge pressure has to be equal to 0. Now let us say the height of the fluid column is h over here. This height is h over here. Now, due to this height h, I can say the pressure created at this particular point A has to be equal to PA has to be equal to gamma of this fluid multiplied to h, gamma times h, or you could also say rho gh, rho gh. Now this is true only if we are having an incompressible fluid. We have discussed already what happens in the case of compressible fluid. Now this is a very basic device, piezometer. Since it is basic, it is also going to have its own limitations. I would want you to guess what the limitations in piezometer could be. Let us start now. Tell me, can I use piezometer for measuring pressure when I'm having a gas inside this pressure bulb? Just imagine that if I'm having a gas, if I expose to atmosphere, the gas would escape completely. If it escapes completely, I can't have any interface created. Therefore, the first limitation we have with piezometer is it is not applicable in the case of gases. So I can write not suitable for gases, not suitable for measuring gas pressures. This is the first limitation we have. What would be the second limitation now? Now imagine I'm having extremely high amount of pressure. Let us say some megapascals pressure. If I'm having megapascals pressure, I would want a very high value of H over here. But then a piezometer will have its own limitation. It can't have a very high amount of height. So therefore, I can't measure extremely high pressures. So second limitation we have with the piezometer is, again it is not suitable for measuring high pressures. High pressure. This is the second limitation we have. Coming to the final limitation now. Now tell me, if I'm having vacuum pressures, I hope you all recall what vacuum pressure is. Vacuum pressure is negative gauge pressure. If I want to measure vacuum pressure, then I need to have a depression created. That is not possible over here. So therefore, third limitation is a piezometer is not suitable for measuring vacuum or suction pressures. These three limitations are present in the case of piezometer. For this purpose, what we do is, from piezometer we graduate to the next device, a very commonly used device, very famous device called as manometer. Manometer. How do we define a manometer? A manometer is again going to be a thin transparent glass tube, just like a piezometer, but only difference is, in a manometer you are going to have an additional fluid called as manometric fluid. So I can say a thin transparent glass tube, thin transparent glass tube, transparent glass tube filled, not completely, filled with an additional fluid known as manometric fluid. Manometric fluid filled with manometric fluid. Now let us see an example of a manometer. Imagine you have a pressure bulb inside which you are having some fluid present. The fluid present inside a pressure bulb is known as working fluid, and this working fluid is represented by gamma W. The property is gamma W. Please understand, W over here does not stand for water, it stands for working. Now I want to measure the pressure inside this pressure bulb, let us say at a certain point A. At a certain point A, I wish to find out the pressure. For this purpose, what I do is I install over here a manometer. Let us say a simple YouTube manometer. A simple YouTube manometer. Now, in this YouTube manometer, I'm already having a fluid called as manometric fluid. There is already a fluid present called as manometric fluid. Now, initially, when I connect this manometer, before connecting this manometer, the manometric fluid on either side of this manometer is going to have same elevation. Why would it have same elevation? Because from this side and from this side, atmosphere is exerting pressure. Since the pressure on either side is same, the elevation of the fluid also is going to remain same. But then the moment I connect this, let us say I connect this pressure bulb to the manometer. Let us say the pressure created by the pressure bulb is greater. So what happens is manometric fluid is going to experience a depression on this side. It is going to experience an elevation on this side. Let us say the manometric fluid is assuming this position. This is how the manometric fluid is assuming the position, and the working fluid takes this space. So let us say the property over here is gamma manometric. This is gamma manometric. Now what I do is I measure some heights. Let us say this height I am measuring as HM, and this height I am measuring as HW. I now wish to find out the value of pressure at point A. To measure the value of pressure at point A, what I do is I take this horizontal level. I take this horizontal level. At this horizontal level, on either side, the pressures are supposed to be same by the virtue of Pascal's law. You see, the condition for the pressures to be same is, first of all, you should have a horizontal level, and from one end to the other end, the fluid should be continuous. There should not be any discontinuity. Continuous fluid should be present. So let us say this is some point X, and this over here is some point Y. So now I can say that the value of pressure at point X is equal to the pressure at point Y. Now please tell me, what would the pressure at point X be equal to? At point X, the pressure should be equal to PA, and then you're coming down. Remember, whenever you come down, you are adding the pressure. Pressure increases. So PA, since I'm coming down, I'm adding plus. I'm coming down with a property of gamma W. You see, throughout I'm having working fluid over here. So gamma W. I'm coming down with a height of HW multiplied to HW. This is the value of pressure at point X. Coming to point Y. Over here I know that the pressure is atmospheric, therefore gauge pressure is 0. As I come down, I can write gamma manometric multiplied to HM. So this is gamma manometric multiplied to HM. Both of them are supposed to be equal. Now, if I wish to find out only the value of PA, then PA ultimately comes out to be how much? It is equal to gamma M times HM minus gamma W times HW. This is the pressure at point A in this setup. Please do not memorize any of these things. These are not standard formulas. These are the values of pressure for the given setup. Now I want you to observe one thing from here. Please see. After having got the value of PA, tell me which of these limitations I had in piezometer has been overcome. Tell me, if I was having a gas over here, would there be any problem? Let us say I was having a gas. Over here, I'm having a liquid. I'm having a liquid over here. Now, what would happen? A gas and liquid can create an interface. So there is no problem of interface over here. Again, a liquid and atmosphere can create an interface. So again, there is no problem with the interface over here. So this setup is still valid in the case of gases. So therefore, this limitation has been overcome. Moving further, I can measure slightly higher amount of pressures over here. Just imagine I choose a manometric fluid which is very heavy. The best example could be of mercury. If I choose mercury, mercury has very high density, therefore I can measure relatively higher values of pressure compared to piezometer. So to some extent you can say even this limitation has been overcome. To some extent. What about this limitation? In this setup, can I find out vacuum pressures? It is possible. Let us take an example for that case. Imagine again a pressure bulb. Let us say a pressure bulb over here, inside which you are having a working fluid. You are having a working fluid. I connect a manometer. I connect a manometer. Let us say the manometric fluid is assuming some position like this. The moment I connect a manometer, the manometric fluid is assuming this position. Before we start solving, please tell me what is the physical meaning of this thing. It basically says that the pressure exerted by atmosphere is greater than the pressure exerted by the working fluid over here. That means the pressure inside the bulb has to be lesser than the atmospheric pressure. Therefore, the pressure inside the bulb is vacuum pressure or suction pressure. So in this setup, I have overcome this limitation also. Let us calculate now the pressure at some point over here, point A. Let us say this is some point A over here. Suppose I take this distance as HM and I take this distance as HW for example. Again the properties over here are, this is gamma working, this is gamma manometric. Now I can say that at this point and at this point the pressures have to be same because the fluid from here to here is continuous. So let us say this is my point X and this is certain point Y. So I am saying pressure at X has to be equal to pressure at Y. What is the pressure at Y? Exposed to atmosphere. It has come multiple times. Whenever we expose anything to atmosphere, the gauge pressure is 0, is it not? So therefore I can say right hand side is 0 over here. What about the left hand side? Let me start from here. Please answer me. I'm starting from point A, PA over here. I'm coming down. Tell me, am I supposed to add or subtract? When we come down, it is increasing. Therefore, plus. I'm coming down with the property gamma W. So therefore, gamma W multiplied to. I'm coming down by a height HW. So therefore, HW. I have reached till here. Further, again I'm coming down. Again I'm supposed to add. I'm coming down with a property gamma M. So gamma m multiplied to. I'm coming down to the height of hm, therefore hm over here has to be equal to. What is the pressure at point Y? 0. This implies that the pressure at point A has to be equal to minus gamma W into HW minus gamma M into HM. This is the value of pressure at point A for this given setup. Now you see over here minus and minus. Therefore, the pressure has to be a negative gauge pressure or vacuum pressure. What you have seen over here in this manometer or these manometers, these are simple cases. Therefore, they are called as simple manometers. This is the first category of manometers called as simple manometers. Now let us take the second type of manometer, which is known as differential manometer. Now the question is, what is the purpose of a differential manometer? How is it different from a simple manometer? You see, a simple manometer was measuring the pressure at a particular point. That was fine. That is not the purpose of a differential manometer. It is going to measure the difference in pressure between 2 points. So I can say the purpose of a differential manometer is to measure difference in pressure difference in pressure between 2 points. The purpose of a differential manometer is to measure the difference in pressure between 2 points. As you move further in the subject of fluid mechanics, you will find out many applications where difference in pressure is important. A simple example. Let us say you are working with a pipe flow. Okay. In a flow through pipe, for finding out the value of head loss, you require the value of difference in pressure between two sections. So when you require difference in pressure, you can use a differential manometer for that purpose. Now let us take an example of a simple U-tube differential manometer. Suppose I have a pipe over here. This is a pipe. A pipe. Let us say a fluid is flowing over here. There is a fluid that is flowing over here. I wish to find out difference in pressure between two locations. What I do is I install over here a U-tube differential manometer. Let us say I install over here a U-tube differential manometer. Inside the pipe, the fluid that is flowing, which I am not shading right now, let us call it as working fluid. And let us say over here the manometric fluid is assuming this position. This is a manometric fluid. I measure the difference. Let us say the difference in elevation over here is HM. Inside there is a fluid. That fluid is working fluid. So let us say the property of the working fluid is gamma W. The property of the manometric fluid is gamma M. I take 2 points over here. Let us say there is a point A. There is another point over here. Let us say point B. A and B, both of them are at same elevation. I wish to find out what is the difference in pressure between point A and point B. So my question right now is PA minus PB is how much? To find out the value of PA minus PB, what I'll do is, I'll again take a horizontal level where the fluid from one end to the other end is continuous. That horizontal level is going to be this one. Let us say these 2 points. Assume this point is X and this point is Y. These 2 points I have taken, X and Y. I know by Pascal's law, the pressure at point X and the pressure at point Y, both of them are supposed to be same. Now what I do is, I take another height over here. This height H I am taking. Now let me tell you, this height H is not given to me in the question. Now we know that pressure at point X and point Y, both of them are same. So I can start with Px equal to Py. Now please observe this point X over here. For finding out the pressure at point X, I'm going to start with point A first of all. I'm going to start with A and come down till X. So let us say I'm starting with PA. PA. Now I'm coming down. I hope you can answer me. When we come down, what sign am I supposed to put over here? I'm supposed to add plus. I'm coming down with a property gamma W and I'm coming down with a height H. So gamma W times H. This is a pressure at point X. Come to Py now. The pressure at point Y, let us start with B now. So I can say PB. Now you see, I have to come down from this point till here first of all. I'm not coming down till the complete height H. I'm only coming down by a height equal to H minus HM. So therefore plus gamma W multiplied to H minus HM. Next thing, after this particular point, I have to move till here. Again I'm coming down, therefore plus. With a property gamma M, so therefore gamma M over here multiply to, with the height HM, therefore HM over here. I have reached the point Y, now I can establish equality sign. Now please observe, on the left hand side I have gamma W into H with a positive sign, right hand side gamma W into H with a positive sign. I can cancel both these things. While I cancel both these things, I have eliminated this H. H was not given to me at first place. I took the help of H, I have eliminated H now. Now I want PA minus PB. So let us arrange PA minus PB on one side. It has to be equal to, please observe, I have gamma M HM positive, I have gamma W HM negative. You see HM over here is common, so take HM common. You have gamma M positive minus gamma W negative. Okay, this is the value of PA minus PB. I have found out the answer for this thing. Now let us extend this question one step ahead. Mostly in examination, they are not going to limit only till finding PA minus PB. They can sometimes ask you to find out pressure difference or pressure in terms of head. So let us say the question is finding PA minus PB in terms of head of working fluid. I hope all of you can recall that whenever I want pressure in terms of head, all I have to do is take the pressure divide by gamma. Since I want this difference in terms of head of working fluid, I am now going to say H working has to be equal to PA minus PB whole divided by gamma working. That is equal to hm multiplied to. Now please answer me. What is gamma m by gamma w? Can I not write it as Sm by Sw? Yes. Minus gamma w by gamma w is going to give me 1. So this is a value. In this setup, the value of Pa minus Pb in terms of head of working fluid is equal to Hm multiplied to Sm by Sw minus 1. Now this kind of differential manometer you have seen is known as U-tube differential manometer. U-tube differential manometer. But sometimes we use another kind of differential manometer which is known as inverted U-tube differential manometer. All you have to do is you have to create the same setup in an inverted manner. Let us take an example. Suppose you have a pipe running over here. You have a pipe running. Let us say you install over here an inverted U-tube differential manometer. Inverted U-tube differential manometer. Let us say this is certain point A. Over here I'm having some point B. The fluid is flowing in this direction. Now let us say the manometric fluid has assumed some position like this. This is a position manometric fluid has assumed. And he has also given you that this difference, let us say, is equal to Hm. The property of fluid he has given you is gamma m. The property of working fluid, of course, is gamma w over here. Again, the question stands the same. What is the value of Pa minus Pb? And identify the value of Pa minus Pb in terms of head of working fluid. This is a given question. Now, for solving this question, again, what I am doing, I am creating something which is not given in the question. Let us say I am creating a certain height h over here. I will take the help of this h. Later on, I'll eliminate h just the way I have done over here. Again, how do we start? My personal preference is taking a horizontal level where the pressures on either sides are same. I hope you can guess very easily now that horizontal level is going to x over here, and let us say a certain y over here. So now I can start with pressure at point x is equal to pressure at point y. Now what is the pressure at point x? Now this is the first time you are coming across motion in upward direction while calculating pressure. So let me start with Pa first of all. Pa. Now you see you are going up. Till now you have gone down, you add it. Now you are going up, you subtract. So therefore minus. Now the property you are going up with is gamma working. So therefore gamma working multiplied to. The height you are going up is with h. So h. You have reached point x. Fine, Px is done with. How do we start for Py? Let us again start with Pb. Pb. Okay, Pb. You're going up. You're going up by a distance h minus hm. And you're going up with a property gamma w. Therefore, minus gamma w into H minus HM. We are still not done. We have reached only till here. We have to further go up till here. Since I'm going up minus, I'm going up with a property gamma m, therefore gamma m. I'm going up with a height hm, therefore hm. Now I equate both these things. Fine. Now please observe, I have a negative gamma wh over here. I again have a negative gamma wh over here. I can cancel these two off. Fine, they are cancelled off. So what am I left with? I am left with PA minus PB is equal to PA minus PB is equal to. Now please observe, I have minus times minus plus. So therefore gamma W multiplied to HM is positive minus gamma M multiplied to HM is negative. So now I can say PA minus PB is equal to. Let me take HM common. Should I take HM common, I'll be left in bracket with gamma working minus gamma manometric. Okay. Now what I have to do, after having found out the value of PA minus PB, I wish to find out same thing in terms of head of working fluid. So let us say divide on either side by gamma of working fluid. What will I be left with? So this difference in terms of head of working fluid is going to be equal to HM multiplied to. Now gamma W by gamma W is supposed to yield 1 minus gamma M by gamma W is equal to SM by SW. This is the answer for this given setup. Again, I do not want you to memorize any of these things. These things are only particular for the given setup. If the setup changes, if the nomenclature changes over here, even these equations are going to change accordingly. So therefore, just use the logic that going down means adding, going up means subtracting. That is more than sufficient to identify the answers in the case of manometers. This is known as your YouTube differential manometer, and this over here is known as inverted YouTube differential manometer. Now, when we already have a YouTube differential manometer, what is the purpose of defining another manometer called as inverted YouTube differential manometer? Now you see, in the case of YouTube differential manometer, we are going to measure pressure differences which are relatively high. But in the case of inverted YouTube differential manometer, you can measure pressure differences which are relatively low. Please remember this thing. Inverted YouTube differential manometer helps you identify pressure differences which are relatively low. Why is it so? The reason is the manometric fluid you are using over here is a lighter fluid. Your working fluid is heavier compared to manometric fluid. Therefore, you can measure smaller pressure differences. So if anyone asks you that you are having a smaller pressure difference, which manometer is more preferable? Is it YouTube differential manometer or inverted YouTube differential manometer? Your answer is supposed to be inverted YouTube differential manometer. This is regarding the concept of differential manometers. The next manometer we are discussing is known as inclined leg manometer. Inclined leg manometer. What is the definition of inclined leg manometer and where is it used? Let us see. Inclined leg manometer is any manometer, any manometer having at least one limb inclined with respect to the vertical. Any manometer having at least one limb inclined with respect to the vertical is known as inclined leg manometer. Now let us see what is the purpose of inclining. Let us take an example of it. Imagine you have a container in which there is a fluid filled. Let us say to this container you have a piezometer connected. A piezometer connected. Neglect capillary effects. So what happens is the fluid in the piezometer would rise up till here. Let us say you are increasing the pressure in this container by a very small quantity P, extremely small amount of pressure. Now due to this increase, what happens? The fluid, let us say, in the piezometer is rising up. Let us say it is rising up by a height small h. Rising up by a height small h. If anyone asks me what is the pressure over here, I would say pressure is equal to gamma times h. That is very simple. But imagine that this h is so small, it is difficult for me to measure. I am not able to measure the value of h. So I require a slightly bigger height or bigger length. For that purpose, what I do now is, instead of connecting this piezometer, let us say I connect over here an inclined tube. For example, connect over here an inclined tube, and this inclined tube again, this inclined tube again is going to have the same rise in fluid. The height by which it is rising up again is remaining same, but the length that is being measured is the inclined length over here. Let us say the length measured is L over here. Suppose this tube is inclined by an angle theta. If it is inclined by an angle theta, I can say from here that the value of h is equal to L times sine theta. Now please understand, I wanted the value of h, but I was not able to measure h. So what I have done, I am again measuring h, but what I have done is, I am measuring h taking the help of a bigger length L. The value of L, of course, has to be greater than h. Now what this is doing is, this is helping me measure a smaller amount of pressure which was not measurable by the conventional tube. So by inclining a tube, I can measure smaller pressures but using the same fluid. So now I have the value of pressure equal to gamma times, instead of h I can say L sine theta. L sine theta. So in the case of inclined leg manometer, this is how we measure the pressure. What is the advantage of inclined leg manometer? Let us see. Advantage. Advantage of inclined leg manometer. The advantage over here is the sensitivity of pressure measurement is increased. So I can write inclined leg manometer increases the sensitivity of pressure measurement. Inclined leg manometer increases the sensitivity of pressure measurement. Now, how do you imagine this sensitivity? Sensitivity. What is this sensitivity? Now, you see, the sensitive word basically means that the response to a smaller thing is still there. For example, this h over here was very small. It was not being measured over here, but it is being measured in the case of inclined leg manometer. That means there is a response to smaller pressure difference also. So I can say sensitivity is ability to measure, ability to measure smaller pressure, smaller pressures. Now, what is the value of sensitivity or the formula of sensitivity? The formula of sensitivity over here is given by the length measured upon the corresponding height. It is equal to length measured upon the corresponding height. Now, if you see over here, corresponding height h is equal to L sine theta. So I can write S is equal to L upon L times sine theta. L and L over here cancel off. If they cancel off, I ultimately get the value of sensitivity is equal to 1 upon sine theta. It is equal to 1 upon sine theta. Mind you, the angle theta over here is measured with respect to the horizontal, but when we define inclined leg manometer, we define that it is inclined with respect to the vertical. The general convention is theta is measured with horizontal, but definition is with respect to the vertical. This is regarding the concept of inclined leg manometer. Now let us start the chapter of hydrostatics. A very interesting part of statics, an important part as well. What do we study in hydrostatics? Imagine you are having a plate which is having zero thickness and only area defined. Let us say you submerge the plate inside a fluid. Now what happens? On that plate there is going to be pressure intensity acting. Due to these pressure intensities, there will be a net thrust developed. That thrust we are studying in the topic of hydrostatics. But before I go into hydrostatics, let me guide you to hydrostatics taking the help of strength of materials. Let us take an example from strength of materials, which is a common example. Imagine you have a beam. Let us say a simply support beam. Suppose I have a simply support beam. On this simply support beam, I have some loading intensity like this. I hope all of you know this kind of loading intensity. Very famously, it is called as UVL, is it not? Uniformly varying load. Let us see, the intensity is represented by W, and this over here is x-axis. Now I can say that intensity of loading over here is a function of x-axis. If I ask you how much is the net load acting on this beam, then very commonly people answer it is equal to the area under the loading curve. That is correct. But how do we get that? For getting that, what I'll do is, since W is varying, I will go at some x position. I'll take a small thickness over here, let us say dx, a small thickness dx, and over this small thickness dx, let us say there is a differential force developed. If I want to know how much is a differential force, I can say the value of differential force is equal to the intensity of loading over here, that is W, multiplied to the length over here, that is equal to dx. Net force over here has to be equal to integral of W dx, ranging from x is equal to 0 till x is equal to L. Imagining the span of this beam is L. So this basically is telling you that the net force is the area under the load curve. All this is fine, but how is it related to hydrostatics? Now let us say I have over here an interface. Below this interface I'm having a fluid which is having a property gamma. On top it is exposed to atmosphere, therefore the gauge pressure on top is equal to 0. Suppose I take a plate, I submerge the plate completely. Let us say the plate has assumed this position. Suppose I represent the plate by Mn. Now please imagine the plate is going to have some kind of width coming perpendicular. It might be having an irregular shape. But every differential area, let us say this is a small differential area, by the virtue of the fluid on top, it is going to experience some intensity of pressure. Let us say this is the intensity of pressure developed. But there's a catch. Please understand, there is going to be one more intensity of pressure, equal and opposite, from the bottom as well. If this is equal to P, this again is equal to P. And where do we get this from? It is talking about a point pressure, a pressure at a particular point in a fluid at rest. This is basically Pascal's law. Now what happens if I draw the intensity of pressure diagram? I'm supposed to get an intensity of pressure diagram something like this. Let us say this is how the intensities of pressure are acting throughout the plate. And a mirror image has to be developed at the bottom as well. But then what we do, we consider only one side for our analysis. Let us say I am considering only one side for our analysis. So imagine I'm only having the intensity of pressure over here on one side of the plate. Now please observe the similarities between these two diagrams. Over here you are having a beam which is having length defined. Now coming to this case, you are having a plate which is having area defined. The intensity of loading over here was equal to load per unit length. That intensity of loading is W, load per unit length. The intensity of loading over here is load per unit area. That is P over here. Now because of this load per unit length, you are having a net force. I am going to have a net force developed on this area Mn, because of P. Now the question is, what is the differential force that is acting on this plate at this differential area? On this differential area, how much is a differential force acting? Now you see the similarity over here. It was intensity multiplied to a small length. Over here it has to be intensity multiplied to a small area. Therefore I am going to get the value of net force developed equal to integral of P times dA over the entire area A. Integral P times dA over the entire area A. This is the net value of force acting on one side of a plate. Mind you, I'm only talking about one side of a plate due to hydrostatic pressure intensities. What would happen if I would take both the sides of the plate? Let us imagine, if I take both the sides of the plate, there is going to be a force pushing down and equally opposite force is pushing it up. Therefore what will happen? The net force would be equal to 0, is it not? So therefore we are considering only for one side of a plate. This is known as your hydrostatic force. The purpose of this chapter right now is first of all to find out how is the hydrostatic force acting on a plate. Now the plate can be flat plate as well as it can be curved plate. So we will gradually go further to see the case of curved plate as well. First we'll see what is happening in flat plate. After finding out the value of force, our second purpose will be to find out the location of this force. Now, before I go into this, let me come back over here. If I ask you, where is this net force located? Then you would answer, it is going to pass through the centroid of this particular area, loading area. So for example, let us say centroid is over here of the loading area, then through this particular point, you are having the net force passing. This is correct. But how do you get that? We get that from a particular theorem called as Varignon's theorem. It is called as Varignon's theorem. I hope all of you have studied this theorem in mechanics. What does Varignon's theorem say? It says that take this particular point as your reference. Now this force over here, this dF over here is creating some moment about this particular point. Likewise, you are having infinite number of dFs. All of them are going to create some moment over here about this particular point. Now all these moments, let us say summation of differential moments is going to give you the net moment. It is going to give you the net moment, and that net moment should be due to the resultant force. This is what Varignon's theorem says. Same thing we are going to apply. Let us say somewhere over here I choose my reference point O. This differential force is creating some moment about point O. Likewise, every differential force is going to create a moment about point O. I can say the sum of all the moments should be equal to the moment of the resultant. Going by that logic, let us say somewhere over here, I get that there is going to be force F acting. This particular point on the plate is known as center of pressure of the plate. It is called as center of pressure of the plate. Now mind you, there is one more point on the plate which is the geometric center of the plate. Geometric center and center of pressure need not be same. You will see mostly they are going to be different. Logically you can tell me where is the geometric center going to be with respect to center of pressure. In this case it has to be somewhere above over here. Your center of pressure over here will be below. Why so? Because you see there is more intensity of loading on the lower part of the plate compared to the upper part of the plate. Since the intensity is over here greater, your center of pressure should get polarized on one side. I hope you are following. This particular point is the next important point in our chapter. For locating this thing, let us say I take the reference as interface, I measure this height I call as h star. So my second formula in this topic will be regarding the value of h star. We will see the formulas later on. I just want you to get the feel of the subject right now. So my first aim was to identify how much force. My second aim is to identify where is the force. Last aim. This last point is not that much important, but sometimes you can use for solving some questions. Our last point is supposed to identify how much eccentricity is there between centroid of the plate and center of pressure. For example, if you see over here between these 2 points, I am having an offset distance. This offset distance I am representing as eccentricity of the plate. So my third point will be to talk about this E. It is to talk about E over here. E stands for eccentricity. So in a nutshell, you can say the aim of this topic is to identify first of all how much force is acting on one side of a plate when it is submerged in a particular fluid. Again, please highlight one side of a plate. Second aim is to identify where the plate is located. Where the force is located. The point at which the force is located is known as center of pressure. Its distance from the interface is represented generally by h star. Our third aim is to find out how much is the offset distance between centroid and center of pressure. Why did I start from here? You see, this topic is just one step ahead of your beam problem. In beam, all you are having was load per length. In the case of plate, you are having load per area. So you're just going one step ahead. You are having load per length, load per area. You see, one step ahead over here. So many similarities can be driven out from here and here. Let us now go for looking at the formulas of each of these things. Now in hydrostatics, let us start with the concept of flat plates. You are seeing a fluid over here under which you are having a plate submerged. Let us say this is a plate, and below what you are seeing is the actual image of the plate. I want to find out the force. So for that purpose, I am looking at the intensity of pressures first of all. So the intensity of pressures you are seeing are developing as they are increasing down. Let us say this point O is my reference point. From point O, I am measuring a distance x and I am measuring a distance h, which is vertically down. The relationship over here is h is equal to x sine theta. The relationship between h and x is h is equal to x sine theta. I have chosen a differential area which is at a distance h below. On that differential area, I am having a differential force dF. Now the value of dF has to be equal to P times dA. Now how much is this value of P? The value of P is equal to gamma times h multiplied to dA. H I can write as x sine theta, therefore differential force over here is equal to gamma into x sine theta multiplied to dA. This is a value. Now if you observe in this equation, gamma and sine theta, both of them are constants. What is variable? X and dA, both of them are variables. So if I want to write the complete value of force, how much would that be equal to? Gamma and sine theta would come aside. I would have integral of x times dA over the entire area A. This is the value. Now integral x dA over the entire area A is how much? This is our next question. Now this you have studied in the concept of moments of area in mechanics. Now this has to be equal to complete area times x bar. What do I mean by x bar? You see over here, this entire plate is having a centroid. The distance of the centroid from the reference point O is x bar. So now what I can do is I can replace this term with area times x bar. So now I have force F is equal to gamma times sine theta into x bar times area, Now please observe this x bar sine theta. You see, x sine theta gave you h, so x bar sine theta will give you h bar. Now what is h bar? You can see the location of centroid from the interface is h bar. So from here I can say the value of force is equal to gamma times area times h bar. This is my first formula. This is the first formula which is talking about how much is the hydrostatic force acting on one side of a flat plate. Gamma times area times h bar. How to remember this thing? For remembering this, I would want you to understand it like this. Force we know, force is equal to pressure times area. Pressure times area. All of us know this thing. Force is equal to pressure times area. But the problem we are having in this case is pressure is not a constant. You see, pressure was a variable. This is a variable. You can observe over here the intensities of pressure are keeping on changing. So pressure is a variable. So what I'll do is I will now take average pressure. Average pressure. What do I mean by average pressure? You see, throughout this particular plate, the average pressure should act at the centroid of the plate. Therefore, this average pressure has to be equal to gamma times centroid's position is h bar multiplied to area. Therefore, this gives you the value of force. So in simple language, you can remember that hydrostatic force is equal to average pressure multiplied to area. This gives us a first formula. Now let us see how to find out the value of H star. I hope all of you remember what H star is. It is a location of center of pressure from the interface. So now what I do is, to find out the value of H star, I will first of all start with differential moment about point 2. What do I mean by differential moment about point 2? It is a moment created by the differential force small df you are having with respect to point 2. So I can say it is equal to differential force multiplied to the perpendicular distance you can see is x. So df multiplied to x. Now I can write df as, if you remember the value of df from the previous slide, it was equal to gamma times differential area into x sine theta. This was the value of differential force, again multiplied to x. So I get the value of differential moment about point 2 is equal to gamma times differential area multiplied to x square times sine theta. Now you see what all things are constant over here. I observe that gamma is a constant, sine theta is a constant. Only x square times dA is a variable. So I can say integral of x square times dA is required. Now the question is, what is going to be the result of integral of x square times dA? If you recall, the second moment of area says that integral of x square times dA over the entire area A is equal to I about y axis passing through O. I about y axis passing through O. Furthermore, by parallel axis theorem, I can say I about y axis passing through O is equal to I about y axis passing through centroid plus area times distance square. Now if you see, the distance from the centroid till the point O is equal to x bar. So this has to be equal to area times x bar square. Now I am going to write down the equation of complete moment about O, therefore has to be equal to gamma sine theta as it is, gamma sine theta as it is, multiplied to integral of these things was equal to this much. So let me write I plus area times x bar square. This is the value I am having. Now let me save this as some equation number 2. Equation number 2. Varignon's theorem says that the net moment should also be equal to the moment created by the resultant force F. So I can say from here, the net moment should also be equal to moment by force F, that is F multiplied to, what is the distance now? It is equal to x star. It is equal to x star. Now what I do is, I'll write the value of force F as gamma times area times h bar. Let me do one thing.
instead of h bar, let me write it as x bar sine theta. This is the value of force F multiplied to x star. Let us save this as equation number 3. Now we see that moment about O and moment about O are same. So therefore equation 2 is equal to equation 3. Since both these equations are same, I can now write gamma area x bar sine theta multiplied to x star should be equal to gamma sine theta multiplied to I plus area times x bar square. Now you see gamma sine theta and gamma sine theta cancel off. So what am I left with? I am left with x star is equal to I am taking area x bar over here. So I have area x bar square plus I upon area x bar upon area x bar. Now you see the result of this is going to be x bar. So I can say this is equal to x bar plus I upon area times x bar. Now what I can do is I can replace every x by its corresponding h by sine theta. Therefore I can say h star upon sine theta has to be equal to h bar upon sine theta plus I upon area times h bar upon sine theta. Now multiply sine theta throughout. From here you get the result, ultimate result, that the value of h star has to be equal to h bar plus I sine square theta upon area times h bar. This is our second formula which we are looking at. So let me save it as some equation number 4. The first equation was for force. If you remember, the value of force was equal to gamma area h bar, very simple formula. The second equation which we are saving is for hydrostatic, is for the location of center of pressure, that is h star, which is equal to h bar plus I sine square theta upon area times h bar. Both these equations are very important. Our next aim is to find out the value of eccentricity. If you observe from this diagram, the value of E has to be equal to x star minus x bar. So I can write x star minus x bar. I can also write this as it is equal to h star minus h bar whole divided by sine theta. Now please recall what was the value of h star minus h bar equal to from the previous slide. If you see, it was equal to I sine square theta upon area times h bar. Let us say I divide this again by sine theta. If I divide this again by sine theta cancels off. From here I can say the value of E is equal to I sine theta upon area times h bar. So I have the formula of E as I sine theta upon area times h bar. So these are the three formulas we have to look for. Let us say this equation is over here, equation number 5. So the first formula we were having, let me summarize. The first formula we were having was force, which is equal to gamma times area times h bar. The second formula we were having is for h star. It was equal to h bar plus I sine square theta upon area times h bar. And the final formula is for eccentricity E, which is equal to I sine theta upon area times h bar. These three formulas we are having. Now at this point, I want you to observe one very important thing. I want you to see when is the value of E becoming 0. So the question is, when is E equal to 0? When is E equal to 0? This is the question. When is the value of E becoming equal to 0? I see for the value of E to become equal to 0, there are two possibilities. The first possibility, standard case, when sine theta is equal to 0. When sine theta is equal to 0. If sine theta is equal to 0, it implies that theta is equal to 0. It implies that the plate you are having, which right now is inclined as you see, it is actually in flat, it is in horizontal position. So I can say the flat plate is in horizontal position. Horizontal position. This is the first case. The second case is actually an imaginary case. That case is when the value of area times h bar is extremely high compared to I sine theta. So let us say area times h bar is extremely high compared to I sine theta. Now what would happen if denominator is extremely high when compared to numerator? You can say if E not equal to 0, at least it is tending to 0. I can say E is tending to 0. That means you are submerging the plate extremely below the interface, so the value of E is tending to 0. Now why am I looking at these cases? What is the physical meaning of E becoming equal to 0? What does it imply? When E becomes equal to 0, you see the center of pressure and the centroid of the plate, both of them are matching. So I can say center of pressure overlaps centroid of the plate. For this to happen, either of these two conditions should take place. Either the plate should be in horizontal position, or the plate should be submerged so much below the interface that the value of area h bar should be much greater than I sine theta. It should be much greater than I sine theta. This gives one very important point which was once asked in IES examination. That point is, as you keep lowering the plate or increasing the depth of the plate, what happens to the distance between center of pressure and centroid? Now you can think logically. Let us say you are keeping the plate much lower. When you keep on increasing the depth, I is not changing. You see, I is not changing. Sine theta is not changing. Area of the plate is not changing. Only thing, the value of h bar is keeping on increasing. So as the denominator keeps on increasing, the net fraction has to decrease. So I can say, as I keep lowering the plate or increasing the depth of the plate with respect to the interface, the center of pressure should keep on approaching the centroid of the plate. To the point, if I keep on increasing the depth and make it infinite, let us say virtually I'm making it infinite. So what happens? The distance between them comes out to be 0. P completely overlaps with point G. Now there's an alternate way of solving the questions on flat plates, that is by a diagram known as pressure prism diagram. Pressure prism diagram. Now how to understand this thing? Let us say this is the actual shape of a plate you are having, which is submerged inside a fluid. And let us say these are the intensities of pressure throughout. And because of these intensities of pressure, there is a prism like shape developed. Suppose some prism like shape is developed. Each arrow over here is representing the intensity of pressure. Now imagine this entire volume over here. The base of this volume is the area and the height of this volume is the intensity of pressure. So I can say the differential volume of this pressure prism diagram has to be equal to differential area of the base multiplied to the pressure. If it is so, pressure times differential area has to give you the differential hydrostatic force. So first thing I learned from here is the differential volume of the pressure prism is giving you the differential hydrostatic force acting on the particular area. So I can say complete volume of the pressure prism diagram has to be equal to hydrostatic force. Hydrostatic force. So I can say the entire volume of the pressure prism diagram is equal to the hydrostatic force acting on the plate. So this is my first point. Let me save it as my first point. What is the second point? Now you see, this entire volume of pressure prism is supposed to have a centroid. Let us say this point over here is representing the centroid of pressure prism. It is representing the centroid of pressure prism. Now let us say through this centroid, the net force is concentrated. The net hydrostatic force is concentrated through this centroid. So if I create an impression of this centroid back on the plate surface, let us say this is the impression of the centroid on the plate surface. What is this point representing over here? This point is supposed to represent the center of pressure. So second point I'm having is the impression or projection. You can use any of these two words. Projection of centroid of pressure prism on the surface of plate represents center of pressure. Center of pressure. So now instead of going for the conventional formulas that force is equal to gamma area h bar, you can use this thing, that is the volume of pressure prism is equal to the hydrostatic force. Instead of going for the formula of star, you can go for this method also. But when are these methods going to become difficult? You should know that, because in those cases you should avoid these methods. Please remember, if you are having a plate which is not having a uniform width perpendicular to your paper or your screen, that time don't go for this method. Because just imagine you are having a triangular plate. In the case of a triangular plate, if you start developing the intensities of pressure throughout, you are going to develop some kind of a diagram like this, which is having a variation in height and which is also having a variation in base. So in this case, even though the formula for volume of pressure prism still holds good, But calculating this volume becomes extremely difficult. So instead of going for this, go for the conventional formula, that is force is equal to gamma area h bar. So please avoid using this method whenever the area is not having a uniform width. For example, a circle, a triangle, a trapezium and all. What if you are having a rectangle? Fine. In the case of rectangle, it will be easier to use this method. Now let us take the case of hydrostatics on curved surfaces. The first thing we have to know over here is, why is the analysis in curved surface different from that in the case of flat surfaces? Let us see. Imagine this is an interface. This is an interface you're having. You have a flat surface over here, and you have a curved surface over here. In the case of flat surface, if you see, you are having intensities of pressure which are keeping on increasing as you go down. Now something like this. In the case of curved surface, again the intensities of pressure are keeping on increasing as you go down. So first thing we see is intensities of pressure, they are keeping on changing. That is same in the case of flat surface as well as in the case of curved surface. So where is the difference lying? The difference, if you see, is in the direction sense of these intensities of pressure. If you see, the direction of every differential force in the case of flat surface is same. But in the case of curved surface, the direction of every differential force will keep on changing. So I see over here, direction of every df. df over here is standing for differential force. Let us say this is df1, df2, so on until dfn. Direction of every df changes in the case of curved surfaces. In the case of curved surfaces. Now if the direction is changing, then how to analyze this thing? Very simple logic. In mechanics or in your basic physics also, whenever a vector's direction changes with respect to space or time, you resolve the vector. Let us say I resolve over here this differential force into vertical component and horizontal component. Then I can say that I am having the net force, hydrostatic force, divided into two parts. One part, let us say, is force in horizontal component and force in vertical. Then I can say the net hydrostatic force acting has to be equal to square root of horizontal component square plus vertical component square. This is the first thing you have to understand in the case of hydrostatic on curved surface. I hope all of you are following till here. The summary is, since force direction keeps on changing, we are resolving into horizontal and vertical components, and then we are taking the vectorial sum of these two to get the net value of force. Fine. Now the question that arises is, how to identify the value of horizontal component and how do we identify the value of vertical component? Let us start with horizontal component first. Suppose a bit I am taking over here, horizontal component. Horizontal component. Horizontal component. Now all these formulas, what we are seeing over here, they require some visualization. So please be with me in this. Let us say you are having a curved surface. On top, you have an interface. Let us say this is the interface. The property of the fluid over here is gamma. This is a curved surface we have. Now what I do,
I take a very small differential area, let us say this over here is an extremely small differential area. Now when I'm showing here, I'm showing it quite big, but please imagine it is very small. This is only for your visualization purpose. This differential area, let us say, is at a depth of h from the interface, and over this differential area there is some differential force acting. Let us say the differential force is dFn, or rather you could just say dF. dF is the hydrostatic force acting on this tiny area, dF, let us say. Now what I do is I will draw a bigger image, a magnified image of this dA. Let us say the magnified image of dA is like this. Now please don't be worried that it was a curved surface, then why did I draw a flat surface over here? Please understand that a curved surface, very small part, is equivalent to a flat surface. That is why I'm drawing a flat surface over here. So this dA right now is a flat surface for me, and over the dA I'm having a force acting. Let us say that force is equal to dF. So all I have done is I have magnified this differential area over here, and I'm showing this dF over here. Fine, till here everything is fine. Now let us say the inclination of this dA with respect to horizontal is equal to theta. This angle is theta. Now I can say that dF is having a component over here, dF horizontal, dF horizontal. If this angle is theta, by the virtue of these two being parallel lines, even this angle has to be theta, and this has to be equal to 90 degrees minus theta. Please feel free to pause the video and visualize these angles. I hope the angles are quite clear. This is very basic parallel lines concept. These two lines are parallel, by the virtue of which this angle and the angle which I am not showing, both of them are same, and then this angle has to be 90 degrees minus theta. Fine. From here I can say that the value of differential force horizontal has to be equal to dF multiplied to cos of 90 minus theta. So dF multiplied to cos of 90 degrees minus theta. This is the value of differential horizontal component acting on differential area. Fine. Cos of 90 minus theta, all of us know this thing, it is equal to sine theta. So let me write it as sine theta. Till here everything is fine. Okay. Now next thing, what is dF over here equal to? Let me write the value of dF. dF I can say is equal to pressure multiplied to differential area, and pressure we know is equal to gamma times h. Differential area is differential area itself. Differential area itself. If I push in this value of dF in the above equation over here, I am supposed to get differential horizontal component is equal to gamma times h times dA, and then I am having sine theta over here. This is a value. Now I want you to combine these two things. Combine these two things. Gamma into h is fine. dA sine theta you combine. What does dA sine theta give you? Please visualize. This area over here, it is going to have a projection in the vertical plane. So let us say in the vertical plane, I am producing a projection of this area. There is a projection of this area. Let me say this is differential area projected. What would this value be? Come on, this is very simple trigonometry. If this is dA, this has to be, the vertical projection has to be equal to dA sine theta. It has to be equal to dA sine theta.
So from here I can say the differential horizontal component has to be equal to gamma times h multiplied to differential area projected in the vertical plane. Till here I think everything is fine. Now next thing, this is the value for a very small amount of force. Let us integrate. Let us say by integration. By integration, if I integrate over here, I can say the net horizontal component has to be equal to gamma times integral of h times d area projected over the entire region. What would this give me? This should give me the horizontal component is equal to gamma times area into h bar of projected area. Area into h bar of projected area. If you are not following this, don't worry. I'll make things clear to you now. This is the formula we are having. Don't worry about this. I'll make it clear by showing a diagram over here. I'm integrating these two things. I'm then going to get that if for differential area I have taken its projected image, for the entire curved surface I have to take its projected image in the vertical plane. This I am calling as area projected in the vertical plane. That is area projected in the vertical plane. Now what is h bar of area projected? You see, the logic is I don't have to worry about the curved surface anymore. All I have to think about is what is the projection of this curved surface in the vertical plane. Now this is my new area, and for this new area, let us say this is a point centroid of projected area. If this is a centroid of projected area, then this distance from the interface till centroid of projected area has to be equal to h bar of projected area. That means the horizontal component of force acting on a curved surface is equivalent. It is equivalent to the force acting on a flat surface. This is the formula for a flat surface. But which flat surface? The flat surface which is representing the projection of curved surface in the vertical plane. So now when I see this area, let us say this is some mn curve, I don't have to worry about mn. Let us say I am worrying about m projected and n projected flat surface. Whatever is the hydrostatic force on this projected area, that is my answer for horizontal component. So Fh is equal to gamma into area times h bar of projected area. What next? After finding out how much is the value of Fh, my next aim is to identify where this Fh is going to be concentrated. So remember, Fh is concentrated at the center of pressure, of the projected area, What does it mean? This projected area is going to have its own center of pressure somewhere below over here. Let's say it is a center of pressure for the projected area. At this particular point, I am going to have Fh concentrated. Fh is concentrated. If I find out how much is this height, this has to be equal to h star of projected area. It has to be equal to h star of projected area. So in simple language, if you want to tell this to someone, how would you explain it? You would just say that if you want to find out the horizontal component of hydrostatic force on curved surface, forget about the curved surface. Visualize the projection of the curved surface in the vertical plane. Whatever is present for this projection, same is true for the force and the location of force. This is regarding horizontal component. Now let us talk about the vertical component. So let us say be it vertical component. Vertical component. Let us say this is represented by F. How to calculate the vertical component of hydrostatic force on curved surface? Imagine this is an interface. The fluid below has a property gamma. And I'm having a curved surface something like this. Let us say this curved surface over here is some curved surface Mn. Let me do one thing. Let me extend a vertical wall from here, a horizontal surface over here. Let us say this Mn curved surface is the corner of a tank. I hope you are able to imagine whatever I've drawn over here. Let us say tank which is having a fluid of property gamma filled. My aim is to identify the value of vertical component on Mn. Horizontal component we have already seen. For horizontal component, let me just summarize once. Repetition will only reinforce your concepts. So let us say this is M projected, this is N projected, this over here is area projected. If I take the interface, let us say this is the centroid of projected area. So this distance will be equal to h bar of area projected. So if anyone asks you what is the value of horizontal component, you could very easily say it is equal to gamma times this area projected multiplied to this h bar. So you would write like this. This is fine, very simple. Where is it located? You can say it is going to have some point over here. At this particular point it is located. What is the direction of horizontal component? You could say since the fluid is present over here, the intensities of pressure will only push, therefore it is going to be on the right hand side. This is how your F horizontal is located. Now let us get back to our main concept. Our main concept is to identify the value of vertical component of hydrostatic force. Now, if you see on any small differential area, fluid present on top, the fluid present on top is exerting its weight equivalent force. Let us say the weight equivalent force is dW over here. The fluid present on top of this curved surface, very small curved surface I have chosen, let us say this again is a differential area. On top of that, the fluid is exerting a weight equivalent thrust in the downward direction in this case. Now if I calculate from M till N, then I can straight away say that F vertical has to be equal to weight equivalent thrust, weight equivalent thrust of the fluid, weight equivalent thrust of the fluid. If Fv is weight equivalent thrust of the fluid, what is the formula for Fv going to become? The formula for Fv therefore has to be equal to, I have told you previously as well that in our subject whenever you come across weight, always go for the formula gamma times volume. Gamma times volume. So this is a formula for Fv, very simple formula. Since it is a weight equivalent thrust, it has to be equal to gamma times volume. Now the question is how much volume? In this case, I think it is quite evident the volume you are supposed to choose is above the curved surface. Let us say this much amount of volume I am supposed to be choosing. This is the amount of volume I am choosing. Right now it is quite simple, but there can be some complications. Imagine a tank which is having this kind of shape. Imagine some tank which is having this kind of shape. Let us say this point over here is point M, this point over here is point N. Again, the property of the fluid is gamma. Now if I ask you what is the value of vertical component acting on Mn and the direction sense also, how do we answer this thing in this particular case? The formula is not supposed to change, it will still remain the same, gamma times volume. Only thing I expect from you right now is for you to identify which volume you have to take. I would recommend you to pause the video, draw this diagram and shade the volume. And please don't be afraid of doing any mistake. If you do mistake, you'll only learn from your mistakes. I guarantee you that. If you have drawn or shaded the region, let me show you one option. Probably someone has shaded this region. Let us say this region I denote as volume 1. And someone, let us say, has shaded this thing. These two are the answers or the options for the volume. Let us say this over here is volume V2. So either the answer is gamma times volume V1 or the answer is gamma times volume V2. Either of these two things. I do not know of any third wrong answer. One of these is correct and one is wrong. Now my aim is to identify which one is correct. Now, you see, at any particular point, let us say this particular point. Let me draw another diagram for you to understand. Let us say this is M, this is N. Please excuse my diagrams if they are not very artistic. Let us say this is gamma over here. Suppose I am choosing any point over here. I am choosing any point. Now, at this particular point, please ask yourself, what is the reason for hydrostatic force? Is it the presence of fluid or the presence of pressure? Two different things. Again, I repeat, is it the presence of fluid or the presence of pressure? The answer should be the presence of pressure over here. So my question to you is, at this particular point, the pressure corresponds to which height? I give you two options. Does the pressure at this particular point, let us say some point A over here, at this particular point, is the pressure corresponding to this height h1 or is it corresponding to height h2? Answer yourself. Is it corresponding to height h1 or height h2? The answer should be pressure corresponds to height h2. That means pressure at point A has to be equal to gamma times h2. If it is equal to gamma times h2, then I should be taking the fluid's weight which is corresponding to height h2. That means at this differential area I am supposed to take the weight of a fluid column, which is corresponding to h2. Likewise, at any particular area I am supposed to take the weight of the fluid column corresponding to the height measured from the interface till the curved surface. Now you might be thinking, how am I taking this volume even though the fluid is not present? So let me recall to you again that the fluid's presence is not important to me, it is the presence of pressure that is important to me. And pressure corresponds to these heights. So therefore, if I keep shading the volume, I am supposed to get the volume starting from the interface till the curved surface. The volume starting from the interface till the curved surface regardless of the presence of fluid. Please understand this, regardless of the presence of fluid. That means even though you're not seeing any fluid present over here, still you are supposed to take this volume only. The reason is at every point over here the pressure is corresponding to the heights measured from the interface till the curved surface. So this is the volume which is causing the value of Fv. So if you see in this particular case, the answer which is correct is this one, this is the wrong answer. So please don't blindly shade the volume which is the volume of fluid connected to the curved surface. Shade the volume starting from interface till the curved surface, regardless of whether the fluid is present over there or not present. Now comes the second question. The second question over here is, what is supposed to be the direction sense of Fv? Is it vertically up or vertically down? Now come back to this diagram, the first diagram. In this case, the presence of fluid was here, the pressure intensities were acting like this. Please imagine the pressure intensities. All of them were acting like this. Therefore, the vertical thrust is supposed to be downward over here. But come to this particular case, the fluid is going to exert the pressure in this direction. So tell me the vertical thrust. Is it vertically upward or vertically downward? If you resolve this, you are supposed to get vertically upward. So Fv in this case, or let us say this Fv which is correct, it is acting in which direction? It is acting in upward direction. And the Fv in this particular case, which is again gamma times volume, it is in which direction? It has to be in downward direction. So finding out the directions is very easy. All you have to do is just recall that fluid is going, or the pressure is going to push, and when it is pushing, when it is compressing, what direction is it acting, and then resolve the direction. Very simple. So now we have identified the formula for Fh, we have identified the formula for Fv. What next we do? We will say that the net force has to be equal to root over of F square plus Fv square. This is the value. Now one more thing. We have seen that the point of concentration of Fh lies, or it passes through the center of pressure of the projected area. And where is the Fv going to pass through? Very simple. This volume you have chosen over here. This volume V2 you have chosen over here. This is a volume V2 which is causing Fv. This volume is going to have its centroid. Let us say this is a centroid. Through the centroid of the volume, your Fv is going to pass. So now let me write down the summary. Let us say this is a summary of whatever we have discussed for Fv. First point over here, volume should be measured from the interface to the curved surface. Now comes a very important phrase, so I am changing the ink for you to understand this. To the curved surface, statement is not finished. Statement further continues saying that regardless of the presence of fluid, whether the fluid is present over there or not present over there, still you are supposed to measure the volume from there itself. Second point, Fv passes through the centroid of the volume in point 1. So whatever volume you have chosen in point 1, through that particular point, the direction sense over here has to be in the upward direction. So Fv is supposed to pass through the centroid of that particular volume. This is regarding the concept of Fh and Fv, and the result of course is root over of Fh square plus Fv square.
Continuing the curved surfaces, let us take a case. This case is AB is a curved surface which is having a net hydrostatic force of Fr. Fr, as you know, is equal to root over of Fh square plus Fv square. Now look at this 3D image which is showing you AB curved surface with the depth. Now Fv, which is equal to weight of the entire fluid above the curved surface, is supposed to pass through the centroid. Fh is a force on the projected area. It is passing to the center of pressure of the projected area. Let us look at the location of center of pressure for the curved surface. Now you see over here Fh. Fh is acting at H star. It is acting at H star of the projected area of AB, let us say. So if I want to write the formula, I can write it as H bar of projected area plus I of projected area multiplied to sine square theta is there, sine square theta upon area projected multiplied to H bar of projected area. Now in this term, I can cancel off sine square theta. Why so? I can cancel this out. It is equal to 1. The reason being that any projected area in the vertical plane is going to be a vertical one, is it not? So we see that in this particular case, the value of theta has to be equal to 90 degrees. If theta is 90 degrees, of course sine square theta is going to be equal to 1. So we have located this Fh. Fv, you have to find out where it is going to be. It is a centroid of the entire volume. You see the volume A, B, D, E, A, B, D, E, the entire volume we have taken here. Now please look at this very interesting point. Fh and Fv are going to have, if you go by principle of transmissibility, they are going to intersect at a particular point. Through that particular point, you are going to have Fr acting. It is Fr is acting through that particular point. If you want to find out the angle of inclination of Fr with respect to horizontal, then this theta with respect to horizontal is going to be tan inverse of Fv upon Fh. Let us start the next topic, which is buoyancy. One of the oldest topics in the subject of fluid mechanics. Very famous topic and very important from any examination point of view. Now let us see the definition of buoyancy first of all. Buoyancy is basically the upward thrust exerted by a fluid on a completely or a partially submerged body. In a simple language, you can say whenever a body displaces a fluid, then the fluid is going to create an upward thrust on that body, and that tendency is known as your buoyancy. Let us take an example. Imagine this is a container you are having, in which you can either have a matter which is completely submerged inside the fluid, or you can have something, for example wood and water you are having. Wood of course is having lesser density, so wood is partially submerged, or you can have a vessel which is again partially displacing the fluid. In any of these cases, the Archimedes principle states that there is going to be an upward thrust, and that upward thrust is equivalent to the weight of the fluid displaced. For example, you can see in the case of this, let us say stone, you are going to have Fb acting. Similarly, in the case of wood, you are going to have force of buoyancy acting. In the case of this vessel, again you are going to have this Fb acting. Our aim now is to identify a proof for this Archimedes principle. So let us see the proof of Archimedes principle. Imagine you have an interface.
you have an interface, and you are having a body which might be completely submerged. I'm showing completely submerged. You can as well have a body which is partially submerged. Let us say this is a body you are having. The property of the fluid inside over here is gamma. At any point, there is going to be a pressure intensity acting. So let us say you have some pressure intensity over here. Likewise, every point is going to have some pressure intensity acting. Every point is going to have some pressure intensities acting. Forget about the topic for some time. Think logically. What would the value of net horizontal thrust on this body be equal to? Now if you see, from this side when I look at this particular body, I realize that there is going to be some area projected on the other side. There is going to be some h bar of area projected on the other side. Likewise, when I view from this end, I'm again going to see some area projected. Again, I'm going to see some h bar. Both the area projected are same. Both the h bar are also. If both of them are same, then I can say whatever is the horizontal thrust acting from this end and from this end, both of them are equal and opposite. Therefore, the net horizontal thrust acting on this particular body is equal to 0. So first thing you have identified is there is no horizontal thrust acting on this particular body if the fluid of course is static. Then what kind of thrust is acting? The only thrust acting on this body is a vertical thrust. The question now is how much is the vertical thrust acting? Let us find out. Imagine I choose a very thin element on this particular body. Let us say this is an element I have chosen over here. This element is having a cross-section area. Let us say the cross-section area is equal to dA. This is the cross-section area we are having. So basically on top also you are having dA, on bottom also you are having dA. This is a very, very thin element. On top, let us say there is some force acting over here. Let me call this force as dF1, and on bottom you are having certain amount of force. Let us call it dF2. Suppose this top surface is at a distance of h1 from interface. Bottom surface is at a distance of h2 from the interface. h1 and h2 over here. And let us say the entire height of this element I have chosen is equal to h. So from here you can establish a relationship which is h2 minus h1 is equal to h. Is equal to h. Now let me write the value of dF1. How much is dF1 equal to? dF1 over here has to be equal to pressure intensity multiplied to differential area. Let us say pressure intensity is P1 over here. So this value has to be equal to the pressure at this point is gamma times H1 multiplied to differential area is dA. This is a value of dF1. Likewise, one more thing before going any further, let me also mention this dF1 is acting in the downward direction. Next thing, what is the value of dF2? dF2 is equal to pressure P2 again multiplied to dA. The value of this pressure P2 has to be equal to gamma times H2 multiplied to dA. This over here is the upward force. Now let us say that dF is the vector sum of dF1 and dF2. Vector sum. Vector sum means I have to take direction sense also into picture. So from here I can write dF is equal to, now if you see df1 is downward, therefore I'll write minus gamma times h1 multiplied to dA. df2 is upward, therefore I'll write plus gamma times h2 multiplied to dA. This is a value. Therefore, the net vertical thrust, this is all vertical please, the vertical thrust has to be equal to gamma times dA times h2 minus h1. What is h2 minus h1? You can see from here. This is the value of h2 minus h1. Therefore, the value of dF has to be equal to gamma times dA times h. Now please observe, what is dA times h? dA times h. This is basically the differential volume of the fluid displaced. It is the volume of the fluid that has been displaced. So basically I am talking about this much of volume of the fluid which has got displaced by this particular element. So now I can say that the value of dF has to be equal to, now we know that gamma times volume actually is the formula for weight. So therefore it is equal to differential weight of the fluid displaced. It is equal to differential weight of the fluid displaced. If this is true, then I can say by integration, the value of complete force in the vertical axis has to be equal to weight of the fluid displaced. This proves Archimedes' principle. So I can say this vertical thrust is known as force of buoyancy. And the formula for force of buoyancy, it is weight of the fluid that has been displaced. Therefore, it is equal to gamma times volume, both of which correspond to the fluid. So it is gamma of fluid multiplied to volume of fluid that has been displaced. Please understand that if there are two matters which have different densities, but they are having same volume of fluid displaced in same fluid, both of them are going to experience the same value of Fb, because the formula of Fb, it calls for gamma of fluid and volume of fluid displaced. Are you following? For example, in a container, if you take a fluid, you are taking a sphere of iron, and you take a sphere, let us say, of another metal. For example, you take of titanium, and let us say sphere and titanium, both of them are having same volume. Then the value of Fb on iron has to be equal to the value of Fb on titanium, because both of them are displacing the same fluid and both of them are displacing the same amount of fluid. So Fb in this case becomes independent of these particular materials. It depends, we'll see further when it depends. Now the next question is, where is this Fb going to be concentrated? If it is a force, there should be a particular point through which this force is concentrated. I would want you to guess. And what topic should help you in guessing? Please take the help of vertical component of hydrostatic force on curved surface. Take that concept to find out where the Fb should be concentrated. I hope you have found out that Fb is supposed to be FB passes through the centroid of the volume of fluid displaced. Whatever volume of fluid has been displaced, through the centroid of that particular volume, FB is supposed to pass. If FB is passing through that particular point, then we also call that particular point as center of buoyancy. We represent it by capital B. This point is known as center of buoyancy. Center of buoyancy. It is known as center of buoyancy. So till now what we have identified are two things. First thing is, what is the formula for force of buoyancy? Second thing is, where is the force of buoyancy going to be concentrated?
Continuing with the concept of buoyancy, let us now look at apparent weight. Imagine you are having a container. In this container, there is some fluid filled in. Let us say the property of the fluid is gamma. Now what I do is, I take a rope and a heavier body is submerged into the fluid. Let us say this body is having gamma B as its weight. When I am holding this, I am holding with some tension T. Let us say the value of gamma B is greater than the value of gamma of fluid. There is some amount of fluid that has been displaced. Now, if I draw the free body diagram for this particular body, let us say this is the body I am having. If I draw the free body diagram, the first thing I am going to observe is a force acting down. The force acting down is equal to weight. Let us say this is equal to weight of the body. The second thing, it is evident from the diagram, there is some tension acting over here. Let us say tension is T. Third thing, very important force, which is our subject's force. There is going to be another force over here by the virtue of buoyancy. Let us call this as force of buoyancy FB. Right now this body is in equilibrium. If it is in equilibrium, I can establish sigma F in vertical direction, let us say Z direction, has to be equal to 0. If sigma F is equal to 0, from here I can say that tension plus FB has to be equal to weight of the body, which further implies that the tensile force I am holding the body with is equal to weight of body minus FB. Now, if you observe over here, when I am holding this body with a force of T, I observe only T. I can't observe the weight of the body. So now what I am observing over here, it appears to me as the weight of the body. Again I am telling you, it is appearing to me, it is not the actual weight, it is appearing to me as if this is the weight of the body. That is why we call this as apparent weight. Apparent weight. So in this case, the value of apparent weight has to be equal to actual weight minus FB. Actual weight minus FB. This is the reason why when a person goes into a swimming pool, he feels lighter. What he is feeling is actually the apparent weight of his body, and that is equal to his actual weight minus FB.
In general, when you are standing, you are observing your actual weight, but when you go into water, you would feel apparent weight. Now, what kind of questions can be asked from here? Commonly, questions asked on this topic are regarding apparent weight of a particular body in two different fluids. So, let us take a standard problem. Apparent weight in two different fluids. Two different fluids. Apparent weight in two different fluids. Now, let us say one body is being submerged in two different fluids. Suppose I am having a container over here, I am having another container over here. In both these containers, I am having fluids. Let us say gamma 1, and over here gamma 2 is a fluid. I submerge a body over here. There is some tension T, let us say T1. I submerge the same body over here. There is some tension T, let us say T2. Now, from here I can say, from this case I can say, the value of T1 has to be equal to weight of the body minus FB1. From here I can say the value of T2 has to be equal to weight of the body minus FB2. Now, this equation I am writing from here. Now, if you look at the ratio of T1 to T2, let us say the ratio of T1 to T2 has to be equal to weight minus FB1 upon weight minus FB2. Weight minus FB1 upon weight minus FB2. This I can further say is equal to. Now, if you see all these terms, W, FB1, W, FB2, all of them are having same volume because same body is being submerged in both the cases. So, let us take volume common. If I take volume common, I am left over here with gamma of body minus gamma of fluid 1 upon volume common to gamma of body minus gamma of fluid 2. This is a condition. I can cancel off volume. Let us say I cancel volume. After cancelling volume, I observe that the ratio of apparent weight T1 upon T2 is equal to gamma body minus gamma 1 upon gamma body minus gamma 2. It also is equal to, now if you remember, the ratio of specific weight can be converted into ratio of densities, can also be converted into ratio of specific gravities. So, from there I can say SB SB minus S of fluid 1 upon SB minus S of fluid 2. This equation over here is helpful in solving many questions based on apparent weight. So, all you have to remember is the ratio of apparent weight of a particular body in two different fluids is equal to the ratio of difference in the corresponding densities or specific weights or specific gravities. All of them should give you the same result. Now, in buoyancy, let us look at the next topic, which is known as equilibrium and stability. A very important topic and a simple topic. Let us first of all understand the concept of equilibrium.
Equilibrium is a commonly used concept in mechanics. What is the meaning of equilibrium? Equilibrium means a condition in which the net unbalanced forces and net unbalanced moments equal 0. This is a definition of equilibrium. Net unbalanced forces and net unbalanced moments have to be equal to 0, which implies if you look at summation of f vector, it has to be equal to 0. If you look at summation of m vector, again this also has to be equal to 0. This condition is known as equilibrium. Now let us say a body is in equilibrium. For example, this marker over here. Right now, let us say I am hinging this marker about this particular point. This marker right now is in equilibrium. Let us say I disturb this marker slightly. From its equilibrium position, I am disturbing it slightly. Now this marker, after getting disturbed from its equilibrium position, can have three conditions. First condition is it might try to come back to its original position. Second condition is it might disturb itself further. Third condition is it might find a new equilibrium position after being disturbed. Now based on these three things, we are defining the next topic or next point, which is known as stability. Stability. Now what is the stability? Stability, basically it is the ability of a body to restore initial equilibrium after disturbance. Initial equilibrium after disturbance. That ability is known as stability. Now based on stability, we are having three types of equilibrium. The first type of equilibrium, it is known as stable equilibrium. Stable equilibrium. Let us take an example of stable equilibrium. Imagine you have a surface, something like this. In this surface, you are having a small spherical body. This small spherical body initially is at equilibrium. Let us say you disturb it. You disturb this ever so slightly, very slightly you are disturbing. After you have disturbed it, it has reached some new position over here. So you have given some disturbance. After this disturbance, if this body is having a tendency to come back to the original equilibrium position, then we say such an equilibrium was stable equilibrium. The second type of equilibrium we have is known as unstable equilibrium. Unstable equilibrium. Now what do we mean by this unstable equilibrium? Let us say you are having some surface now, inverted surface like that, and imagine you place a spherical body over here. Somehow you manage to keep it in equilibrium position. After having kept it in equilibrium position, you disturb this body very slightly. You are giving some slight initial disturbance. Let us say it has reached this new position. Now the question is, what is going to happen to that body after reaching the new position? Is it trying to come back, or is it further disturbing itself? You will observe that it is further disturbing itself. If a body further disturbs itself after initial disturbance, then you call that kind of equilibrium as unstable equilibrium. Now coming to final one, third type of equilibrium is known as neutral equilibrium. Neutral equilibrium. Now what do we mean by this neutral equilibrium? Imagine this time the surface is a flat surface like this, a horizontal flat surface. You are having a body over here, a spherical body. Initial equilibrium position is this thing. You disturb it slightly, let us say you displace it by some distance and you place it over here. Tell me, after having placed over here, is it trying to come back to the original position or is it disturbing itself further? Neither. It is neither coming back nor is it further disturbing itself. It has found a new equilibrium position. It has found a new equilibrium position. If it finds a new equilibrium position, then we call that type of equilibrium as neutral equilibrium. So you can summarize this thing by saying that there are three types of equilibrium based on stability. First one is the most desirable one. In that case, a body will try to come back to the original equilibrium position after disturbance. Second one, not desirable, unstable case, where a body would further disturb itself after initial disturbance. And third one, a body is neither disturbing itself nor restoring equilibrium. It has found a new equilibrium position. Now, where do we apply all these things in our subject of buoyancy? Let us see. Now, first of all, you should understand that for stability to be discussed, a body should first of all be in equilibrium. Without equilibrium, we can't start talking about stability. So let us see when all stability topic is possible. Imagine this is an interface we have, a fluids interface. Let us say I take a body, place it in this particular fluid. One of three things is possible. First thing is the body might be having lesser density than the fluid, therefore the body might be floating, something like this. In this particular case, you can say gamma of body is less than gamma of fluid. This, let us say, is the first case. Please don't misunderstand this first case in these things. This is entirely different, please. Second thing that might happen is the body might be submerged inside, but the densities of body and the fluid, both of them might be same. Let us say this is the second case. Or third case possible is the body is submerged inside, density of body is greater than the density of fluid. This is a third case. Now I want you to imagine in which of these cases equilibrium is possible. Now you look at the first case. In this particular case, you will observe that weight of body has to be equal to Fb. A floating body, weight of the body and Fb, both of them are going to be equal. Fine. In this particular case, there is a possibility of equilibrium. Second case, again over here gammas are same and volume displaced is same, so again weight of body has to be equal to Fb. Again over here there is a possibility of equilibrium. Finally, third case, if you see, over here weight of body should be greater than the force of buoyancy. What would happen in this case? Eventually the body would accelerate. If the body is accelerating, then we are not having this condition valid, therefore equilibrium is not possible in the third case. So equilibrium is either possible in the first case or in the second case. That means only in these two cases we can talk about stability. So whenever we talk about stability, please imagine either the body is floating or it is submerged, but it is having same density as the density of fluid. The first category, the first type of body is known as floating body. It is known as floating body. The second category of body, which is submerged but it is not having any acceleration, that type of body is known as neutrally buoyant body. Neutrally buoyant body. We are interested only in these two bodies. The third category of body which we are not interested in, you can call it as accelerating body. Accelerating body. So I hope it is clear to you that our next purpose is going to be talking about stability of these two bodies, either floating body or neutrally buoyant body. This especially the floating body stability conditions are very important for us, because if you look at a ship, a floating vessel like a ship, in that case stability is very important. If a ship feels some kind of disturbance, you would expect it or you would want it to come back to the original equilibrium position. In other words, you would want it to have stable equilibrium. So we will find out the conditions when a floating body and a neutrally buoyant body is going to have any of these equilibrium conditions. Now what are the conditions required for equilibrium to exist? First of all, conditions required for equilibrium to exist. Now again, we are talking only about floating bodies or neutrally submerged body or neutrally buoyant bodies. In these two cases, we have to identify when is equilibrium possible. First thing, if I want net forces to be equal to 0, then the value of Fb has to be equal to W of body. So weight of body and force of buoyancy, both of them have to be equal. Only then equilibrium is possible. Second condition. Before I write second condition, I want you to think of a case. Let us say you are having a particular body fully submerged. Let us say this is a fluid you are having, fully submerged. Let us say in this case, this condition has been satisfied. Fb and weight of body, both of them are equal. But let us say, for argument's sake, let us say that I am having center of gravity somewhere over here, I am having center of buoyancy somewhere over here. What would happen then? In that case, the force W would be falling down from here and the force Fb would be going up from here. Now in this case, even though Fb and W, both of them are same, can you say the body right now is in equilibrium? No. The reason is you are having some eccentricity between them. This is eccentricity. And when you see two equal forces, opposite in nature, separated by eccentricity, they should create a couple. If they create a couple, that means there is a moment developed, therefore this body right now is not in equilibrium. So now the second condition is I should not allow any couple to take place. If I should not allow any couple to take place, that means E should be equal to 0. That implies Fb and weight of body should have same line of action. Same line of action. That means both of them should having a same line of action, or they should pass through same line. In that case, there won't be any eccentricity, therefore there won't be any couple or moment. These two conditions have to be satisfied. Only then equilibrium is possible, only then stability can be discussed. Now let us start. Let us start about the concept of stability for neutrally buoyant bodies. So write down stability of neutrally buoyant bodies. Stability of neutrally buoyant bodies. Let me start with the first case. Imagine this is an interface you have. Interface. You are having a particular body submerged completely inside. The body is neutrally bound. But let us say in this body the concentration of mass is at the bottom. So I am calling this body as bottom heavy body. Bottom heavy body. In the case of bottom heavy body, please imagine this particular case. Center of buoyancy is over here. Center of gravity is over here. This is center of gravity G, let us say. Through center of buoyancy you are having Fb going up. Through center of gravity you are having W going down. W going down. Right now Fb and weight of body, both of them are same. Both of them are having same line of action. Now let us say you give this body a small disturbance, a very small angular tilt you are giving. When I say small, please assume very small. When you give it a small angular tilt, now let us say the body is assuming a new position. The body is assuming a new position. Let us say something like this. This is a new position assumed by the body. Now after having assumed this position, center of buoyancy is over here. Center of gravity, let us say, is over here. Through center of buoyancy you are having Fb going up. Through center of gravity you are having W going down. Now look at this, you are having an eccentricity developed. That means there should be a couple. Your next aim is to identify what kind of couple. Is it trying to restore the initial equilibrium, or is it trying to further disturb the equilibrium? If you see, this couple is trying to restore. It is trying to restore. If it is a restoring couple, then I can say bottom heavy bodies are going to have stable equilibrium. Remember this. Bottom heavy body will always have stable equilibrium if it is a neutrally buoyant body, of course. Second case, let us see. Imagine you are having an interface. You have an interface. You take a body. Let us see. The body is somewhere over here, fully submerged. But let us say the concentration of mass is on the top over here. This is how the mass is concentrated. I call this second category of body as top heavy body. Top heavy body. Now in this top heavy body, if you observe, center of buoyancy is over here, center of gravity is over here, G is over here. Through center of buoyancy, you are having Fb going up. Through center of gravity, you are having W coming down. And let us say you give a small disturbance. Again, initially before giving disturbance, both these conditions were satisfied. After having given some disturbance, let us say the body takes a new position Suppose the concentration of mass is now over here. This is where the mass has got concentrated. Center of buoyancy now is over here. Center of gravity is over here. Center of gravity is over here. Now through center of buoyancy you are going to have Fb going up. Through center of gravity you are having W going down. Again you see an eccentricity has developed. If it has developed, then there should be some couple. Now the question is, what kind of couple is it? Is it a restoring couple or further disturbing couple? If you observe, it is going to rotate in this manner. That means it is a disturbing couple, self-disturbing couple. If it is a self-disturbing couple, I can safely say a top-heavy body is experiencing unstable equilibrium. Unstable equilibrium. Now let us look at a final case. Imagine you are having, let us say, an interface. Final case. Suppose you have submerged a body over here. This body, let us say, is a homogeneous body. This body is a homogeneous body. What do I mean by homogeneous body? It means that the concentration of mass throughout is uniform. If it is throughout uniform, I can say center of buoyancy and center of gravity, both of them are going to coincide at a common point. Let us say B and G are coinciding at a common point. From here I can say there is a force coming down, W. From here itself there is a force coming up, that is Fb. Now you see, both these conditions are satisfied. On top of that, you are having a bonus condition also, and that bonus condition is center of buoyancy and center of gravity, both of them are coinciding. They don't just have a common line of action, they have a common point as well. Now let us say you give a small disturbance. You give a small disturbance, the body has tilted, it has assumed a new position. Let us say it has assumed a new position. Again, after assuming a new position, center of buoyancy and center of gravity, both points are still the same. If they are still the same, then again from here itself you are having a force W coming down, you are having a force Fb going up. There is no eccentricity developed whatsoever. So what would happen now? Will you have any moment at first place? No, you can't have any moment. That means a body has now tilted and it has found a new equilibrium position. It will stay in this position itself. So this kind of equilibrium happens to be neutral equilibrium. It happens to be neutral equilibrium. There is no mathematics involved in analyzing stability of neutrally buoyant bodies. All you have to remember is bottom heavy body, stable equilibrium, top heavy body, unstable, and a homogeneous body, neutral equilibrium. So please not expect questions from this topic frequently. You can have questions, but very rarely from this topic. What is important is stability of floating bodies, which we will be further seeing. Now let us look at the stability of floating bodies. Stability of floating bodies. Very important topic. You can expect a question from here in any examination you write. Now let us start from the basics. Imagine you have an interface. This, let us say, is an interface. You are having a body. Suppose this is a body you have. This body is partially submerged, something like this. Let us say this body has an axis. This is the axis of the body. Now right now I'm not disturbing it at all. I want to analyze the point center of gravity and center of buoyancy. So I can say that center of gravity is somewhere over here, G is somewhere over here, center of buoyancy, let us say, is somewhere over here, B is somewhere over here. Okay, now you see that W and FB, both of them are equal, and apart from that you are also observing that W and FB are having same line of action. So this is a condition I'm having right now. Let us say now I'm tilting it, very slight tilt. Let us say the tilt I'm giving over here is theta tending towards 0 radians. Please remember, it is important to note that theta over here is a very small quantity tending towards 0 radians. But what I'm going to draw is going to be exaggerated for you to understand. So let us say after tilting, the body has taken a new position. Suppose this is a new position the body has assumed after having tilted. Let us say the axis now has taken some position like this. This is the axis we are having. Imagine this is the axis we are having. Now please observe what has happened due to tilt. Previously on either side of the axis the volume displaced was same, but now what has happened, because of tilting there is more volume displaced on this side, right hand side, compared to the volume displaced on the left hand side. What do I mean by this shading? If you look at this part of the shading, I'm basically telling you this part was previously above the interface, whereas this shading part was previously below the interface. Now what has happened? More volume has been displaced towards the right hand side compared to the left hand side. Because of this, what happens is center of buoyancy, which was previously somewhere over here, it will not remain at the same position. This center of buoyancy, it is going to shift towards the right hand side in this particular case. So let us say this is center of buoyancy, center of gravity is where it was previously. This is the previous center of buoyancy. The new center of buoyancy is supposed to shift. Let us say it is shifting to some point over here. If you understand this much, rest of it is very simple. All you have to understand over here is whenever a floating body is given a small angular tilt, the amount of volume displaced on either side is not same. Since it is not same, the center of buoyancy will shift wherever the volume displaced is more. If you see over here the volume displaced is more, so center of buoyancy is shifting over there. Once it shifts, the entire structure of our diagram changes. Now what happens? Through center of buoyancy, the new one, I am going to have FB going up. Please understand, FB is not going up from here, it is going up from the new shifted center of buoyancy, and W is coming down from here. W is coming down from here. So now if you see, I can have a stable equilibrium from here as well. But everything depends on the shift of center of buoyancy. Let us take 3 cases based on the shift of center of buoyancy. Suppose this is the axis of the ship or the floating body. This is the axis, let us say. Initially center of buoyancy is over here. Center of gravity, let us say, is over here. Center of buoyancy has shifted to some point over here, let us say B prime. This new point of center of buoyancy is B prime, let us say. Now I can say that the force of weight is coming down over here. W is coming down over here. FB is going up over here. FB is going up over here. Please tell me what kind of moment is it going to create? Is it creating a restoring moment or further disturbing moment? You can observe it is going to create a moment in anti-clockwise direction. This has to be restoring moment. It is restoring. Let us say R stands for restoring. If it is a restoring couple or restoring moment, then this particular case is for stable equilibrium or unstable equilibrium. I can say this is the case for stable equilibrium. Stable equilibrium. Okay, let us come back to this later. Let us look at the next case. Imagine the axis of the something like this. This is the axis of the ship. Suppose center of buoyancy is somewhere over here. Center of gravity of the ship or the floating body is over here. Let us say center of buoyancy has shifted. It has chosen some position over here. Let us say B prime. Now, from point G, I am having a force in the name of W coming down. From point B prime, I am having a force which is FB, that is going up. Now, please imagine what kind of couple is this going to create? Is it creating clockwise movement or anti-clockwise movement? Very simple, clockwise movement. So let us say it is a clockwise movement. Now please tell me, if it is clockwise movement or clockwise couple, then is it restoring or further disturbing? You can say it is further disturbing. It is trying to further tilt this. So it is a disturbing case. So this is the B bit. I can say this is unstable equilibrium. Unstable equilibrium. Again, let us come back to this later on. Imagine the third case now. Let us say third. This is the axis of the ship. Center of buoyancy over here. Initially, center of gravity over here, point G. Let us say center of buoyancy has shifted, and incidentally it is coming just below center of gravity. Let us say B prime is over here. From this point G, I have the force W coming down. From this point B prime, I have the force FB going up. If you observe, these two forces are again having same line of action, no eccentricity whatsoever. So neither restoring moment nor self-disturbing moment. So this is a third case, let us say, third case I am having, which is of neutral equilibrium. Neutral equilibrium. I hope till here everything is fine. But the problem with all these things is, in examination or when I am working in practice, I can't discuss stability like this. I can't say when B shifts from here to here and all those things. I have to be quantitative, mathematical in my approach. For this purpose, now let me do one thing. Let me extend a vertical line from this B prime. Imagine a vertical line coming up from this B prime. If it keeps coming up, it is going to intersect the axis of the ship somewhere over here. In this case, it is going to intersect the axis of the ship somewhere over here. In this case, come on, please tell me, where is it going to intersect the axis of the ship? In this case, it will intersect the axis of the ship exactly at this point G. Now this point has become very important. Why? Please observe, when this point, I'll name it later on, when this point is above point G, I am having stable equilibrium. When this point is below point G, I am having unstable equilibrium. When that point coinciding with point G, I am having neutral equilibrium. That means the position of that point relative to G can tell me what kind of equilibrium I am having. Now it is time for us to give name to this point. we are going to call it as meta center. This point M over here is known as meta center. So point M is known as meta center. Meta center. After having defined this point meta center, we are going to name two distances as well. First distance is from point B to point M. From point B till point M, this distance is known as metacentric radius. Metacentric radius. Then I'm having a more important length, most important rather, from point G till point M. This distance GM, most famous thing, it is known as metacentric height. Metacentric height. Metacentric height. So now I can establish a relationship between these two. What kind of relationship? Please tell me. GM is equal to BM minus BG. So I can write over here GM is equal to BM minus BG. This equation I can establish. GM is equal to BM minus BG. Now let us come back to each of these cases. The first case over here, stable equilibrium case. Please tell me, if I compare BM and BG, who is greater? Amongst these two things, BM and BG, who is greater? I can say over here BM is greater. When BM is greater than BG, then automatically GM should be greater than 0. And please remember this thing, whenever the metacentric height is positive, you are supposed to have stable equilibrium. So now for stability of floating body, in simple language you can straight away say, whenever the metacentric height is positive, we have stable equilibrium. Come to the second case now. In second case, please compare BM versus BG. Compare BM versus BG. You'll find that in this case, when you compare BM and BG, you will find BM to be less than BG. If BM happens to be less than BG, then GM, metacentric height, has to be less than 0. That means metacentric height is negative. If you have a negative metacentric height, then you are going to have unstable equilibrium. Come to the final case. Before I write, I want you to tell me what is going to happen to GM over here. I hope you have got it. If you compare BM and BG in this case, you will find that BM and BG, both of them happen to be equal. If both of them are equal, then the value of GM has to be equal to 0. So it implies whenever metacentric height is 0, you are having neutral equilibrium. So the underlying concept over here is only based on metacentric height. Metacentric height positive, stable. Metacentric height negative, unstable. Metacentric height 0, neutral equilibrium. This is the concept of stability of floating bodies. Now let us give a formal definition to this particular point. This point, metacenter. How do we formally define metacenter? This point metacenter, how is it defined? This point metacenter is a point about which a floating body experiences simple harmonic oscillations, when given a small angular tilt or a small angular disturbance. Again, by small angular disturbance, I am saying this value of theta is tending towards 0 radians. Please understand, the condition for simple harmonic oscillation will only exist provided this theta is very small. So what is the definition's meaning over here? Please understand this. The body initially is like this. This is a body you are observing. Initially the body is like this. Now the moment you tilt or you give it a small angular tilt, then what is happening? The body is imaginarily getting hinged about this particular point, and it is swinging, it is oscillating. The point about which it is getting imaginarily hinged or it is oscillating about which point, that point is called as metacenter. You would ideally want, please imagine, you would ideally want the center of gravity to be below the hinge or above the hinge. Imagine you have a pendulum. Would you want the center of gravity of the pendulum to be below the hinge or above the hinge? If you are having center of gravity of a pendulum above the hinge, let us say you give a small disturbance, it will collapse. Same thing over here. Right now in this particular case, if I say this is a hinge point, this point M over here is a hinge point and center of gravity is above over here, if you give a small angular displacement, it will collapse. That is why it is unstable. In this particular case, the point of hinge M is over here. Gravity, center of gravity is below. That means what will happen? If you give a small tilt, it will just oscillate. It will not collapse. This is regarding the basics of stability of floating bodies. Now let us talk about metacentric radius first. Metacentric radius given by Bm. Imagine that the front view of a ship is something like this, and the top view is something like this. This, let us say, is the front view, and this, let us say, is the top view of a floating body or a ship, let us say. Let me define some axes. Let us say this axis is x-axis. This axis over here is z-axis. This axis again is x-axis, and this axis over here is y-axis. A ship can oscillate about any of these axes. It can oscillate about x-axis or y-axis or z-axis. You have to identify oscillation about which axis is dangerous, and accordingly you have to design the value of metacentric height of a particular ship. So let us analyze now which axis oscillation is dangerous, which axis oscillation can topple the ship. Let us start with z-axis first of all. Imagine a ship is oscillating about z-axis. Now z-axis oscillation would be such that it is going to tilt the ship, it is going to steer the ship something like this, but it is not overturning the ship. So I can safely say that this axis oscillation is not dangerous for me. Let me do one thing. Let me rank this as number 3. This kind of oscillation is known as yawing effect. Now oscillations about x-axis or y-axis are going to be dangerous for me. Therefore forget about the front view, just imagine the top view. Imagine this is a ship you're having, you're looking from the top view. Now it can oscillate about either x-axis or y-axis. Oscillation about x-axis is going to rock the ship like this. This rocking effect also is not that much dangerous when you compare to oscillations about y-axis over here. So I say if there is oscillation about y-axis, this is second most dangerous, but the most dangerous, sorry, this is second most dangerous about x-axis. The most dangerous has to be about, in this particular case, about y-axis. Now why is it so? If you look about y-axis, the concentration of mass of this particular ship is very close. If it is close, then the inertia with respect to y-axis is going to be less. So a small disturbance can easily topple the ship about y. Whereas with respect to x-axis, the mass is spread far apart. If it is far apart, then the inertia about x-axis is going to be higher. So from here I can say that the most dangerous one is with respect to this axis, which is known as rolling effect. Rolling effect. The second most dangerous is about this axis, which is known as pitching effect. It is known as pitching effect. Third most dangerous is yawing effect. So how to identify which effect is rolling effect? Very simple. All you have to do is you have to look at the top view at the interface. In the top view at the interface, find out the axis about which area moment of inertia is least. That axis will give you rolling effect. Now, after having identified that which axis is giving rolling effect, the next thing is to write the formula for metacentric radius, the value of B. How much is the value of Bm? Bm is equal to I upon V. This is the formula for metacentric radius. Bm is equal to I by V. Very simple formula. What does I over here stand for? What is I over here standing for? I is standing for area moment of inertia. Area moment of inertia. Of which area? The first question is of which area and about which axis? Area moment of inertia of top view in the waterline. In the waterline or interface. In the waterline or interface. That means at this particular level, whatever is the top view, that I have to see. And this area moment of inertia should be taken about. It should be taken about which axis, rolling or pitching? We are designing with respect to rolling effect, therefore about rolling axis. So first of all, we have identified the value I. I is area moment of inertia of the top view in the waterline. We are not looking at this particular top view. This is wrong. We are supposed to look at this top view at the waterline about rolling axis. Next, what is V? V is very simple. V is over here volume of fluid displaced. V is volume of fluid displaced. So this is regarding the concept of metacentric radius. Now let us come to the more important formula, which is metacentric height. Metacentric height. This metacentric height is given by, Gm. Now the question is, what is the formula for Gm? We have already established previously that Gm has to be equal to Bm minus Bg. Gm is equal to Bm minus Bg. Bm over here stands for metacentric radius, as we know. We have identified the formula for Bm. So now let us write down that this Gm over here is equal to I by V minus B. So this is a standard formula for metacentric height. Gm is equal to I by V minus Bg. This is a formula you're supposed to remember. Now, apart from this formula's direct questions, you can have theoretical questions also asked. For those theoretical questions, let me mention some points. First point. The formula for Gm is valid. It is valid only if simple harmonic motion conditions are valid. And we have mentioned already that simple harmonic motion conditions are valid provided theta is extremely small, tending towards 0 radians. So first thing you have to remember, this particular formula, which is a very important formula, it is valid provided theta is tending towards 0 radians. Second thing, again important point. Now what is this Gm depending on? Gm depends on what? Gm depends on, yes, what does Gm depend on? I see over here, first of all, Gm is depending on I. I basically is moment of inertia. That means it is depending on the geometry of the ship. So I can say it is depending on geometry of floating vessel. In our case, it is ship. Geometry of ship. It is depending on volume and Bg. If you do these calculations, you will realize the volume and Bg over here, they will depend on density of fluid and density of the ship. So I can say apart from this, it is depending on densities of fluid and the floating body, that is in our case ship. So please remember, metacentric height of a body depends on its geometry. It depends on density of the ship or the density of body and the density of fluid. Finally, third point. Imagine you have a ship designed or you have a ship manufactured. Once the ship is manufactured, its geometry is fixed. Its density is fixed, let us say. You are letting the ship travel in a particular ocean, so the density of fluid also is fixed. When all these things are fixed, I, V and Bg are also fixed. When all these things are fixed, that means Gm is now becoming a constant. This is a very important point. You have to remember that metacentric height of a particular body, in a particular fluid, is a constant. Metacentric height of a particular body in a particular fluid happens to be a constant. So anywhere in that particular ocean, if theta is tending towards 0 radians only, everywhere you can say the value of Gm remains a constant. This is regarding the standard formula of metacentric height of a body. Now, the next thing we are going to see is known as time period of rolling. Time period of rolling. Questions have appeared from here also in examination. Let me tell you the background of this topic first of all. We have already mentioned that a floating body observes simple harmonic motion whenever it is given a small disturbance. And remember please, small disturbance again means I am repeating this multiple times because it is important that the angle of tilt has to be extremely small, theta tending towards 0 radians. That time the body is observing simple harmonic motion. When it observes simple harmonic motion, it takes a specific amount of time to complete one cycle of oscillation. Let us say this over here is observing simple harmonic motion. After coming back to its original position after completing one cycle, whatever time it has taken, that is called as time period of rolling. Similarly, a floating vessel also takes a specific amount of time, that is called as time period of rolling. We have to identify how much it is. Let's see. Imagine this over here is interface. Let us say a floating body in a tilted position is something like this. A floating body in a tilted position is something like this. Suppose this is the axis of the floating body we have. Let us say this is point G and this over here is point M, meta center. Through point G we are having a force going down. The force is W. Through point M we are having a force going up. The force is Fb. Both these forces are equal, opposite. Eccentricity is there to create a restoring moment. Now first of all, in order to create this position, I have to give some disturbing moment. First thing, I have given some disturbing moment. Disturbing moment. I have to provide some disturbing moment at first place. How much is a disturbing moment? We know the formula for moment from our mechanics. It is equal to I times alpha. I over here stands for mass moment of inertia, not area moment of inertia. I stands for mass moment of inertia. Alpha is angular acceleration initially given. Now let us say disturbing moment was given in this direction initially. After that there is going to be a restoring moment also. So let me say there is something called as restoring moment. Restoring moment. Restoring moment is trying to restore back the original position. How much should this be equal to? It is basically the couple derived from W and F. So I can say it is equal to W multiplied to the lever arm. Please observe the lever arm, important. I drop a vertical from here, I extend a horizontal from here. This distance is the lever arm. This distance is the lever arm. How much is this distance equal to? Let us say this angle which is very small angle is theta. This angle is theta. Now simple trigonometry will tell you that this lever arm over here has to be equal to Gm multiplied to sine theta. So it is equal to Gm multiplied to sine theta. Gm multiplied to sine theta. Now let me go one step further and also mention the directions. Disturbing couple or disturbing moment was given in a clockwise direction. So let us say it was in clockwise direction. Restoring moment is in anti-clockwise direction. So let me mention like this, anti-clockwise direction. So this is the background of what is happening over here. For equilibrium purpose, these two moments should be equal and opposite. They are opposite, they have to be equal now. So what I'll do is, I'll write their equation, but before that, please tell me, if theta is tending to 0 radians, your basic mathematics should tell you that when theta tends towards 0 radians, it implies that the value of sine theta is equal to tan theta is itself equal to theta. provided theta is in radians. It is itself equal to theta. So now in place of sine theta, I'm just going to replace by theta. So what do I have from here? It implies that I times alpha is equal to, since directions are opposite, I write minus W times Gm times theta. W times Gm times theta. This is the value I'm having. Next thing, I can write as I is equal to mass times k square. K, I remember, is radius of gyration. W is equal to m times g. G is acceleration due to gravity. So now I can write from here that m times k square times alpha is equal to minus of mg times gm times theta. Let me cancel off m on either side. I am now left with alpha is equal to minus of g times gm upon k square multiplied to theta. This is a value. This equation is very important. What is this equation telling you? Look at this g. Is it a constant or not? It is a constant. I have mentioned previously that for a given body in a given fluid, as long as theta is very small, metacentric height also is a constant. K also is a constant. If all these things are constant, it basically is saying alpha over here is proportional to, please don't misunderstand, alpha is angular acceleration, this is proportional to minus of theta. Alpha is proportional to minus of theta. What does it mean? It means acceleration proportional to negative of displacement. Acceleration proportional to negative of displacement. Recall from your mechanics, acceleration proportional to negative of displacement is the standard form of simple harmonic motion. This is the standard form of simple harmonic motion. And whatever is that proportionality constant in simple harmonic motion is equal to omega square. It is equal to omega square. Omega square. Now keeping this in mind, I can further say that the value of time period of oscillation has to be equal to 2 pi divided by omega. It is equal to 2 pi by omega. Now if it is equal to 2 pi by omega, it implies that the value of time period of oscillation has to be equal to 2 pi divided by omega, means it is equal to, over here, root over of k square upon g times gm. Very important formula from examination point of view. So the time taken in a floating body to oscillate in a fluid is equal to 2 pi root over of k square upon g times gm. Again, this is valid as long as theta is very small. This is valid as long as theta is very small. Now, after getting this equation, let us discuss further. You can observe from this equation that the time period of oscillation is proportional to 1 by root over of gm. 1 by root over of gm. That means higher the metacentric height, lower the time period of oscillation. That means if metacentric height is high, the time taken is less. So the ship is going to oscillate faster. So I can write over here higher GM implies, or let us say double implies, faster oscillations. Faster oscillations. And faster oscillations are also going to imply uncomfortable journey in a ship. Imagine you're sitting in a ship and the ship is oscillating very fast, very quickly it is oscillating. So automatically the journey is going to become not that much comfortable, is it not? So getting these things in our head, we can decide that if I'm having two ships, let us say one is a passenger ship, and the other is a warship. Now think logically, in which of these cases is the metacentric height supposed to be higher? Now you see, higher value of GM also implies one thing. It also implies higher stability. Now you see, in the case of passenger ship, comfort also is very important. If comfort is important, then what will you do is, you will slightly sacrifice on GM. Okay, you are slightly sacrificing on stability and trying to increase the comfort. Therefore, in the case of passenger ship, the value of GM is going to be slightly less compared to the value of GM in the case of a warship. In warship, comfort is of no importance, stability is of prime importance. Okay, therefore the value of GM in warship has to be much higher. So summary of all these things is, you have to remember this formula and you have to remember this logic, the logic which says that higher stability leads to lower comfort. Very simple, higher stability, lower comfort. You decide what is important where. Now let us look at the formula for metacentric height by another approach. Let us say metacentric height alternate formula. This is again going to employ basic mechanics. Imagine you have an interface. You have a floating body. Let us say this is a floating body you're having. Suppose this is the axis of the floating body. Let us say this floating body is having a weight, suppose W. On top of the floating body over here, you place a very small load, extremely small load. Let us say P. Please understand, P over here is much lesser than W, a very small load. Right now everything is fine. But let us say I displace this P away from the axis by a distance x. Suppose I am displacing P by a distance x away from the axis. Now what happens? Because of this displacement, the ship is going to experience a tilt, a turn. So let us say the ship has assumed a new position. Let us say this is a new position the ship has assumed. Suppose this is the axis of the ship. This is where P is. The distance over here is equal to some distance x. The distance is equal to some distance x. Let us say the angle of tilt is equal to theta. If it is equal to theta, I will complete this triangle. This angle, if it is equal to theta, I can say the horizontal distance is equal to x times cos theta. So let me start writing now. Disturbing moment.
moment is equal to, disturbing moment is equal to P times X into cos theta. This is the value of disturbing moment. Now, there is supposed to be some restoring moment also. So let us find out how much is a restoring moment. Let us say this is a centroid or center of gravity G. This is metacenter M. Through center of gravity, I am having the force W going down. From here, I am having the force FB going up. Again, I complete this triangle. This angle, let us say, is equal to theta. I can now say the distance over here is equal to GM sine theta. So I can say restoring moment is equal to W times GM sine theta. W times GM sine theta. Let us equate both these things. For equilibrium, Px cos theta in magnitude has to be equal to W times GM times sine theta, which further implies that the value of GM has to be equal to P times X cos theta upon W times sine theta. Now observe this thing. You are having sine theta by cos theta in the denominator. So I can now write from here that the value of metacentric height by experimental approach is equal to P times X upon W times tan theta. This is the formula for metacentric height by alternate approach, or this is experimental approach. P over here stands for the load, extra load you are placing. X is a displacement from the axis. W is the weight of the actual body, floating body. Tan theta is tan theta. Now, one more condition over here I have to tell you. If P is significant, with respect to W, that means value of P is not much lesser than W, then what happens? This formula is going to slightly change. In that case, the formula for GM then becomes P into X upon. Now, if P is significant, you should think of the entire weight over here as W plus P. So it is W plus P whole multiplied to tan theta. If the value of P is not very small in comparison to W, then the formula for GM slightly changes. More often than not, you are going to use this formula. The value of P will be much lesser. It will be a fraction, a small fraction of W. Therefore, this formula is more applicable.
Now look at this question, a very simple question. Which of the following pressure units represents the least pressure? The word least is important for us. He has given you 4 options. First option millibar, second one 1 mm of mercury, third is 1 Newton per mm square, fourth is 1 kg force per centimeter square. Whenever these kind of questions appear in examinations, always convert all the units into one common unit. For example, in this question I am going to convert every option into pascals. Let us see. Let us start with A first of all. The first option he has given me is 1 millibar. 1 millibar. Now in this 1 millibar, if you see, milli implies the 10 power minus 3 units and bar implies 10 power 5 Pascal. 10 power 5 Pascal. And we know that this value will come out to be equal to 10 power minus 3 times 10 power 5 is equal to 100. So first option is 100 Pascal. Fine. Second unit now. Second unit he has given us 1 mm of mercury. 1 mm of mercury. I hope all of you remember that 1 mm of mercury is also called as 1 torr. It is also called as 1 torr. I have already mentioned you the value of 1 mm of mercury. Approximate value is 133.33 Pascal. So for sure B is not the correct answer, because 133 Pascal is of course greater than 100 Pascal. Third one now. Third unit he has mentioned is 1 Newton per mm square. 1 Newton per mm square commonly is called as 1 MPa. Very high unit. 1 MPa is equal to 10 power 6 Pascal. This also cannot be the correct answer. Finally, I am having 1 kg force per centimeter square. 1 kg force per centimeter square. How much should this be equal to? 1 kg force is equal to 9.81 newtons per 1 centimeter square is 10 power minus 4 meters square. So if you calculate this value, it will come out to be equal to 9.81 times 10 power 4 Newton per meter square, that is equal to Pascal. If you see, even this value is much greater than the first option. Therefore, even this cannot be the answer. Therefore, the least value over here is 1 millibar. If he asks you what is the highest value, then the highest value would be this one, 1 Newton per mm square. Very simple question. You can expect this question in IES kind of examination and also in the case of GATE examination, but that would be very simple GATE examination question for 1 mark. Now this question is saying that the standard atmospheric pressure is 760 mm of mercury. Fine, we know this thing. 760 mm of mercury is also called as 1 atmosphere. That is a standard value. Fine. At a particular place, the barometric reading is 710 mm of mercury. Fine. At this site, absolute pressure is 360 mm of mercury. Okay, he has given us P0, that is local atmospheric pressure. He has also given us the absolute pressure. The pressure gauge reading in mm of mercury is equal to how much? He is asking us what is the gauge value. So let us write the given data first of all. Given data. He has mentioned that the value of standard pressure, standard atmospheric pressure is equal to, it is equal to 760 mm of mercury. If he does not mention this thing, still we already have an idea of this. This is the value, fine. Then it says that the value of local atmospheric pressure, P naught, P naught is equal to 710 mm of mercury. The absolute pressure, let us say P absolute over here, is equal to 360 mm of mercury. Fine. What is he asking from us? Gauge pressure. Gauge pressure is equal to how much? This is a question. Very simple question. Now, in the question, I can use the equation P absolute is equal to P naught plus or minus P gauge. We have seen this equation already. When to use plus over here, when to use minus? That is a question. You are going to use plus. You are going to use plus in this equation if the value of P naught is lesser than the value of P absolute. If P naught is lesser than P absolute. And you are going to use minus over here, minus if the value of P naught is greater than P absolute. And remember, in this particular case, the gauge pressure is going to be negative gauge pressure or vacuum gauge pressure. So now in this case, I see that the value of P naught is greater than the value of P absolute, so I'll use minus. If I use minus, then it implies that 360 mm is equal to 710 minus P gauge, which further implies that the value of P gauge is equal to 710 minus 360 mm of mercury, but in vacuum, and this value comes out to be equal to 350 mm of mercury in vacuum, or you can say suction pressure. Now if you look at the options, first option 400 mm of mercury in vacuum, wrong. Second option 350 mm of mercury in vacuum, that would be correct option. Rest to say 360 mm in vacuum, and then none of the above. The answer over here is option B. B is the correct option. Now this question is saying that two tanks A and B with the same height are filled with water. The volume of tank A is 10 times the volume of tank B. What can you say regarding the pressures at A and B at the bottom of the tank A and B respectively? He has a difference in volume, same height, same fluid, and then he is talking about the pressure difference. Let us say this is some tank A, there is some tank B over here. The volume of tank A is greater. Let us say this is some tank B. Both of them are having same height. Let us say volume in A is equal to 10 times volume in B. Height at the bottom of A is equal to height at the bottom of B. The property of fluid in both these places is gamma. The question is, what is the pressure at the bottom going to be? If you look at pressure at point A, it has to be equal to gamma times HA. Pressure at point B
has to be equal to gamma times HB, gamma times HB. Now we know that gamma is same, HA and HB are also same, therefore the pressure at the bottom in both these tanks has to be same. Now this gives you a very important result, that the pressure is not a function of volume. Please remember this thing, pressure does not depend on volume. It is not a function of volume. It depends on the property of fluid and the depth. Imagine if you are having a test tube, extremely thin test tube, and same height, even at the bottom of that test tube also would have the same value of pressure, because pressure does not depend on volume, it only depends on height. So over here the answer is supposed to be option C. Option C. Now this question is a typical IES question. It is actually a previous IES question only. The question says match list 1, that is features of a manometer, with list 2, that is a type of manometer, and select the correct code that is given over here. Now list 1 is saying, now whenever these kind of questions come, read the entire question once and then again read it bit by bit. List 1 is saying open-ended manometer for positive pressure, B is open-ended manometer for negative pressure, C is for measuring pressure in liquids or gases, D is for measuring pressure in liquids alone. Now let us see. A, open-ended manometer for positive pressure. If you see in the options given below, that is list 2 options, only 2 manometers are open-ended. So open-ended manometer, if I mention over here, open-ended manometer, I am having 1 and 2, not 2 rather, I am having 1 and 4. 1 and 4. 1 and 4 are open-ended manometers. Now amongst these 2 manometers, 1 and 4, which one is suitable for measuring positive pressure? If you look in the case of manometer 1, the meniscus of the fluid is below the bulb. The bulb is somewhere over here, meniscus is somewhere over here. That means you are traveling up now. If you keep traveling up, as you know, the pressure keeps on decreasing. So now what happens over here? Over here you are having 0 gauge pressure, and as you go up, the pressure is falling down below 0 gauge pressure. That means this has to be negative gauge pressure. Come to the fourth one. In the fourth one, if you observe, meniscus is on top, the bulb is below. So you are going to travel down. As you travel down, the pressure is supposed to increase. So from here I can say open-ended manometer for positive pressure, this one has to be manometer 4. And open-ended manometer for measuring negative gauge pressure, this one has to be manometer 1. Fine, I am having A is for 4, B is for 1. Now come to the C and D bit. C bit says for measuring pressure in liquids or gases. Liquids or gases. If you see, there are 2 manometers left now, 2 and 3. The second manometer, if you observe, this manometer is an inverted U-tube manometer, and he has mentioned one very important point in this inverted U-tube manometer, that you are having SM lesser than SF. That is, a manometric fluid is lighter compared to the working fluid. If manometric fluid is lighter, imagine this particular case. If let us say the working fluid is a gas, so manometric fluid would also have to be a gas, because density is supposed to be lesser for manometric fluid over here. So imagine you are having a gas in the bulb and you are having over here also gas. Gas and gas can never create an interface. If they never create an interface, then this particular manometer is not suitable for measuring pressure in gases.
if it is not suitable for measuring pressure in gases, then this will go for option D. So D is for 2. D is for 2. Now what is left for measuring pressure in liquids or gases? Now if you look over here in the third option, in this case you can measure pressure for both liquids as well as gases. Imagine you are having over here in the bulbs liquids, then also manometric fluid can be a liquid and create an interface. If you are having gases, again the manometric fluid can be a liquid and create an interface. So option 3 goes for C. So let us see what code is correct over here. A for 4. The moment I see A for 4, I only see one option, that is option B. I am having 4132. If you see over here, 4132. So answer over here is option B. Now you have to find out over here the pressure at point P in terms of head of oil. Here seeing a pressure point P is connected to U-tube manometer. The gauge pressure at P in terms of meters of oil is how much? The point P over here is located inside this bulb. So inside the bulb you are having a point P. You have to find out how much is the pressure at that particular point in terms of head of working fluid. Now how to find this out? Let us start with the end that is exposed to atmosphere. We know that when anything is exposed to atmosphere, the gauge pressure over there has to be equal to 0. So over there the gauge pressure is 0, fine. Then you are coming down. As you come down, you are going to add. So let us say plus. I am adding over here. Now I am moving down with mercury and with a height of 0.1 meters. So gamma of mercury multiplied to 0.1 meters. Gamma of mercury multiplied to 0.1 meters. After that, I am supposed to shift towards the left. Now you see, I am shifting towards the left. The next point, that is this point, also is supposed to have same pressure. Then from there I am moving down by a distance of 60 centimeters. So therefore plus gamma of oil multiplied to 60 centimeters, that is 0.6, is equal to the pressure at point. It is equal to the pressure at point P. Fine. Now he wants the value in terms of head of oil. Therefore head of oil is supposed to be equal to gamma of mercury multiplied to 0.1 plus gamma of oil multiplied to 0.6 whole divided by gamma of oil. That is supposed to be equal to. Now gamma of mercury by gamma of oil I can write as S of mercury divided by S of oil. This is multiplied to 0.1 plus gamma of oil by gamma of oil we know is equal to 1. So therefore 0.6 over here. That is equal to S of mercury, it is given, it is equal to 13.6. S of oil, it is given in the question, it is equal to 0.85 multiplied to 0.1 plus 0.6. This value, if you calculate, will come out to be, this value is equal to 1.6. Add to it 0.6. This is equal to 2.2 meters of oil. So it is as if you are having a 2.2 meters height column of oil on top of point P. This is the answer for the question. Now this question is on inverted U-tube differential manometer. The question says the pressure difference between points M and point N for the manometer shown in the figure in centimeters of oil is how much? So the question is, if you simplify, you can write like this: Pm minus Pn in terms of centimeter of oil. Centimeter of oil is how much? Now let us start with Pm. Pm. At point M, the pressure is equal to Pm. From point M, I am going up. If I go up, I am supposed to subtract. I am going up with water, therefore gamma of water. I am going up with a height equal to 6 centimeter plus 3 centimeter of water. If I write in centimeters, I have 9 centimeters over here. I have reached a particular point. Same pressure is applicable on the other limb also at the same level because the fluid is continuous. After coming to the other side of the limb, I am coming down. If I come down, I am supposed to add, let us say plus. I am coming down with gamma of oil. So gamma of oil multiplied to. I am coming down with a height of 3 centimeters. 3 centimeters, fine. Then I am coming down again. So therefore plus. I am coming down with water this time. So therefore gamma of water multiplied to how much height? Now you see 6 centimeters plus 12 centimeters. That should give you 18 centimeters. I have reached the point N, therefore this should be the pressure at point N. Now I want Pm minus Pn. This implies Pm minus Pn is equal to, if you shift these things to the other side, you are going to have minus of gamma of water multiplied to 9 centimeters minus of gamma of oil multiplied to 3 centimeters. Fine. Now I want the value of Pm minus Pn in terms of centimeter of oil. So I have to do over here, this implies head of oil equal to Pm minus Pn divided by gamma of oil, that is equal to minus 9 multiplied to S of water upon S of oil minus 3 centimeters, that is equal to minus 9 multiplied to S of water we know is equal to 1. Now S of oil, if you see he has mentioned it is equal to 0.83 minus 3. If you calculate this value, it comes out to be equal to minus 13.84 centimeters of oil. So the answer in this case is option B. Now this question is a previous gate question for production engineering. The question says a manometer is used for pressure measurement in a closed tank. The three fluids F1, F2 and F3. There are three fluids over here. You can see this fluid over here is F1. The fluid over here is F2 and the fluid inside the tank over here, that is F3. The fluids F1, F2 and F3 have specific weights. Now this is not G, it is gamma. So this is having a specific weight of gamma. This has a specific weight of 2 gamma and this has a specific weight of 0.5 gamma. So please read it as gamma, 2 gamma and 0.5 gamma respectively. The schematic arrangement with manometric readings and other dimensions are shown in the figure. The lengths and dimensions are shown in the figure. In order to ensure zero gauge pressure in the tank at the mid level, that is at this particular level in the tank, inside the tank, if I want to maintain zero gauge pressure, then what should the value of H be equal to? How much should the value of H be? How to start this question? You see, it is already mentioned in the last statement that the pressure at the midpoint in the tank is supposed to be equal to 0. So let us mention straight away that point as some point A. Let us mention this point over here as some point A. The pressure at that particular point is equal to 0. So I'll start with pressure at point A is equal to 0. Now we have to write an equation for PA, equate it to 0. The only unknown in that equation will come out to be that H value. From there we can find out. Let us start from here, from the open end. If I start from the open end, I know that the pressure over here is already equal to 0. From there, if I keep moving down, I am supposed to add plus. Now I am moving down with a property gamma, and I am moving down up to a height of 1.2 meters. 1.2 meters, fine. I have reached till here. Reaching here is as good as reaching the corresponding level over here. So I am here right now. From here I am moving up. I am moving up, therefore negative. I am moving up with a property of 2 gamma. So 2 gamma over here multiplied 2. I am moving up by a height of 0.2 meters. 0.2 meters, fine. I have reached till here. Reached till here. Again I am moving up now. So therefore minus. I am moving up with a property of 0.5 gamma. So 0.5 gamma multiplied 2. I am moving up with a height of 0.6 meters plus h by 2. 0.6 meters plus h by 2. I have reached the point A, and at that particular point we know the pressure is equal to 0. So I have this established. Let us cancel gamma throughout. If I cancel gamma throughout, I am now left with 1.2 minus 0.4 minus 0.3 plus h by 4 is equal to 0. From here, or rather minus, this is supposed to be minus h by 4 is equal to 0. This is minus. Now 1.2 minus 0.4 is 0.8, minus 0.3 is 0.5. So 0.5 meters is equal to h by 4. From here it implies that the value of h has to be equal to 4 times 0.5, that is equal to 2 meters. So the pressure at point A is 0, provided the value of h is equal to 2 meters. This is our answer. The question is now saying a circular plate of 2 meters diameter is immersed vertically in water. The upper edge is 1 meter below the free surface of water. Location of center of pressure in meters is how much? So let us imagine that this is an interface we have. This is an interface. You are having a circular plate. A circular plate, let us say. The diameter of this plate is equal to 2 meters. This location is equal to 1 meter. If let us say this is a center, then this location is another 1 meter. From here, first thing I can mention is the value of h bar is equal to 2 meters. H bar is equal to 2 meters. What next? We want over here the value of h star. Location of center of pressure means the value of h star. H star is equal to how much? Now let us write the formula for H star. H star we know is equal to H bar plus I sine square theta upon area times H bar. Area times H bar. If you look, it is vertically immersed. If it is vertically immersed, sine square theta over here has to be equal to 1. The reason being, theta value over here is 90 degrees. Next, H bar is known to us. Let us calculate the value of area and I. Let us write area now. Area for a circular plate has to be equal to pi by 4 d square. That is equal to pi by 4. Diameter over here is equal to 2 centimeters, or 2 meters rather, not 2 centimeters, 2 meters. Therefore 2 square. From here I can mention area is equal to pi meter square. I, area moment of inertia, it is equal to pi by 64 times d power 4. Pi by 64 d power 4, that is equal to pi by 64 times, again diameter is 2, so 2 power 4. 2 power 4 we know is equal to 16. 16 by 64 means the value of I has to be equal to pi by 4 meter per 4. Now all I have to do is assemble these two values. Assemble these two values in the equation. I am continuing over here. So the value of H star now comes out to be equal to H bar we know is 2 plus I is equal to pi by 4 sine square theta we have established it is equal to 1. Area over here is equal to pi. H bar is again equal to 2. So pi and pi cancel out. So this over here is equal to 2 plus 1 by 8. The value of 1 by 8 is 0.125. Therefore, the value of H star has to be equal to 2.125 meters. This is the answer for the question. 2.125 meters. Now this question is saying a circular annular plate bonded by two concentric circles of diameters 1.2 meter and 0.8 meter is immersed in water with its plane making an angle of 45 degrees with respect to horizontal. If the center of the circles is 1.625 meters below the free surface, then the total pressure force, that is the hydrostatic force, on one side of the plate in kilonewton is how much? Let us see how to solve this kind of question. First of all, what do you mean by annular plate? Annular plate. Annular plate basically means a plate which is having a centroidal portion, a portion in the center that is removed. So it is creating an annulus in between. So let us say it is something like this. You are having a plate, then you have a centroidal portion removed. The mass is only over here, something like a ring. So this is the annular plate you are having. Now he has mentioned for this annular plate, the value of H bar is equal to 1.625 meters. This is given. He has also mentioned that D outer is equal to 1.2 meters and D inner is equal to 0.8 meters. Okay. Further, he says that this is submerged in water. It is submerged in water. Therefore, the value of gamma of fluid over here is 9.81
kilonewton per meter cube. This is a given data. What do we have to find out? We have to find the hydrostatic force is equal to how much? We know that the formula for hydrostatic force is gamma times area times h bar. This is the formula. We already have the value of gamma, we already have the value of h bar. All we have to find out is the value of area. How to get the value of area? Now you see, you are having an annular plate. The area for annular plate is supposed to be equal to pi by 4 d outer square minus d inner square. This is the area of the annular plate. That is equal to pi by 4 times d outer over here is 1.2. So 1.2 square minus 0.8 square. 1.2 square minus 0.8 square is supposed to be equal to 0.8, or 0.8 by 4 is equal to 0.2. Therefore, this value will be equal to 0.2 pi meter square. Once I have this value, I can now say the value of force, which is equal to gamma times area times h bar, is equal to 9.81 times pi into 0.2 times h bar is 1.625 meters. Now this is in kilonewtons. If you calculate this value, the value of force approximately comes around 10 kilonewton. So this over here is our answer. Hydrostatic force acting on one side is approximately equal to 10 kilonewtons. A rectangular tank full to the top has its length, breadth and height in the ratio of 2:1:2. The ratio of hydrostatic force at the bottom of the tank to that at the largest vertical wall is how much? Simple question. Let us first of all construct a small diagram representing the tank. Let us say this, let us say, is a rectangular tank you are having. Rectangular tank. He has mentioned you that length is to breadth is to height, or depth is equal to 2:1:2. So this, let us say, is length, this let us say is breadth, this let us say is height. Now he is asking you what is the ratio of hydrostatic force at the bottom. So the first area we are looking at is this area. So on this, let us say you are having some force F1 versus the hydrostatic force on the largest vertical wall. Now there are two vertical walls. One vertical wall is B times H, one vertical wall is L times H. Now it is evident L times H will have a larger area. So let us say we are looking over here for second vertical wall being this thing. Let us say over here we are having some force F2. So the question is F1 upon F2 is how much? This is a question. Let us see start. Whenever these kind of ratios are given, I personally prefer taking some constant and establishing the values. For example, L is, let us say, equal to 2A. That makes B equal to A and makes H again equal to
2a. Fine. Now the value of force F1 has to be equal to gamma into area 1 multiplied to H1 bar, that is equal to gamma times. Now area, the area of this bottom portion is equal to L times B. L times B is the area. H1 bar is the centroid of this particular area. The centroid of this area is completely at the depth H, so that is multiplied to H. If I put in these values, I am supposed to get the value of F1 is equal to gamma times L is equal to 2a times B is equal to A times 2a. So the value of force F1 is equal to 4 gamma A cube. Let us say this is some equation number 1. Coming to the next one, that is F2. The value of F2 has to be equal to gamma into A2 into H2 bar that is equal to gamma times. Now area for this particular rectangle is equal to L times H. So L times H multiplied to. Now where is its center? This is a vertical rectangle. Its center is supposed to be at half the distance from the top, that is equal to H by 2. So multiplied to H by 2. So the value of F2 comes out to be equal to gamma times L is 2a, H is again 2a, H again is 2a upon 2. So if I cancel off 2 and 2, I get from here the value of F2 is equal to 4 gamma A cube. This, let us say, is equation number 2. Now we want over here F1 upon F2. That has to be equal to 4 gamma A cube upon 4 gamma A cube. Therefore this value is equal to 1. So the answer for our question is F1 upon F2 is equal to 1. Now this question is regarding the hydrostatic forces on curved surfaces. The question says, one end of a two-dimensional water tank has the shape of a quarter circle of radius 2 meters filled with water up to the radial depth. Fine. The vertical component of hydrostatic force per meter length on the curved surface in kilonewtons is equal to x pi. This over here is x pi. Please read it as x pi. Acceleration due to gravity is equal to 10 meters per second square. Then the numerical value of x is equal to how much? So the question asked over here is, what is the value of x over here equal to? Let us now construct a diagram to understand this. Let us say you are having a tank. The tank is having one end in the form of a quarter circle, something like this. And let us say the fluid is filled up till here. You are having a fluid filled up till here. So let us mention this as some mn. Mn is a quarter circle. Okay. This quarter circle would have its radius over its center over here. Let us say this is O. This is the radius r. The value of r is equal to 2 meters.
r is equal to 2 meters. The value of g is given as 10 meters per second square. And the value of vertical component of force, let us say Fv is the vertical component of force, it is equal to x times pi. This value is x times pi. Units are kilonewton. The width perpendicular to your screen, let us say the width is small w. We have to find per unit width, therefore let us say 1 meter is the width perpendicular to the screen. Now this much data is given to us. We are supposed to find out the value of x is equal to how much? X is equal to how much? How do we find this out? We know the formula for vertical component of force has to be equal to gamma times volume. And I hope you remember the volume is supposed to be measured from the interface till the curved surface regardless of the presence of fluid. So let us say over here this volume has to be considered. This volume has to be considered. How much is this volume equal to? This is gamma times volume over here is 1/4 of a circle, that is pi r square divided by 4. I want the answer in kilonewtons, so I'll take gamma also in kilonewtons. For water we know that if G is equal to 10, gamma is equal to 10 multiplied to pi times R over here is equal to 2. 2 square by 4. 2 square cancels with 4. Therefore, the value of Fv over here is equal to 10 pi. Compare 10 pi with x pi kilonewtons. This further implies that the value of x has to be equal to 10. So for this question the answer is 10 units. Now this question is again on hydrostatic forces on curved surfaces. The question says the net horizontal hydrostatic force due to fluid of weight density gamma on a cylindrical body of diameter capital D as shown per unit length of the cylinder is how much? So on one side you are having the fluid up till the top, on the other side you are having the fluid up till half, that is a central. Now let us say over here having a force, horizontal force F1, and over here I am having a horizontal force, let us say this force equal to F2. So I can say that the net horizontal force summation of Fx has to be equal to F1 minus F2. This is a value. Let us start with F1 first of all. F1 has to be equal to how much? We know that the horizontal thrust in the case of curved surface is equal to gamma times area into h bar projected, let us say projected 1, that is equal to gamma times. Now if you look from that side, how much is the area of projection you are going to see? You would be seeing a rectangle with a height equal to capital D and length perpendicular equal to 1. So therefore D times 1 is the area multiplied to the center of that rectangle from the interface is supposed to be equal to D by 2 distance away. So therefore the value of F1 is supposed to be equal to gamma D square divided by 2. Gamma D square divided by 2. Let me save this as equation 1. Now coming to F2. F2 is equal to again gamma multiplied to area times h bar of projected area 2, that is equal to gamma times area. Now this should be easy for you. What is the area you see from this side? It is equal to d by 2 multiplied to 1 unit width. Therefore, d by 2 multiplied to 1, this is the area. And its center from its interface is equal to d by 4. So this value comes out to be equal to gamma d square by 8. This is the value of force F2. So I have F1 as well as F2. I want the net hydrostatic force in the horizontal direction, which we know is F1 minus F2. Therefore, this has to be equal to gamma d square by 2 minus gamma d square by 8. This value comes out to be equal to 3 gamma d square divided by 8. This is the value of net horizontal thrust. Sigma Fx is equal to 3 gamma d square by 8. In which direction is this force? Now since F1 is dominating, therefore this should be in the direction of F1, that is towards the right hand side. The answer over here is supposed to be option D, 3 gamma d square divided by 8. This question is an assertion reasoning question. Assertion reasoning questions are commonly asked in IAS examinations, very rare in GATE examinations. Now, before we start this question, let me briefly discuss to you how to approach an assertion reasoning question. Assertion reasoning question is going to have two statements, statement 1 and statement 2. Apart from these two statements, you are having one more thing known as reasoning effect. Means, is statement 1 a reason, is statement 2 a proper reason for statement 1? Now let us say if you find statement 1 to be correct, if you find statement 2 also to be correct, and you find that there is a reasoning effect, that means statement 2 is a proper reason for statement 1, then the answer over here is A. Answer is A. If you find statement 1 is correct, and if you find statement 2 is also correct, but there is no reasoning effect, that means statement 2 is not a proper reason for statement 1, then the answer over here is B. Answer is B then. If you see that statement 1 is correct and statement 2 is wrong, statement 2 is wrong, there is no need for checking the reasoning now. In this case, the answer is supposed to be C. If you find that statement 1 itself is wrong and statement 2 is correct, then the answer over here is supposed to be D. So whenever you come across assertion reasoning question, establish some kind of a table like this and tick whatever is correct, and if anything is wrong, you put a cross, you'll get the answer correspondingly. Let us look at this question now. The question is saying, statement 1 says, at great depth the vertical distance between the center of pressure and center of area of immersed surface becomes negligible. Let us analyze this by writing an equation. The vertical distance between center of pressure and center of area. What is the meaning of this thing? Distance between center of pressure and center of area is equal to h star minus h bar. This is the thing. We know that the value of h star minus h bar is equal to I sine square theta upon area times h bar. This is the value of h star minus h bar. Now he is saying at greater depth. Greater depth means the value of h bar is increasing. If h bar increases, you look at this value. I is not increasing, I is remaining same. Area is not increasing, area is remaining same. Sine square theta is not increasing, it is remaining same. Only thing is increasing is this value. That means if h bar increases, it implies that the value of h star minus h bar is supposed to decrease. The denominator is increasing, therefore the entire fraction is supposed to decrease. Therefore statement 1 over here is a correct statement. So if I mention a table like this, this is for 1, this is for 2, this is for reasoning, I can say that statement 1 is a correct statement. Fine. Now before going to statement 2, let us again come back to this. We have mentioned already that as you keep on increasing the depth of submergence, center of pressure is moving closer to centroid of the body or the centroid of the plate. If you remember that, straight away you can say that this statement is correct. There is no need to do all this analysis. Now let us go to statement 2. The depth of center of pressure of any immersed surface is independent of density of liquid. Now again let us analyze this by writing the equation. Depth of center of pressure, that means h star. He says it is independent of density of fluid. Let us check. What is the formula of star? It is h bar plus I sine square theta upon area times h bar. Now please tell me, do you find that h star, is it a function of density of fluid anywhere? No. If you see, nowhere in this equation I am having density, therefore h star is not a function of density. If that is true, then the statement 2 also is true. So I can say over here, statement 2 also is true. Now check whether you are having a reasoning effect. Is this condition a reason for this to happen? No. This nowhere is related to this. So now I can say that statement 2 is not a reason for statement 1. If this entire thing is happening, I can say the answer in this case is supposed to be option B. Option B is correct over here. This is how you are supposed to approach assertion reasoning questions. Please remember, we as engineers understand diagrams and equations more than statements. So whenever these kind of statements are given, either try to convert them into some equations like this or try to convert them into some diagrams. They'll be more helpful in analyzing than analyzing the statements. Now the question says a wooden block having specific gravity equal to 0.64 of rectangular section 4 meters long, 1.25 meters breadth and 2 meters depth floats horizontally in a vessel consisting of a liquid of mass density 1025 kg per meter cube. 1025 kg per meter cube is generally the density of seawater. So probably the fluid is seawater over here. The question continues, says that the depth of block under the liquid and the volume of water displaced would be equal to how much? Very simple question. Now this question is on a prismatic body. This question is on a prismatic body. So we are going to get a result for this particular question. If it is possible, remember this result. That result will be applicable for any prismatic body when it is floating. So let me draw a rough diagram. Imagine this is an interface we have. This is an interface. There is a body which is floating. Let us say the front view of the body is something like this. This body is floating. This body has a cross section of capital A. It has a cross section of capital A. If I I get in this particular case, the value of capital A is equal to 4 meters times 1.25 meters, that is equal to 5 meters square. This is the value of capital A. Next thing, this body is having a depth of 2 meters. So let us say this is capital H. The value of capital H in this case is equal to 2 meters. Further, this body is having a depth submerged. Let us say it is equal to small h. The question is, what is the value of this small h? I hope the diagram is clear to you and it is explaining the question quite well. So what is the value of small h? This is the first question. Apart from that, the second question is volume of fluid that has been displaced. That is going to be cross-section area multiplied to small h. So getting the value of small h is sufficient to get the value of volume also. So how do we start this thing? Now whenever you see floating bodies, always think of equilibrium. So right now this entire body is in equilibrium. So what I can do is, I can say that the value of weight of the body has to be equal to Fb. Weight of the body has to be equal to Fb. What is the formula for weight of the body? It is equal to gamma of body multiplied to volume of body. Fb is equal to gamma of fluid multiplied to volume of fluid. From here I can say volume of fluid displaced is equal to gamma of body by gamma of fluid, or you can say Sb upon Sf multiplied to volume of body. This condition is valid for both prismatic or non-prismatic floating bodies. So if it is possible, remember this result. Now we want over here the value of small h. If it is a prismatic system, this entire system is prismatic, so I can say area times small h. Volume of fluid displaced is equal to cross-section area times small h has to be equal to Sb upon Sf times volume of the body is equal to cross-section area times capital H. I can cancel off cross-section area on both sides. I am now left with small h is equal to Sb upon Sf into capital H, which further implies the value of small h is equal to Sb upon Sf. Now if you look in this particular case, in this case Sb is equal to 0.64 and Sf is equal to 1.025. So put in these values. So 0.64 upon 1.025 multiplied to capital H over here is equal to 2 meters. If you calculate this, the value of H comes out to be equal to 1.248 meters approximately. So this is a result which is valid only for prismatic bodies, and this is our first answer. Now if I want to find out the value of volume of fluid displaced, so I can say volume of fluid displaced is equal to Sb upon Sf is 0.64 upon 1.025 multiplied to volume of body is equal to 5 times 2. If you calculate this value approximately comes out to be equal to 6.24 meter cube. This is the volume of fluid that has been displaced. volume of fluid that has been displaced. So in this particular case, the answer is supposed to be option D. Option D is the answer. It is given that a solid sphere and a hollow cube have the same outer surface area. The ratio of buoyancy force on the sphere to that on the cube when they are fully submerged in a liquid is given by. Now this question, as you keep doing, you will realize this question is a basic mathematical question. The question first of all says that the surface area of a cube is equal to surface area of a sphere. And both this cube and sphere are both completely submerged inside a fluid. So let us first of all write down the equations for surface area. Surface area of a cube is equal to 6 times a square. A over here, let us say, is the edge length of a cube. Surface area of a sphere is equal to 4 pi r square. It is equal to 4 pi r square. Now from here I can say, let us convert one term into other term. I can say the value of A is equal to 4 pi by 6 under root of times r, that is equal to A is equal to r root over of 2 pi by 3. Save this as an equation. Let us say equation 1. Now let us come to the second part of the question. The question is ratio of buoyancy force when both of them are submerged inside. So we want over here FB acting on sphere FB acting on cube is equal to how much? How much is this value equal to? Now we know that the ratio of FB is supposed to be equal to gamma of fluid multiplied to volume of fluid displaced. If it is completely submerged, then I can say volume of sphere over here and gamma of fluid multiplied to volume of cube. So now the value of gamma cancels out. So basically the question is asking us the ratio of volumes is how much if the surface areas are equal. That is why I said this question will come down to basic mathematics. And this is one of the previous GATE examination questions. You will come across many GATE examination questions where you will require more mathematics than your technical subject. Let us continue now. I can now say that FB on sphere by FB on cube has to be equal to volume of sphere. Volume of sphere is equal to how much? 4 pi by 3 times r cube. Volume of cube is equal to a cube. So this comes out to be equal to 4 pi by 3 times r cube upon. Now what I am doing is, I am taking this value of a, which is in terms of r, and putting over here. It would be equal to r cube multiplied to 2 pi by 3 multiplied to square root of 2 pi by 3. Let us cancel what all can be cancelled off. R cube and r cube cancels off. Pi by 3 cancels off. 2 cancels off to give you a 2 over there. So therefore this value comes out to be equal to, if I put this 2 under square root, I am going to get 4 times 3 upon 2 pi. So this gives me root over of 6 by pi. This is the value of force of buoyancy on sphere upon force of buoyancy on cube. Root over of 6 by pi. So the answer, if you compare over here, has to be option C, root over of 6 by pi. A 10 centimeter steel cube, steel having specific gravity 7.6, is submerged fully in a two-layered fluid. The bottom layer being mercury, specific gravity is 13.6, and the top layer being water. The height of the cube above the liquid interface in centimeter is how much? So this is a question of flotation of a body in two fluids. So let us say you are having two fluids. This is the interface between two fluids. You are having a steel cube over here. You are having a steel cube over here. This is water. This is mercury. He says that the entire height is 10 centimeters. Entire height is 10 centimeters. The height of the cube above the liquid interface, that is this height, let us say it is equal to small h. It is equal to how much? I am considering this as a capital H value. This height small h is equal to how much? He has given you specific gravities. The specific gravity over here is equal to 1. Over here it is equal to 13.6. Specific gravity over here is equal to 7.6. Let us start now. This question is a basic question on equilibrium. So draw the free body diagram and establish equilibrium. So let us say this is the body we have. This body is going to have, first of all, weight coming down. Since it is displacing two fluids, let us say this is fluid 1 and this is fluid 2. Since it is displacing two fluids, it is supposed to have two forces of buoyancy. Let us say this is FB1 and this over here is FB2, two forces of buoyancy. By equilibrium, I can write that the value of W has to be equal to FB1 plus FB2. W should be equal to FB1 plus FB2. Now, that implies gamma of steel multiplied to volume of steel should be equal to gamma of water multiplied to volume of water displaced plus gamma of mercury multiplied to volume of mercury displaced. This is the equation we have. I can write this equation as S of steel multiplied to gamma of water. Volume of steel is equal to cross section area multiplied to the entire height of steel is equal to 10 centimeters. Must be equal to. This is gamma of water. I am representing by gamma itself. Cross section area, volume is cross section area multiplied to small h plus S of mercury multiplied to gamma of water multiplied to volume is cross section area into 10 minus h. Now if you see what all things can be cancelled, gamma times A throughout can be cancelled. If I cancel this off, the equation now becomes S of steel is 7.6. So 7.6 into 10 is equal to H plus 13.6 into 10 minus h. So therefore I am having 76 is equal to h plus 136 minus 13.6 h. I have taken this value in centimeters, therefore h also will be in centimeters. This implies 12.6 h is equal to 136 minus 76 is 60, implies h is equal to 60 upon 12.6 centimeters. From here we get the value of h is equal to 4.76 centimeters. So the portion of cube above the liquid interface is equal to 4.76 centimeters. A spherical balloon 1.6 meters diameter is completely immersed in water and chained to the bottom. If the chain has a tension induced of 10 kilonewtons, the weight of the balloon in kilonewton should be how much? Let us say you are having some tank. In this tank, let us say there is some fluid. That fluid is water. This is water. You have a balloon which is spherical in shape, a spherical balloon. It is connected to a chain over here, a chain over here. The diameter of this balloon is given as 1.6 meters. Also mentioned that the tension over here, is equal to 10 kilonewtons. 10 kilonewtons. The question asked us, what is the weight of the balloon? Now, again, this balloon is in equilibrium, so let us draw the free body diagram. Let us say this is a balloon we have. There is a tensile force T over here, its self weight W over here, going down. There is only one force that is going up, and that is force of buoyancy. Force of buoyancy. Now, I can establish equilibrium and write summation of vertical forces is equal to 0. What does this imply? This implies that W plus T has to be equal to FB, which further implies the value of W is equal to FB minus force of buoyancy minus tension. Now, what is the value of force of buoyancy? Force of buoyancy is equal to gamma of water multiplied to volume of water displaced, that is equal to 9.81 multiplied to volume of water displaced over here is pi by 6 times d cube, that is 1.6 cube. If you calculate this value of FB, it approximately comes out to be 21 kilonewtons. FB comes out to be 21 kilonewtons. What does this imply? This implies the weight has to be equal to 21 minus 10, 21 kilonewtons minus 10 kilonewtons. This implies the weight of the balloon is equal to 11 kilonewtons. So the answer for this question is 11 kilonewtons. A vertical gap 23.5 mm wide of infinite extent consists of oil of specific gravity 0.9 and viscosity 2.5 pascal second. A metal plate 1.5 meter cross 1.5 meter cross 1.5 mm weighing 50 newtons is to be lifted through the gap at a constant speed of 0.1 meters per second. Please highlight constant speed over here. Estimate the force required to lift the plate. Let us construct a diagram to understand this. Imagine you are having a vertical gap. Let us say a vertical gap where these two walls are fixed. In between these two walls you are having a fluid, and in between you are having a plate. In between you have a plate over here, let us say completely enveloping is a fluid we have. This is a fluid we are having. Regarding this fluid, he has mentioned you two things. One is a specific gravity equal to 0.9, viscosity equal to 2.5 pascal second. These two things he has mentioned regarding the fluid. Regarding the plate, he has mentioned you weight of the plate is equal to 50 newtons. Further, he has also mentioned you the volume of the plate, that is equal to 1.5 meter cross 1.5 meter cross 1.5 mm. This has been mentioned. Further, he has also mentioned you that this distance is equal to 23.5 mm. 23.5 mm. Now, I want you to imagine 23.5 mm. 1.5 mm is consumed by this plate. If it is so, then this distance over here, this distance over here, and this distance over here, both of them are going to be equal to how much? 23.5 minus 1.5 will give me 22. Half here means this is 11 mm and this is 11 mm. So 11 mm of viscous fluid on either side of the plate you are having. Now the question says that this plate has to be lifted up. So let us say you are lifting up this plate. The plate is supposed to have a constant velocity equal to 0.1 meters per second. And in order to lift this, you require a particular force. That force is equal to how much is the question. I hope the diagram is explaining the question quite well. Now let us see how to start solve this question. If I say that the velocity over here is constant, that means acceleration is equal to 0, which implies net force has to be equal to 0. So I am going to draw the free body diagram, write the equation of equilibrium. I should get the answer then. So let us draw the free body diagram now. Let us say this over here is the plate. This is a plate we have. There is a force we are applying over here. That force is equal to F. There is a force coming down in the name of weight. Since the body is displacing a fluid, therefore there has to be another force over here. That force is Fb. Since you are lifting the fluid against a viscous fluid, lifting this body against a viscous fluid, you are supposed to have shear forces on either side. Let us say Fs and Fs on either side. Now if I write the equation of equilibrium, I can say by equilibrium, summation of vertical forces has to be 0, which implies F plus Fb has to be equal to W plus 2 times Fs, which further implies the value of F has to be equal to W plus 2 times Fs minus Fb. The lifting force F over here has to be equal to weight of the plate minus twice the shearing force, because on either side you are having shearing force, minus force of buoyancy. Now we already know the value of W. We do not know the value of Fs, we do not know the value of Fb. Let us calculate each of these things. Let us first of all talk about Fb. Fb has to be equal to gamma of fluid multiplied to volume of fluid displaced. That is equal to, if you see, gamma of fluid is equal to 0.9 times 9.81. This is the gamma of fluid we have. Volume of fluid over here is equal to 1.5 meters cross 1.5 meters cross 1.5 into 10 power minus 3. From here you get the value of Fb. Moving further, the value of force of shear is supposed to be equal to shear stress multiplied to shearing area. That is equal to mu into du upon dy multiplied to shearing area. So the value of Fs has to be equal to mu, we know, is equal to 2.5 multiplied to du by dy. If you observe, this end is supposed to have the velocity equal to 0.1 and this end is supposed to have 0 velocity. So 0.1 minus 0 upon, gap is 11 mm, therefore 0.011 multiplying area. If you see the shearing area, you are supposed to have over here 1 meters cross 1.5 meters. So therefore it is 1.5 cross 1.5. From here you will get the value of Fs. Take this value of Fb and this value of Fs, assemble over here. Then you would get the value of F required to lift the uniform velocity of 0.1 equal to 122.475 newtons. This is the value of force required to lift the plate. Now this is an assertion reasoning question. An air-filled balloon released down goes up and up till it reaches a certain elevation and floats in air. This is statement 1. Let us analyze the statement, whether it is correct or not. Suppose this is ground level. Air-filled balloon. The fluid around over here is air and you are taking a balloon filling with air. Now my question to you is, whatever is the density of the fluid inside and outside, both of them are same. So if you draw the free body diagram, you are going to have W and you are going to have Fb. If the density of this and the density of this, both of them are same, will you have any resulting thrust to lift this body upward? The answer is no. You won't have any thrust to lift this body upward. Therefore, there is no chance for air-filled balloon to keep moving up. Imagine that we change this question to a hydrogen-filled balloon. So let us say instead of air over here, you are having hydrogen. Then what would happen? The weight would be less, the value of Fb would be more. Then what happens? There would be a resultant upward thrust to keep lifting this balloon upward. In that case, the statement 1 would be correct. But since statement 1 is saying air-filled balloon, statement 1 itself is wrong. Statement 1 is wrong. The moment statement 1 is wrong, I can answer that option D is supposed to be correct in this case. But let us still see the statement 2. With increase in elevation, the atmospheric air density decreases. That means as you keep going up, density is supposed to decrease. That is correct. That is correct. As you keep going up, density and temperature, both of them are supposed to decrease. So statement 2 is correct. There is no point of reasoning over here. Therefore, the answer over here is supposed to be D. A solid body weighs 5 newtons in water and 7 newtons in an oil of relative density 0.85. The specific gravity of the solid body material is how much? This question is a question on apparent weight. Both these weights, 5 newtons and 7 newtons, both of them are not the actual weights of the body. They are the apparent weights. So we have discussed already that whenever you are having the ratio of apparent weight of two fluids or a single body in two fluids, that time you can mention apparent weight 1 upon apparent weight 2 is equal to S of body minus S of fluid 1 upon S of body minus S of fluid 2. This is the ratio we have. Now if you observe, in this case he has mentioned apparent weight 1 is equal to 5 newtons and the value of SF is equal to 1. It is in water, therefore SF is equal to 1. Apparent weight 2 over here is equal to 7 Newton, and this is in some oil which is having 0.85 as its SF. If I put in these values over here, it implies 5 upon 7 is equal to SB minus 1 upon SB minus 0.85. If you cross multiply, you would get 5 SB minus 5 times 0.85 is equal to 4.25, has to be equal to 7 SB minus 7. Further implies 2 SB is supposed to be equal to 2.75, which implies SB is equal to 2.75 divided by 2, that is equal to 1.375. Therefore, the specific gravity of the body is equal to 1.375. A floating body would be in stable condition when he has given you 4 options. Before reading the options, recall what is the condition for stability or stable equilibrium in the case of floating body. The condition is Gm has to be greater than 0. Gm has to be greater than 0. If you want to theoretically mention this, what does it mean? M has to be above G. M is metacenter. M lies above G. G is center of gravity. G is center of gravity. Now let us read the options. Option A says center of gravity is above its center of buoyancy. Now center of gravity, center of buoyancy is not important over here. M and G are important. Second one says center of buoyancy is above metacenter. Center of buoyancy above metacenter, again wrong. Metacenter is above center of buoyancy. That is possible, but this is the exact condition. Last one, metacenter is above its center of gravity. Perfect statement. So answer over here has to be D. Metacenter is above center of gravity. A cylinder made from wood S is equal to 0.6 is of diameter small d and length 2d. The cylinder is kept in water with its axis vertical. State its condition of equilibrium. Okay, very simple question. Let us say there is a cylinder. Something like this. This is a cylinder. Let us say it is kept in water. This is the interface. This entire height over here, is capital H. It is mentioned as 2D, where D is the diameter. D is the diameter. He has also mentioned that S of fluid, it is water, therefore it is equal to 1. S of body is equal to 0.6. This much is mentioned. We have to identify what is the condition of equilibrium, stable, unstable, neutral, what kind of equilibrium it is. Now we know for a floating body the condition depends entirely on Gm value. So we have to identify whether Gm is positive or not. Recall the formula for Gm. Gm is equal to I by V minus Bg. We have to now find out I, V, Bg, assemble them over here and check the value of Gm to get the answer. Let us start with I. I is the area moment of inertia. Area moment of inertia of the area in the top view at interface. That means at this particular level, whatever is the area, for that I have to find out I value with respect to rolling axis. The area is circular, so the value of I is going to be pi by 64 times d power 4. Let me save this as some equation 1. Okay. Now volume of fluid displaced. Now if you remember, some time back we have discussed that whenever you look for volume of fluid displaced, that time you are going to see SB upon SF multiplied to volume of body. This equation is valid for both prismatic as well as non-prismatic bodies. So this is equal to SB over here is 0.6, SF is equal to 1.0 multiplied to volume of the body is equal to pi by 4 into d square multiplied to h. H over here is equal to 2d multiplied to 2d. If you calculate this, it comes out to be equal to 1.2 by 4 is equal to 0.3. 0.3 pi d cube. This is the value of volume. Let us save this as equation number 2. Finally, we have to get the value of Bg. How to get the value of Bg? Look over here. In this entire diagram, this point, let us say, is point G, and there is some point over here. That point is point B. If you measure this distance, that is from the bottom till point G, then this distance would come out to be equal to capital H by 2, and this distance would come out to be equal to small h by 2, where small h is the depth of submergence. So from here I can say the value of Bg has to be equal to, that is, this distance has to be equal to, capital H by 2 minus small h by 2, capital H by 2 minus small h by 2. Now over here I can say the value of small h for a prismatic body we have mentioned some time back. The value of small h is equal to SB upon SF multiplied to capital H. So small h has to be equal to 0.6 divided by 1 multiplied to 2D. So small h is equal to 1.2D. Now I can write over here Bg therefore is equal to capital H by 2 means 2D by 2 minus small h by 2 means 1.2D by 2. Therefore the value of Bg is equal to D minus 0.6D, that is equal to 0.4D. Let us save this as equation 3. I have the value of I have the value of V, I have the value of Bg. Now I can write Gm is equal to pi by 64 times d power 4 upon 0.3 pi d cube minus 0.4d. This value is equal to, now pi and pi cancel, d power 3 cancel off, d upon 19.2 minus 0.4d. I'm continuing over here. The value of d upon 19.2 minus 0.4d approximately comes out to be, approximate value is minus 0.35d. Now please see over here, the sign you are having is negative. That means you are having a negative value of Gm. If Gm value is negative, therefore this has to be a case of unstable equilibrium. The answer is B over here. Let us start with the topic of rigid body motion now. This topic is only present in IS examination. It is not there in GATE examination. Under rigid body motion, we are going to see two topics, two subtopics. First topic is going to deal with translation of fluid. Second topic is going to deal with rotation of a fluid mass. The topic of rotation will be discussed later on in Bernoulli equation chapter under the heading of vortex motion. Under the heading of vortex motion. Now, what do we study in rigid body motion? Imagine you are having a fluid mass which is being accelerated or which is being moved such that the entire fluid mass is moving like a single rigid body. In that case, there is a relative equilibrium created between the fluid particles. That is why this topic is also referred to as relative equilibrium. In this topic, we are going to have our Pascal's law still valid. I hope you recall that Pascal's law is valid as long as the shear stress is equal to 0. In this case, the fluid might be moving, but still the shear stress over here is equal to 0. Now let us see the topic of translation. Under this topic of translation, let us see the first case I am taking is that of vertical translation. The first case is of vertical translation. Vertical translation. Now, what do we do in this vertical translation? Suppose you take a container of fluid. You accelerate the fluid either vertically upward or downward as if the entire fluid is moving like a single rigid body. So imagine you are having a container in which there is a certain fluid present. Let us say the property of the fluid is gamma. You are accelerating the fluid in the vertical direction with a certain acceleration Az. Now, by the virtue of this acceleration Az, what changes are developed in the pressure measurement in this fluid we are going to see. Let me also add over here that this fluid is having a column height of capital H. Now what I do is I draw the free body diagram of this fluid along with the plate below. So let us say this, let us say, is the fluid, and below I am having a plate. Now this fluid is having its own weight W over here. Furthermore, this fluid is pressing the bottom plate with a certain force F. The bottom plate is replying with a press over here, let us say F, and then there is an acceleration over here Az. These things are developed. I can say on this particular fluid, summation of force has to be equal to mass times acceleration. I take z-axis, I get z-axis over here. If you see in z-axis, I am having F upward minus W has to be equal to mass times acceleration in z, which further says that F has to be equal to W plus mass times acceleration, or let us say mg plus mass times acceleration in z, which implies the force over here is equal to mass common to g plus Az. Now what is the value of mass? I can write that the value of mass is equal to density times volume. It is equal to density times, if you see the volume, it is equal to cross section area multiplied to the height h. Therefore, this implies that the value of force is equal to density into cross section area times h multiplied to G plus Az. This is the value of force. Now I can say that the value of pressure has to be equal to force upon area. If pressure is equal to force upon area, this implies that the value of pressure is equal to density area H multiplied to G plus Az whole divided by area. I cancel off area on both the sides. If I cancel off area, I am left with the equation pressure is equal to rho into G plus Az multiplied to H. This is the equation. Now I want you to observe this equation. Pressure is equal to rho G plus Az multiplied to H. Please observe this equation. I am having G plus Az over here. I wish to call G plus Az as G effective. If I call G plus Az as G effective, from here I can get that the value of pressure. In general, we know pressure is equal to rho GH, but now it is going to be rho into G effective multiplied to H. This is the equation I'm getting. So whenever you are having a vertical translation created, the effective acceleration due to gravity is going to change. Now mind you, I'm having over here a vertically upward acceleration. Since it is upward, I have taken plus Az. If I was having a downward acceleration created, I would have taken over here minus Az. Ultimately, the formula would still remain same. Pressure is equal to rho into G effective times H. Now, I can say, summarize from here that whenever you have a vertical acceleration, the effective acceleration due to gravity changes. Please visualize. Imagine you are standing in a lift. Let us say this over here is a lift and you are standing over here. As the lift starts to move upward, it is accelerating upward. What would happen? You would feel yourself to be heavy, is it not? Something very similar is happening over here. The fluid is feeling heavier. Its gamma value, which was supposed to be rho times G, has now become rho times G plus Az. It is feeling heavier. Similarly, if you're standing in a lift and the lift suddenly moves down, it is accelerating down, you would feel yourself to be lighter. Same thing is happening in the case of fluids also. The density is rho, of course, but the gamma value was supposed to be rho times G. Now the effective gamma value would become rho times G minus Az when the lift is going down, is it not? Same thing what you feel in the case of lift is happening in the case of vertical translation over here. One more point I want to add over here. Please remember, we are talking about accelerations. If we speak about velocity, nothing is going to change over here. These things are not going to appear. For example, if I have a container with a fluid, let us say density is a property, I am moving this fluid up with a constant velocity, let us say 10 meters per second constant velocity. If you ask me what is the pressure at this point, I would say rho GH, that's it. There is going to be no change. Remember, we want acceleration to be created in order for the equations to change. Okay, if you find these things difficult to remember, the simple way you can remember is anything you add with G has to be acceleration, because G itself is acceleration. That is why you are not looking for velocity, you are looking for accelerations over here. So if you have a question having constant velocity, forget about all these concepts, use a common equation rho GH. This is regarding the concept of vertical translation. Under translation, the second case we are taking is that of horizontal translation. Let us say 1B, horizontal translation. Horizontal translation. Now, in the case of horizontal translation, you're taking a container of fluid, you're accelerating in some horizontal axis, let us say x-axis. For example, suppose you have a container filled with the fluid up till a certain height over here. Let us say you're accelerating this fluid forward with an acceleration ax. This is how you're accelerating it. Let me define some geometry. Suppose this length over here is equal to capital B. This height over here is equal to capital H. This is capital H. Now, when you start accelerating, please think logically. When you start accelerating over here, then the interface which was initially horizontal, it should now become inclined. So, let us say the interface is now becoming inclined. The interface is now becoming inclined. This is the new interface I am having, and let us say the angle of inclination over here is equal to theta. Let me further go on to say that the new height developed on this left hand side, let us say this small height over here, I represent by small h. If there is no spilling of fluid taking place, I can say same is the height small h over here. The height small h over here also is same. My first aim in this topic is to identify the value of theta. So, our first aim is to identify the value of theta. So, let us say theta is how much? This is the first thing. Now, simple trigonometry will help you find out theta in this case. Go by symmetry. If there is no fluid spilling out, by symmetry you can say that this length over here has to be equal to half this base, therefore b upon 2. Now, look at this triangle over here. This triangle with angle theta has opposite equal to small h, adjacent equal to b by 2. So, I can say from here tan theta is equal to opposite upon adjacent. Therefore, the value of tan theta is equal to 2h upon b, or you can say theta is equal to tan inverse of 2h upon b. This is the equation we are having. But I can't be satisfied with this equation for theta. The reason is, please imagine you're accelerating furthermore. If you accelerate furthermore, the fluid will start to spill out. Once the fluid starts to spill out, the amount of fluid present previously and the amount of fluid present now, both are not same. So, this equation will now be not valid. Therefore, I have to replace this 2h upon b by something which is more universally used. Let us see how to develop that. To understand that, what I do is, I will take the deformed shape of the fluid and its free body diagram. So, let us say the deformed shape of the fluid is something like this. This is a deformed shape of the fluid. Of course, the angle is theta. Angle is theta. I am not drawing it over there. I see that the fluid present over here is pressing the left hand side wall with certain force. Whatever force it is pressing with, same force is acting back on the fluid. So, let us say there is certain amount of force over here F1. Similarly, the right hand side wall is being pressed with some F2, and the wall is replying back by the virtue of Newton's second law, again by F2. And I know that this entire fluid is accelerating with Ax. Now, I can say by Newton's second law, summation of force in x has to be equal to mass times acceleration in x. So therefore, I can say F1 minus F has to be equal to mass times acceleration in x. Now the question is, what is the value of F1 and what is the value of F2? F1, the value of F1 has to be equal to gamma times area times h bar. I am denoting A1 and H1 bar because it is for F1. That would be equal to gamma times. Now please concentrate. What is the area this force is acting over? I see that this height right now is equal to capital H plus small h, is it not? I have not defined the vertical over here. So please imagine the vertical perpendicular to your screen is equal to 1 unit. Therefore, it is capital H plus small h multiplied to 1 unit. This is the area. And what is the value of h bar over here? Half the distance from the interface is going to be capital H plus small h whole divided by 2. Therefore, I have capital H plus small h whole divided by 2. From here, I can say that the value of F1 has to be equal to gamma upon 2 multiplied to capital H plus small h whole square. This is the value of F1 I am having. Now that I have the value of F1, I can move forward to the value of F2. For finding the value of F2, I'll use the same procedure. Gamma times area times h bar. This time A2 and H2 bar. That is equal to gamma times. Now this should be easy for you. Please tell me what is the height you see over here. It is equal to capital H minus small h. Therefore, capital H minus small h. Width perpendicular to your screen is 1. H bar is equal to half of capital H minus small h. Therefore, capital H minus small h by 2. This yields that the value F2 has to be equal to gamma by 2 multiplied to capital H minus small h whole square. This is a value of F2. Next thing, coming to mass. Let me save these equations first. Let us say this is some equation 1. This is some equation 2. Now coming to mass, I know that mass has to be equal to density times volume. That is equal to density times. Initially the volume I have and later on the volume I am having, both of them are same. The volume is B multiplied to capital H multiplied to 1 unit. So B multiplied to capital H multiplied to 1 unit. This is a mass. Now assemble all these things in the equation. So I have, from here I can see that gamma by 2 multiplied to capital H plus small h whole square minus gamma by 2 multiplied to capital H minus small h whole square has to be equal to density B capital H multiplied to acceleration Ax. Now I can say gamma by 2 is common multiplied to. Now you see capital H plus small h whole square is equal to capital H square plus small h square plus 2 times capital H small h minus capital H minus h small h, capital H minus small h whole square. That is going to be minus capital H square minus small h square again plus 2 capital H small h. This should be equal to density times B into H into Ax. Now you observe capital H square and capital H square cancel, small h square and small h square cancel. I am having gamma by 2 multiplied to 4 capital H small h. So I have over here gamma by 2 multiplied to 4 capital H small h has to be equal to density times B times capital H into AX. I can cancel off over here capital H and capital H. 2 cancels off, 2 remains over here. Now, one more thing I can do is density can be cancelled off and G will remain over here. I wanted to replace 2H by capital B. So I see over here that 2H by capital B, 2H by capital B is equal to AX upon G. What does this imply? This implies that the value of theta over here is equal to tan inverse of AX upon G. This is the equation I can use. Theta is equal to tan inverse of AX upon G. Now, I was having this equation, but this equation was not always valid. It was having its own limitation. You can use this equation only if you are having no spilling taking place, and if there is a closure to this container, the fluid should not touch upper head, then you can use this equation. If any other case is happening, you have to use this. That is why I recommend forget about this equation, only use this equation over here. Again, let me recall that all these translations we are seeing should have acceleration. We are not worried about velocity alone. Imagine I was having a constant velocity over here. In such a case, there would not be any change in inclination. Change in inclination is only possible when I am having acceleration. So I can summarize over here that whenever we have a horizontal translation, horizontal acceleration, the line of constant pressure and the interface, both are same now, they are going to change their inclination by an angle theta. The value of theta is equal to tan inverse of AX upon G. All the other lines of constant pressure are also going to change their inclination similarly. So this will be how the lines of constant pressure will arrange themselves, all of them inclined by an angle theta. The third case we are having is that of translation along incline. Imagine there is some inclined surface. Let us say the angle of inclination is alpha. On top of this surface, there is a container in which, let us say, you have a fluid. And you accelerate this container along the incline with an acceleration A. This acceleration A is going to give you AX as well as AZ. The value of AX over here is supposed to be equal to A cos alpha, and AZ is supposed to be equal to A sin alpha. Now, if you recall, horizontal translation is going to create a change in the inclination of the free surface, and vertical translation is going to effectively change the acceleration due to gravity. So both these things are going to appear in this case. Let us say the surface is inclining by an angle theta. Now the first question over here is, what should the value of theta be equal to? Please recall, the value of theta in the case horizontal translation was equal to tan inverse of ax upon g. It was, I'll write over here, tan inverse of ax upon g. This was the value we got previously. But now I can't hold the same formula as good over here. The reason is I'm also having az. Remember, whenever you have az, all that is happening because of az is the value of g is going to change. So I can say this is equal to tan inverse of ax upon g effective, which further implies the value of theta is tan inverse of ax upon g plus az. This is the first equation we have. Theta is tan inverse of ax upon g plus az. Next thing, let us say the hydrostatic force on the left wall over here is equal to F1, on the right wall it is equal to F2, and further this height, let us say, is equal to capital H, and this height over here is equal to, let us say, small h. I wish to find out the value of F1 and F2. Now start with F1 first of all. I know that the value of F1 has to be equal to gamma into A1 into H1 bar. Gamma A1 H1 bar. But this time, you see, gamma is having G already. Therefore, I am not supposed to write gamma, I am supposed to write gamma effective. That is equal to rho into G plus AZ. This is gamma effective over here. Area. Area is equal to capital H plus small h multiplied to 1 unit, and H bar is equal to capital H plus small h whole divided by 2. Therefore, the value of F1 is supposed to be equal to rho into G plus AZ multiplied to capital H plus small h whole square divided by 2. This is the value of F1 we have. Similarly, if I look for the value of F2, I know that F2 has to be again equal to gamma effective multiplied to area, this time A2, multiplied to H2 bar. Again I can write from here that F2 is equal to rho into G plus AZ multiplied capital H minus small h multiplied to 1 multiplied to capital H minus small h whole divided by 2. Therefore, the value of F2 has to be equal to density into G plus AZ multiplied to capital H minus small h whole square divided by 2. This is the value of F2. Now say I choose 2 points. A point over here, let us say A, and a point over here, let us say B. I want to find out the pressure at point A and the pressure at point B, PA and PB values. PA, you see, pressure is equal to gamma multiplied to this H. But then again, I won't be using gamma, I'll be using gamma effective. So this is equal to gamma effective multiplied to H plus small h, that is equal to rho into G plus AZ multiplied to H plus small h. Coming to PB, again gamma effective multiplied to H minus small h, that is equal to rho into G minus Az multiplied to plus Az, plus Az multiplied to capital H minus small h. So in the case of translation along an incline, it's a combination, you can say, of both horizontal translation as well as vertical translation. So you can summarize by saying, in the case of vertical translation, the effective acceleration due to gravity changes. In the case of horizontal translation, the angle of inclination of the free surface is going to change. In the case of incline, you are going to have a combination of both horizontal as well as vertical translation. This completes the concept of translation.